Right. And first, I would like to thank the organizers, especially Professor Biancani and Professor Mazzoli, for giving me this chance to introduce our recent work. My talk is about the new high TC superconductors, which are primarily by using high pressure extreme conditions. We have many collaborators, including my students, my colleagues, and the Institute of Physics, Chinese Academy of Sciences, and our collaborators in the east of USA and in Max Planck Institution in Germany, and in the NSRC in United States, and Professor Uchida Uemura from Tokyo and Columbia University. Today, I will mainly introduce one of the topics. The material is barium 214 plus 4 minus Y, which has a similar the crystal structure. You see the 214 structure, and then quite different with the LA 214 is that in the barium 214 you have the reverse of the orbitals. Usually d square minus square is on the top of the z square, but in this case it's just reversed. And then of course the material is synthesized at very high oxygen pressures and temperatures, but once it's quenched or recovered to the ambient case, and the material is a superconductor, the TC can be as high as 73 Kelvin. So this is a very surprising results. So this is what I'm going to talk today. If I have time, I will introduce two hydride superconductors, which are our recent works. And one is the calcium polyhydrides, which can be superconductor and 180 gigapascal. It's very high, but the TC is also very high, 210 Kelvin, higher than that. And the other one is the high polyhydride is zirconium. It still is which superconductor and very high pressure, more than 200 gigapascal. TC is about 70 Kelvin. And this is once we have done previous, like quick escape this one, and then back I switch to the 214 structure. So this is a very classical one, early 214. And the main point of this structure is you have the oxygen, copper oxygen 6 octahedral. And because the Young-Taylor effect and also the very strong interlayer, the Chasez-Zezel layer and the CO2 plane layer, very strong Coulomb repulsion. So this is a octahedral has a distortion along C-axis. So you have the orbital order like this. S square minus Y square is on the top of the Z square orbital. And this S square minus Y square is just near the Fermi level. So this is the electrons which are contributed to the superconducting properties. Although this is the configurations we are just obtained from the 214 structure, but actually this is a very universal for all the high TC cuprates. It is the X square minus square is dominated for the superconducting properties. So based on this, the orbital order configurations, this is an update phase diagram of high TC cuprate, and it's very complicated and very comprehensive. And still, there is some of our mysteries which we are not very well understand. And then the paramechanism. Paramagnetism for the high TC cuprate, people believe is D wave. So this is experimental results. It's no doubt. And then let me change it to our results. And this is the crystal structure, as I mentioned, and which are synthesized and using very high oxygen pressure and high temperature. This is the facility. This is my students who is the first author of this paper, Wu Minli. And he devoted almost more than 2 years and to upgrade this machine to create a very high oxygen pressure and to optimize the recipe in order to get the single phase of 214 structure. And then I like to dedicate this work to Professor Ke-Jin Zhou because during the process we consistently get his encouragement. Unfortunately, he passed away last year, and this is the main results we dedicated to him. And pressure which are needed to the synthesizer about 18 gigapascal. Of course, this is a very high oxygen pressure, and plus 1,000 degrees C. We have discussed with Professor Zhou because his team, is very has a lot of studies on the overdose, the high distributor. I will mention this later. And then the difference that with the LA214, this you will see this the autohandler instead of elongated as the universal case, it's compressed along the C-axis. And with compress of the C-axis, you have the orbital order reversed. So disease square becomes dominated in the electron pockets. So once we release pressure and the temperature, we recover the sample, we measure the properties. This is measured at ambient conditions. So the TC is around 73 Kelvin. This is pretty high TC, and the volume fraction is up to, if you take a look at the field cooling MAR, then the volume fraction is more than 20%. So that means this is the bulk property. It's not a filamentary on the impurity on the mineral phase. So this truly is the properties of the sample itself. And if we compare this case with the standard, the orbital order case from the LA214. So this is LA214. Usually the TC around 40 Kelvin if you optimally dominant sample. And then the barium 214, our TC is around 73 Kelvin. So it's almost 80% for enhancement. So this is very strange and one very unusual case for the orbital reverse. But because people usually believe this disease square is harmful to the superconductivities. So once you get a sample, you get the real sample you measured. It's just a different story. Then we have collaboration with Professor Wimula in Columbia University. He's really is an expert on the mu-SR. With mu-SR, we can get the superconducting volume fraction, which more than 30% and very low temperature, around 5 Kelvin. So this case is a consistent with what we measured before by using the magnetization susceptibility measurements, right? So it's a proof. It's kind of a bulk properties, and then we collaborate with Professor Buchner at Florida University. He's an expert on specific heat measurements, and from his measurements, you can see the TC around almost the same as what we measured from the magnetic properties, 73 Kelvin, and then we supply the field. Then you have the transition shifted to the low temperature, and this is again tell you transition temperature is consistent, and it's prompted for the bulk sample. So then let me shift to the structure itself. We measured the sample in our institute by using the X-ray diffraction. It's just roughly measurement because, as you know, X-ray is not sensitive for oxygen, but X-ray can give you a basic structure, primary structure form. Then with this primary structure form, then we have collaboration with Professor Ke-Jin Zhou and the NIST. which has a very good neutral source, and himself is also really expert on the high TC cuprate structure. Yeah, and he measured the the neutron diffraction and both the room temperature and the low temperature, and then the structure model is again is consistent with what we measured by X-ray. So if you take a look at the R factor, so the structure is quite reasonable. Then we have a comparison with both of the the room temperature and the low temperature, and A parameter and the C parameter. And then if you take a look at this kind of let me see this one with other modular cuprate, you will see this is Barham case is really strange. Let me see, it's C-axis, apical oxygen distance, quite small, quite short. So this gives you the rather unusual, the compressed, the octahedral configurations. And then if we put together this in-plane and out-plane copper oxygen distance, you have this the octahedral profile, and then consequently the opposite orders format. So just the opposite reversed. And from the very simple models, calculations, rigid band model, and you have the band structure is that instead of the universal, is just at the corners pocket, and you have the gamma point, and you have this another additional pocket. So this gives you additional carrier densities. So we also measure the XPS, and then the XPS gives you the this compare. Of course, we always compare with LA214. And if you take a look at the Barham 214 and LA214, it's quite similar, but the satellite peak is quite shifted to the low energy part. That means it's really in an overdoped state. And based on this, there are a couple of the models which are proposed to the Barham 214. In principle, this says this in this case, the superconducting state, most likely you have the D plus minus or even S plus minus pair state instead of a pure Davis state for the rest of all the other high TC cuprate. And then Professor Giacomo Grahali and his team measured this sample by using rigs. And I briefly just introduced his conclusions. A significant departure from a common quasi-2D electronic structure of the superconducting cuprate of the pure D square minus square symmetry. This means for the other cuprate, but this significant departure from that scenario is indicated to the Barham 214. And then I quickly go through the high TC hydride. And yesterday, Professor Ermas gave a very nice introduction. I skipped this part and directly to our results. Calcium case. This is our recent work published, just recently published. Then the materials were synthesized between 106 gigapascal and 190 gigapascal plus in situ laser heating. So first we synthesize them at high pressure, high temperature. Then we quenched from the high temperature and then maintain the high pressure. Then you measure the electrical conductance properties, and this shows one of the samples, which are superconducting and around 180 gigapascal. And then of course, we also measured, I didn't show you here, we also measured the shift of the superconducting change as an applied magnetic field. So when you apply magnetic field, then there is a transition shift to low temperature. So this is tell you most likely this superconducting transitions. And based on the transition of the shift of the TC as a applied math field, we can estimate the operative field, and then the coherence length. So this is a previous theoretical predictions for this calcium case. And in principle, this structure model, we just are tentative side, but not sure it's really this structure model. And there is two papers in sequence published in arXiv first, but recently all accepted, formally published. The other case for the superhydride is the zirconium case. This is the 40 elements. So before what we see, the superhydride is all the materials which are most likely the alkaline earths on the main groups. But this is the 40 elements. And because of the electron, I believe there's probably there is some of effects on the supernatant state. So the TCs for this material is not so high, 70 Kelvin. Of course, and very high temperatures, very high pressure, 220 gigapascal. And again, we measured the change of the TC at function pressure and estimated the critical field and the Ginsburg-Landau coherent length. So finally, I give a brief summary of the perspective. So this barium 214 seems a very unusual high TC cuprate, which has a likely different pairing scenario. And then the problem is that perspective is that because this is a reversal for the monolayer case. So if we apply this strategy to the CO2 plane, like mercury 2123, is it possible to further increase the supernatant transition temperature even in high TC cuprates? So this is for the first one case, of course, by reverse the optical order. The other is for both for the superhydride. Of course, this mechanism is very simple, conventional BCS theorem theory. The phono-mediated very strong electron-phono interactions. The problem for this one is that how can we reach such a high temperature and lower pressure, or even an ambient case? This is the perspective for the polyhydride. Maybe we can introduce some of the chemical pressures to introduce inner pressure, and then reduce the pressure, physics pressure apply, which are required to realize such high temperature superconductivity. So with that, I'd like to thank you for your attention. Thank you very much.
Okay, thank you. Do we have any questions, either here in the audience or on Zoom? Yes, there is a question. Just a second.
Thank you, Jean.
Yes.
Can you tell us which are the new the new direction where you're working now with new materials?
Professor Bialcani, can you repeat your question again?
Oh, can
you repeat your question again? I'm sorry, I didn't catch your point.
Oh.
Thank you for your talk. And can you tell us which are the direction? Hope to have a higher TC even in this direction. Thank you.
What's the TC? What's for which one?
What is the new direction in research materials in this matter? Do you work in other materials?
Yeah, I'm right now working on the over state. I think it's very interesting because I think the rest in this session, Professor Gauzzi and Conradson will talk about overdoped oxygen, overdoped state. I think this is one of our the main research topics because the sample can be quenched to ambient case, so you can extensively study the properties. So the other is that hydride, for the hydride case, we're trying to, release the pressures which are used to introduce a very high TC ship conductivity. I think the research on the high TC cuprate can give some of our, clues trying how to, reduce the pressure to the high TC hydride.
Okay, thank you very much. Let us thank the speaker once again.
Thank you very much.
And if you could please stop sharing, and I would like the next speaker then to share his screen. The next speaker is Andrea Gauzzi. The topic is high TC superconductivity in strongly overdubbed cuprates. I need a chunk.
Oh yeah. We.
If you can please stop sharing your screen.
Okay. I will. Okay, great. Thank you very much.
Okay, thank you.
Okay.
You're still sharing your screen.
I stopped.
You're sharing your presentation.
Okay, sorry.
I think if you allow me, Professor Jin, you are still the organizer. I think you should name Professor Marcelli as organizer again.
So I think Professor Scott is right. You should change.
Yeah, Professor Jin, you are organizer still, I think. So you should name either me or maybe me.
Oh, yeah. Okay, I have the power to do that. I don't know how to do. Yeah, I will try to. Yeah, we are.
Yeah, you go to participants and.
Okay. And I change it back to Professor Mazzoli. Okay. Yeah. Is that right? This should be back. So this should be okay. I changed Professor Mazzoli to be the chair.
No, I'm the organizer, yes.
Oh, you are the organizer, so you can change. Yeah.
Can you see my presentation?
Yeah, I can see.
Yes, we can see your presentation, yes.
Okay, can you hear me also?
Yes, I think it's okay if you start.
Good morning to everybody. It's a pleasure to be with you also virtually. And I would like to thank warmly Antonio Bianconi and Augusto Marcelli for their very kind invitation. It's always a great pleasure to participate in this stimulating conference. And a special thanks to Antonio for keeping the community alive in spite of all the difficulties that we had recently. So as Professor Jing mentioned, so we are interested in an unusual region of the phase diagram of cuprates, which is the strongly overdoped region. And by the way, I really thank Professor Jing for his nice talk that introduced the main concept. So let me put back the usual phase diagram we are accustomed to. And what I would like to show you is that not what is shown in this phase diagram, what is not shown in this phase diagram. That means in this strongly overdoped region where the doping P is as large as 0.4 or 0.5, and you see it's completely outside the diagram we are used to look at. Antonio asked me to give also a bit of historical perspective of the field, and for this I would like to really thank all the people who contributed to this work, in particular Ted Jebol and Massimo Marezio, who are no longer with us. And among the collaborators, I would also spend a word to Sandro Massida, who also passed away some years ago, who gave an important contribution to an understanding of the disorder in these overdoped cuprates. Now the main collaborators are Steve Conradson, who will speak later, who is the driver of this project and the expert in the spectroscopy and EXAFs. For the synthesis, Marit Karpinen in Helsinki and Edi Giglioli in Parma, former postdoc of Marit Mikko, current PhD student in Helsinki, Linda, Roberto De Renzi and Giuseppe Allodi for the NMR, NQR, and muon spin relaxation work, Paolo Radelli for the neutron work, Amir Hemadzet and Yannick for the physical property studies, Gianguido Baldinozzi for the structural studies, and Sandro, Alessandra Continenza, Gianni Profeta, and Fabio Bernardini for the ab initio studies. The outline is as follows. I will first spend a few words about the earlier results before 2019, let's say, that have been almost overlooked, and they concern mainly the so-called 1-2-1-2 system, more known as IPCO and ISCO. ISCO is just IPCO with the strontium instead of barium. I will say that high pressure oxygenation is the key to achieve strong overdoping, and I will summarize the anomalous superconducting properties of these systems. And then I will move on to more recent results. Professor Jean has already nicely introduced the system barium CO3 plus delta, and I will also mention the novel phenomenological scenarios that emerge to explain the results of superconductivity in the strongly overdoped regime. And then in particular, I will discuss the role of disorder and the different types of disorder and band effects before drawing the conclusions and mentioning the perspectives. So the question I would like to address is why has the overdoped region been so little studied in the past? We are all accustomed to the phase diagram where we have an optimum doping at around 0.15, which marks, divides, let's say, a region in the underdoped region where the properties are markedly non-Fermi liquid to a region in the overdoped area where the system seems to display more conventional Fermi liquid properties. And the reason probably why there was no interest in this strongly overdoped region is because of the so-called boomerang effect observed by Professor Mura, Bernard et al. That means that if we increase further the doping above the, let's say, 0.3, TC goes back. So in other words, the TC seems to scale with the superfluid density. So above the optimal doping, the superfluid density, which can be measured by means of muon spin relaxation spectroscopy, shows a boomerang effect. In fact, I would like to emphasize that only a few overdoped systems have been studied so far, in particular the lanthanum 214, the calcium-doped IPCO, and the thallium compounds. So difficult to say that these phase diagrams can be really universal. So here I would like to show that it is in fact incomplete, at least, because in the strongly overdoped region, we have still superconductivity at high TC, even higher than in the dome in some cases. And I would like to draw your attention to an old work carried out in Bordeaux by again Muller and collaborators, and which demonstrated for the first time, to the best of my knowledge, the possibility of stabilizing a trivalent copper. And to me, it's having this premise, it is quite unusual or difficult to understand why people, when superconductivity in cuprates have been discovered, didn't really start from this extreme, copper 3+, and prefer to study from the copper 2+ point. Possibly the reason is that these phases are require high pressure synthesis. Still, this work, which really stimulated later work by Ravo in Caen, and later, as we all know, Bernardo and Müller, already pointed out some very interesting. I hear some echo. I don't know if the microphone could be closed. In some of the speaker may have the microphone open, please. So I think that in this paper there are very interesting remarks. One is that the susceptibility behavior suggests a strong delocalization of the Eg electrons with the antibonding sigma band. And second, that the covalence parameter is higher than the critical values defined by Goodenough, suggesting a metallic character. And in fact, all these compounds are metallic, but not superconducting. So how we can obtain such a strong overdoping? Well, as I said, the key is high pressure. Professor Jean already showed the technique is based on multi-anvil presses. Here you see a cross-section of one configuration, the so-called Walker type, that can achieve high pressure oxygenation up to 25 GPa. And as oxidizing agents, typically we can use potassium chlorate or potassium perchlorate, or even oxygen silver oxide. And by carefully studying the phase diagram, we can achieve very high purities, better than 95%, typically in powder form. And here I will report, as already said, results obtained in Helsinki, in Aalto University, in Marit Karppinen's group, or in Parma by Edi Giglioli. So how can we be sure that the system is highly overdoped? Well, one typical tool is a spectroscopic tool, typically Xanes, the L-edge of copper. Here I show some earlier results obtained by Antonio Bianconi's group in the early days of superconductivity. Here is this case of lanthanum 214, slightly, let's say, lightly doped in the superconducting state, but in the low TC. And you see that the two absorption peaks split by the spin-orbit coupling, corresponding to the creation of the hole in the P3½ level to fill the D level completely. And then we look at the Mazzoli results, the lanthanum CO3, where lanthanum is 3+, and you see that the peak is now split in two, let's say A peak and B peak, and the B peak at higher energy correspond to what we now understand as the creation of a ligand hole in the copper. So we have basically a 3+ configuration. And by considering the relative intensities of these two peaks, we can quantify the valence. In fact, some people already tried to study cuprates in the strongly overdoped cuprates, Stephen Conradson found for example, this PhD thesis by Luis Marco De Zanetti in Professor Chu's group in 2000, where he claimed to have overdoped IPCO up to 8, so with delta equal 1. However, these results, for some reason, were never been published, and for several years, nothing happened until Mari Karppinen's and Isao Yamauchi in Japan, and then Massimo Marezio and Ke-Jin Zhou and others studied this so-called homologous series, which is basically IPCO, in the case S equal 1, where you replace barium with strontium, and then you can obtain other members of this homologous series with the several reservoir layers, still with the 2 superconducting layers per unit cell. And this series is very interesting because it shows some definite trend, and definitely the TC is very high, is basically similar to that of IPCO, up to 87 Kelvin. Again, the spectroscopic results are quite compelling because remember the shape of the Kapper L-edge spectrum. In the case of the S equal 1 compound, you clearly see a strong component of the Kappa 3+, which is weaker in the other members. And so this corresponds to the highest valence of Kappa for the S equal 1 compound, which is almost equal to half a hole, extra hole per Kappa in the plane, whilst the other members correspond to a weaker, still significant overdoping. I should focus on the S equal 1 members, which has the maximum TC, 87 Kelvin. And here I compare its structure with that of IPCO or ISCO. So in the case of IPCO, as you know, we have a orthorhombic symmetry with the chains. Here, the chains are not shown. In the case of strontium, you create disorder in the basal plane so that the system becomes tetragonal, and the TC drops from 91 Kelvin to 63. Interestingly, when you substitute partially the Kappa in the chain site by molybdenum, you recover basically the original TC of 87 Kelvin, but still the disorder in the basal plane remains and the symmetry remains tetragonal. The reason why molybdenum has been chosen is because molybdenum is hexavalent, and so it facilitates the oxidation process. So the keywords are that through this partial substitution, you obtain very high doping and a highly disordered basal plane and a tetragonal structure. And here you can find the references, Okai et al. For the ISCO, Kao et al. Choose in Paul Chu's group again for ISCO, Giglioli et al. Again for ISCO, and Grigoravichute and Chamaisem for the S equal 1 compound. So it's true that the synthesis of these compounds is quite challenging, at least in order to obtain single phase. One has really to master the high pressure synthesis and to identify very reproducibly the pressure and temperature conditions. So we are talking about 2010, and still these results didn't create any impact or very little impact. So Massimo Marezio and Ke-Jin Zhou asked me if I could complete the work using in-depth neutron study to show that this system is really a single phase and we have really bulk superconductivity. So we did that and published the paper in 2016. Again, the samples synthesized by Mikko Nisula and Mari Karppinen in Helsinki. And we obtained basically a perfect structural refinement with no trace of impurities except a residual few percent of potassium chloride and calcium perchlorate. And as in the case of Professor Jin discussed, we have a bulk superconductivity because we have about 30% Meissner effect, and the transition is quite sharp. The structural analysis shows already many years ago, so we are mentioning 2016, a very unusual structural property that Professor Jing mentioned. So already at that time, we noticed that actually it was Ted Jebol and Massimo Marezio who were really interested and puzzled by this structural property, that the apical oxygen distance is very short, much shorter than in the other cuprates. And this accounts for the large valence. Using the so-called bond valence sum, we estimate the valence to be 2.45, perfectly in agreement with the value 2.46 obtained using Xanes. So we are really well beyond the dome, and this record short distance indeed indicates that we are in a multi-orbital system. That means that both EG orbitals are occupied. So just for comparison, remember that IPCO7 optimally doped has a apical oxygen distance of 2.298. So you see there is a difference of 0.13 angstrom, which is huge. And also we noticed a clear that our data completed a trend already observed, that the shorter the C-axis, in other words, the shorter the apical oxygen distance, the higher the TC. So our compound corresponds to this red point. Then I just recall Professor Jing results that after a few years, this new system, which is very different from the previous one, with a strong overdoping, has been reported, with TC again very high, and again with this structural anomaly of having a short apical oxygen distance. So this is similar to the copper molybdenum 1212 system. However, as Professor Jing mentioned, there are defects in the CO2 plane, so there are some further anomalies in this compound. And again, the Xanes spectra nicely shows the presence of kappa 3+ in the B peak. Now, recently we tried to cover in a more complete manner the overdope region. And so we varied the concentration of oxidizing agent. This is the point that we already found with the maximum oxygenation, and then we reduced the oxygenation. The C-axis goes up, but in this range of doping, still the TC seems to be constant. So surprisingly, the TC seems to be saturated. So that is a puzzle. And in order to try to understand it, I may show you the anomaly in the specific heat, which was already observed in the overdoped lanthanum 214. In a superconductor, you expect that the residual specific heat at low temperature is 0, because all electrons are paired. And this is the case indeed for optimally doped IPCO and optimally doped lanthanum 214, where you see the intercept goes basically to 0. But this is not the case for overdoped lanthanum, and also for the high pressure oxidized molybdenum substituted 1212, the black dots. So this means that there are some unpaired electrons, and Wang et al. In 2007 already found the systematics that starting from about 0.21 in the doping, the residual gamma starts to increase and then saturates in the normal state. And more recently, Ivan Bozovic group using optical conductivity measurement in overdoped lanthanum-214 films has seen that if you compare the optical conductivity in the normal state, in this case, for example, the TC is 27.5, and so at 32 we are in the normal state, we have the normal conventional Drude-like peak, and in the superconducting state you still have this residual Drude peak, as if some fraction of electrons was still impaired. More recently, we moved to the IPCO system in order to reproduce the results by Desanetti that have not been published. And so, again, with the Linda Zederholm, the Maritz student in Helsinki, she synthesized various compounds with different degrees of, with different concentration of oxidizing agent, in this case, of silver oxide. You still find almost constant, in this scale we see an increase, but in fact the difference is only 1 Kelvin, TC. And interestingly, we have that the structure becomes progressively orthorhombic. So
you have 2 minutes left.
Yes. So I'm coming to the conclusion. So in summary, the new phase diagram shows that we have a wide area in the overdope region where TC is high. We have basically almost constant TC as a function of doping. So in summary, we have bulk high TC superconductivity for doping up to 0.5, accompanied by record short apical oxygen distance, which implies multi-orbital superconductivity. We have a large fraction of unpaired holes, indication of saturation of superconductivity. Steve Kivelson admitted that in a recent paper in occasion of Ted Jabbol's 100th birthday, that we may miss, these results indicate that we may miss the understanding of the origin of the superconducting pair in cuprates at 0 order. So in order to continue, we are working on single crystallite to try to measure the transport properties. We are trying to grow single crystal to measure transport and ARPES. And we are trying to study the region between the usual dome and the superconducting overdope region, which remains to be studied. The question is, for example, if we have a Fermi liquid in this region, which has not been established yet, and whether we can reach the full overdoping. Thank you very much for your attention.
Thank you very much for this talk. Do we have any questions? Any questions on Zoom, maybe? I don't see any. Oh, there is one. Okay, just a moment.
So you say that you measure some unpaired holes in your system. How do you understand this presence of unpaired holes in the system within some scenario? I mean,
yes, that's a very, very interesting and important question. Thank you. Look, there are a couple of scenarios that have been proposed in the literature. One, I think, which is, in my opinion, is most interesting, is proposed by Ivan Bozovic group, is that there are phase fluctuations in the overdope region that destroy the superconducting coherence, and that results into the presence of a fraction of unpaired electrons. So basically, it's a dynamical quantum phase fluctuation process.
so is there any possibility that this is a hint of inhomogeneity in the system? Because you may have a metallic fraction if the system is not homogeneous. That, of course, is
Yeah, but yes, but to me, that what this lack of phase coherence means, that in principle all electrons are the same, because we don't have any indication of really chemical inhomogeneity. So you are right. We can envisage a phase separation scenario, but in dynamical terms. I don't think we can imagine
on some nanoscopic scale.
Yes, yes, definitely. Definitely, that's a possibility. I agree with you.
Thank you very much.
Okay, let us all thank the speaker once again. Move on to the next speaker, Stephen Conradson, with more on overdose cuprates, perhaps a different view.
Okay, great. All right, well, like everyone else, I'd really like to thank the organizers for continuing this for 26 years. It's been a very valuable conference, and I hope that we're able to continue. I'm going to be presenting results, additional results on these, especially the YB A2CU308, the fully overdoped material. And there's been a lot of collaborators on this. In fact, I've done very little of the work. Okay, so here are some of them that have contributed. Big international project. We send me around the world, and as well as samples for different experiments at different laboratories. Okay. All right, so if you do, as you've seen in this meeting, internet search, gives this, all right? Dozens, hundreds of the phase diagram that we all know and have, I guess, come to love, all right? But the question now is, what's the real phase diagram? Okay? As you can see, there's good experimental basis for this. This has just been shown in the last couple of pictures. If you go through the literature and you look at the experiments that people have done, what you find is yes, okay, that the dome exists, and as you overdope, that in both classes of compounds, YBCOs, the other layered compounds, and the lanthanum cuprates, you get this cutoff above the optimum doping. All right. Let's see. But there's a couple of outliers. Bernard Keimer just published this thin film on calcium doped lanthanum cuprate, and even back 30 years ago, there's some earlier work that showed that when you increase the oxygen pressure up to several atmospheres, perhaps there was a boost in the critical temperature with high oxygen stoichiometries. Right. So both Professor Jin and Gauzzi have talked about how you synthesize these highly overdoped superconducting cuprates, hydraulic press. They've also pointed out to a certain extent that these have been ignored by the community, despite having the first ones showing up in the literature just a few years after initial HT discovery. In fact, Jim Jorgensen is part of this in a 4-layered YBC compound, TC of about 115. He did the structure. All right. And so what we did very recently is Linda, student of Marit's, and I and our collaborators put together this review article. I encourage everybody to read it. And one of the things that we did was we went through the literature and we found some of these overdoped superconducting compounds. We made a table. And here's some of the ones that we listed in the table. So despite what Professor Jin and Gauzzi may have said, in fact, there's a very large number of these that have been put in the literature over the years, starting 30 years ago. And although some of these, especially at the beginning, were kind of sketchy, much of this work was very carefully done. So these are established, right? This is nothing new. And I have to admit that, like everybody else, I was unaware of these until I walked into Ted's office a few years ago. He said, "Why don't you study these?" So that's what we did. And so this is going to make a dramatic entrance for the phase diagram Professor Gauzzi just showed. So this, in fact, would be a much more accurate phase diagram for cuprates that includes these compounds that are made with this HPO process. All right, so again, highly overdoped superconducting cuprates, and this is not just a few oddballs or outliers, there's a very large number of these. Okay, so as you just heard, what's special about these? Well, the critical temperatures go up to 50, or the transition temperatures go up to 50 to 115 Kelvin, despite being overdoped. They break the trend of the higher TC with the longer copper apical oxygen distance. Many of these are quite short. in the barium cuprate, the inverted copper geometry. Professor Jin, after, I don't know, 20 years, is able to make single-phase strontium cuprate that he did not talk about. The XAFS experiments that we performed showed that there are oxygen vacancies in the copper planes. In fact, these are about copper oxygen 1.5. So in fact, it's part of the structure. Another odd thing about the strontium cuprate is that the magnetization, when we orient these, it's rotated into the plane. And when we just looked at yttrium strontium cuprate, we found that it didn't orient at all in a field. And of course, as Professor Gauzzi just pointed out, coexistence of superconducting fermi liquid carriers in the overdoped region. Okay, another thing we found from the XAFS is there's very large transformations of the dynamic structure at the superconducting transition. So normally when we have these transitions, of course, the structure is not involved, but what we see in these cuprates is that there is, but it's not the static structure, it's the dynamic structure. So in a lot of ways, it's very unfortunate these cuprates were ignored for this length of time. All right, so what are their structures? We put the extra oxygen in, it does not affect, or in fact, it enhances the superconductivity. Where is it going in order to be able to do that? So if we look at the compound we just saw in the last talk, this one with the molybdenum substitutions, we have a publication on this. Again, I encourage people to look at these. What we find is isostructural with parent YBCO, all right? And we'll show that the excess oxygen, in fact, goes into these open spaces between the copper 1 atoms. So these chains are being converted into partial planes. The XF showed that molybdenum was clustering, showed that molybdenum was all octahedral. And so what happens then is that the molybdenum atoms have 6 neighbors. This is just in the plane, 4 in the plane, and the 2 apicals. And of course, where there are interfaces with the coppers around these molybdenum clusters, then the coppers have unusual geometries too. They can have more than the 2 nearest neighbors that they normally have from the chains. So we have is, with the recipe for these YBCO compounds that are overdoped, how do we do these? Well, we start off with yttrium, barium, or strontium, the O7. We put in a substitute of a metal that prefers an octahedral trigonal geometry that wants to have a larger number of oxygen neighbors in its plane. Okay, so then when we substitute it for a fraction of the chain copper, what happens then is that this preferred geometry for the substituting metal facilitates the insertion of the additional oxygen from the HPO synthesis. All right, so that's one way we can make these. In fact, that's the most popular way in that list that I showed you. But when we go to the lanthanum cuprates that Professor Jin has been working on, for example, the strontium cuprate, which exceeds even what he was talking about for the barium cuprate. Its 95 Kelvin TC is more than twice as high as the parent lanthanum cuprate. So this HPO process not just only preserves the superconductivity, it very much extends it. So we have publication there. This just shows how when we orient the samples in a field, how unlike every other cuprate we studied, it orients along the vector in the plane, not along the C-axis. This compound is very special. Consistent with that, when we did the XAFs on the oriented materials, what we found was that the vacancies seem to be in one direction. The vacancies in the plane seem to only be in one direction, despite the compound being tetragonal. It's about half those oxygen sites along what we're calling the A direction are the ones that are vacant. 95 Kelvin TC, all right? So despite not having a CuO2 plane and these other odd things about the structure, TC stays quite high. All right, so the XF sees the dynamic structures. The metals are where they are crystallographically. The oxygens, well, there's a lot of oxygens that are missing in the planes. And we also saw that there's some very odd things about the apical oxygens. There are some long non-crystallographic distances that seem to indicate that the apicals had shifted, and so they often bridge some of the coppers in the plane instead. All right, so the HPOs, we take the YBCO type, we have this kind of approach where we can make them, and we know what the structures are. We look at the lanthanum cuprates, something else is happening. So there's multiple motifs as HPOs that all give high transition temperatures. And so what this means is that when we talk about order or disorder in HTSC, it's quite complicated. There is no single trend that we can identify. Okay, so let's talk about this YBA2CU308. So this is the thesis, Paul Chu's group. I talked with Paul, he stood by the work. He explained that he had not published it because the student had to go back to Brazil and there wasn't time, which seems like an odd explanation for something which is so radical. So just like all the others, the orthorhombic structure in the 7 collapses to the tetragonal structure. So this means that the peaks that we have in the diffraction pattern that signify the orthorhombic splitting will merge. So in this thesis, you can see how he did it. And in our series of compounds that we made, Linda and Edie and Marit, we had the same pattern, all right? He did it, we did it. Okay, you can track the lattice constants as a function of the increasing oxygen stoichiometry. He was able to do it, sorry, this shifted down. He was able to do it across the entire diagram. He went up to 08, and he had a whole series of compounds, all right, along the way, a whole series of stoichiometries. And so he was able to trace out the changes in the lattice constants, and we pretty much we duplicated what he had. As we increased the amount of oxidizer that increases the amount of oxygen in the material, we were able to get probably about 7.8, okay? And then because we have a different geometry for our press, we had to mix the silver in. He was able to keep it separate. And so this last point is probably just an anomaly because some of the silver oxide peaks overlap with the YBCO peaks. But what we did do, what he didn't do is we did the Rietveld refinement. I'm not sure why that wasn't done at the time. So we have the structure, and we did the XS measurements on the oriented samples. Good XS. The curve fits show that they matched the crystallography quite well. But of course, in terms of the location of the excess oxygen, what we did is that the oriented samples are able to look at the amplitude of the in the planes. All right, so in the AA plane, and of course, if we're inserting this extra oxygen into the site in the chain, the number of oxygen neighbors to the coppers will go up. And we know how much it should go up by. And so in our 7.8% sample, so here's our YBCO7 measurement. We go to the YBCO8, a little bit of noise, but it's almost exactly where it should be in terms of percent increase in the oxygen amplitude in the plane corresponding to the 07.8, so it agrees with the diffraction that we did as well. All right, and just for comparison, the molybdenum compound that's in green has an oxygen about 7.5. It's in between, it's where it should be too. So this method works. All right, so the structure is this, and where do the extra oxygens go? They go into these sites, and so these coppers that used to be the chain coppers are now making their own CuO2 plane. All right, they're octahedral. Okay, and TC stays the same. Oh, the other thing, of course, is that it is fully ordered. All right, when you go up to 7.8, there's no partially occupied sites in the material. Okay, that's the structure. That's great. What about the superconductivity? For some reason, these aren't showing up on. Okay, so in the thesis, of course, he did a variety of the susceptibility measurements. He was doing as a function of pressure on different stoichiometries or range of stoichiometries up to the 7.9 one that he had. This is what he got, showing that TC and the volume fraction do not change as a function of stoichiometry. And we get our series, and we get the same results that he did. All right? Okay. So there's his graph of TC, and again, this isn't showing up. Okay, it lost some of the things on the copy. So this is, zero field and field cooled. Here's TC going all the way up to his final compound, 7.98. And when we put ours on, if this had not shifted, then ours overlay as well, within a few Kelvin. All right, so we did it too. We started off with a little bit lower TC in our starting material that we use to oxidize. So we're climbing up and converging on the same location. Okay, TC stays high, 89 to 92 across the entire series. only varies by 2 Kelvin. And of course, the superfluid density given by this susceptibility is essentially constant as well. All right, so let's see, the one other factor, the experiment that Andrea just showed was, of course, the heat capacity. He was showing some other measurements as well. And what these show is that the excess holes or carriers seem to be going into a Fermi liquid phase. So this could be why the superconductivity stays pretty much the same. It's because the excess holes are being shunted into a Fermi liquid, as opposed to going into the superconductivity or becoming superconductivity carriers. An interesting point is in the molybdenum compound, unlike these others, we get this kink down at low temperatures. This is from Schottky effect. And of course, in the molybdenum with the molybdenum clustering, that's an inhomogeneous system. This makes sense that we see it in the YSCO MO. Okay, so what I've demonstrated is this is real. All right, this is not, gee, impurities, second phase, you know, or anything else. We really do have superconductivity going up to P equals 1. All right. So we duplicate also, this has now been duplicated to independent laboratories, which is the gold standard for science, right? It didn't change with time either. We did this 20 years apart because the thesis was done in 2000. All right, so what is the real phase diagram for cuprates? Again, making its dramatic entrance, this is it, right? So despite what I showed in that first slide and what many people have showed at this meeting, this is the actual cuprate phase diagram. All right, so we have two kinds of classes of cuprates, one of which gives the dome, and one of which, the superconductivity, extends all the way up to the maximum possible doping levels without changing. So all the coppers at the end are copper 3s. The copper ones are originally octahedral. They're not the same. So even though there's CO2 plenty of their own, they're not quite the same as the ones that were still there and are intact. Right. All right, so you can go to the literature, go to these meetings. There's a lot of theories for the cuprates that are derived from the dome, one of which is the order-disorder. Well, when we look at this new phase diagram, of course, those don't apply anymore because in the region, until we get up to 08, then of course the oxygens are going in different locations. So there's disorder which is present and all these other ones too, okay? So the dome or the extension is not really sensitive to order and disorder in these materials. And when we look at the lanthanum cuprate derivatives, those HPO compounds, those are much more highly disordered. It's a very odd kind of bonds in them. This was more complicated. And what we have to look at then is that there's certain structures that are compatible with this extension of the superconductivity. There's other structures which cause us to have the overdoped side of the dome. All right? Again, if you're talking about Coulomb repulsion as a mechanism for the overdoped side of the dome, like, well, it doesn't work anymore because we can put a lot more charge in than just up to there. As Andrea showed, there's XAS measurements, this one spot right here, and the others as well. Okay? So what can we say now that we are more enlightened with this new information, which is actually pretty old? Like I said, these were done a few years after. Okay, so after 35 years, and essentially hundreds of millions of dollars poured into this, what have we been studying? A very narrow slice on the underdoped side of the phase diagram. And all of our information pertains to only the fraction of cuprates that are doped with O2 or cation substitution, right? When you put oxygen with the HPO, you get this other phase diagram, which the superconductivity is much stronger than it is with these other methods that we've all been focused on. Okay? All right, so the profound result from this, though, is that the superconductivity saturates. We get up to optimum doping, TC and the volume fraction stay constant, even as the carrier density is increasing by a factor of 6. Okay, so perhaps that's a coincidence. Maybe something's happening with the band structure. It ends up being the same, even as we're putting a lot more oxygen in. It's kind of nice. I mean, YbCO8 is fully ordered, and so we can do the electronic structure calculations on the endpoint without having to make any kind of corrections for disorder from doping. And so we have some preliminary results on this. They're very interesting. We have to pursue this much further. But we find out as we go look at the Fermi level, and no, they are not the same. All right. So there's a lot of, as we expect, there's very large differences in the Fermi energy in the band structure. So this conundrum of the saturation persists. What's doing it? If the mechanism, any of the popular theories that have been proposed, then what is the origin of HTSC? Okay, so they pointed out this is pretty much catastrophic for a generic theory of HTSC, or the ones that we've been working on that are derived from the dome. All right, so then we go back and say, okay, so what aspect of the YbCO structure is maintained that would explain how it can saturate and remain constant? And what doesn't change much is the crystal structure. All right, but we don't look at the static structure, S of Q. We have to look at the dynamic structure, S of Q and E. And we can do that with XF. That's one of its real strengths. And as we know, we've been doing this for 30 years. We have the original results. What we can see is this difference with XF between conventional polarons and what we're calling at the time tunneling polarons, and try and clarify the situation. We now are trying to say internal quantum tunneling polarons. What happens is that we have our charge inhomogeneity. We've got the polaron and say the square lattice, and the sum of the charge, a fraction of it goes onto one of the neighboring oxygens. All right, which we know happens in these, right? Okay, and then that particular one, before the polaron can jump to the next copper site, we have an opportunity for this fractional charge to jump around by quantum tunneling to the other oxygen neighbors. And this is the internal dynamics of the polaron, and this is what is important. So let's see, we published this before on the dynamic structure. I'm running out of time. We have done XFs as a function of temperature with advances of the synchrotrons. We can now do it, get a good spectrum every 2 Kelvin, very fine temperature points on this. So we've done this now in the YSCO-MO and also the strontium cuprate. These are Fourier transforms, the XFs. We can assign these peaks to the various neighbors, and these are oriented samples. What's quite fascinating to look at is this big shift in these non-crystallographic oxygens right at TC in the strontium cuprate. And these are in the BC plane. Remember that in this case, it does not orient along the other axis. So if we take these two compounds, and what we're going to do is we're going to take the XFs, we're going to isolate just the IQTP parts of these, which we can do by subtracting off the other contributions. So in these two compounds, we're going to look at these specific oxygen neighbors. Okay, so 2 minutes left. So when we do this, what's interesting to do then is here's the apical oxygen YSCMO, and we see the 2-site distribution. There's these 2 distances right here, and we can see that there's a big shift in the relative amplitudes, the numbers of atoms when we cross the superconducting transition. This is the copper. This is the strontium XFs along the C-axis. All right, so we can see that these are independent measurements from the curve fits. We can see small changes in the distances. There's a fairly substantial change, the red line, in the difference in the number of apical oxygens at the 2 distances. And what's funny is when we overlay the strontium XF, from the copper to strontium pair, we see it almost does it exactly. And the same thing happens with the strontium cuprate. Again, we look at the amplitudes from one of the oxygens in the IQTP. We compare that with the amplitude of the strontium, and here they are. One's going up and one's going down. And so what we have is very strong coupling or correlation between the oxygens of the IQTP the strontium and the superconductivity. Because of course, for the strontium cuprate, this also happened right at the superconducting transition. And so what we've done is we're developing theories on this based on the dynamic structure. We had done this before. We did the exact ionization measurements on the IQTPs. What we've done now is we've advanced it. So we actually have 6 atoms, including the strontium and an oxygen in the plane. We have a pair of these copper oxygens. The copper strontium is anharmonic, so we have anharmonic coupling. We've been doing is treating these 2 copper oxygen pairs as oscillators. We're using the Kuramoto approach, and then we have the anharmonic coupling as the coupling constant in Kuramoto. And what we see is that a critical value of this coupling, we get a transition in the dynamic structure to a synchronized phase. So all of the oxygens are tunneling opposite to each other. And this is important for the superconductivity because in the synchronized phase, we bring the planar oxygen into the system and we're transferring charge into it. So the synchronization, we know, pumps charge in from the apical oxygen into the planes. And we've actually got more work since. We know a lot more than we did. And that's what I have to say for now. Thanks very much for listening.
Okay, thank you very much. We are out of time completely, so I suggest we postpone the discussion for the coffee break and move on to the next speaker, who is Gennady Longvenov. Okay, I'll try to. Yeah. No. No. I don't think so. Oh, yeah, we do. Okay, we do.
Okay, so first of all, I would like to the microphone. Yeah? First of all, I would like to say thanks to Professor Bianconi, Antonio for invitation me to here and the organizer for this nice conference. So today I will present a recent result related to high TC interfaces. In principle, after listening some talks, I have also some result which will be very good fit to this session, but I will follow my initial plans. So, plan of my talks is simple, so as usual, motivation, method, results, and then 2 points which I want to deliver to this auditorium. At the end, conclusion and test. So this is in literature a lot of papers about interfaces where different phenomena can be obtained due to different interplay between different mechanisms. But my focus is on the superconductivity, but basically high temperature superconductivity, which one can create by using cuprate-based heterostructure with different counterparts. So, however, questions which I have the following. First question, 2D high temperature superconductivity is homogeneous in plane or inhomogeneous? Second, inhomogeneity is intrinsic or extrinsic properties. What is minimal size which necessary to establish high temperature superconductivity? And last but not least question, what is the role of crystal structure point defects, including, of course, dopants. Dopants from point of defect chemistry is defect, but dopant defined high temperature superconductivity. And also, from point of chemistry of defects, oxygen vacancy also present in such ionic crystals. So this is my question, and now I try to answer at least on 2 of them. So my tool is oxide molecular beam epitaxy, which is set up in Max Planck Institute since 2012. So this is a commercial system from DC Instruments, and it's allowed us to grow high quality oxide films and heterostructures, so to combine different sequences. Let's start from first question about homogeneity of the interface. So this is a continuation of our work with Ivan Bozovic when we obtained high temperature superconductivity between overdoped cuprate, lanthanum strontium cuprate, and undoped cuprate. However, continuation in Max Planck, we did a study of chemical pressure effect. So we change dopant. With Bozovic, we work with strontium, but in Max Planck, we synthesize with calcium and barium. Here you can see a resistive transition for this different structure. You can see that TC different. So this means that somehow chemical pressure affect transport properties and superconductivity. Very strong support was in Max Planck was done from macroscopy group. So here you can see this is HDF image where you see very good pitaxial quality, coherence interface, but here you see chemistry. Basically, this is Yale's map, two-dimensional map, and you see that distribution of different dopant are different from calcium, strontium. They're different from one to the other. Here is some cartoon where we compare our two-dimensional interface with classical homogeneous doping, so just three-dimensional doping. So in here we have overdop site, and then there is some distribution of the dopant at the interface. Here we have random distribution of the dopant in the 3D material. So, first implementation from this is that distribution of cations or dopants affect transport properties. The other system which we study is two-dimensional doping of undoped cuprate. So we take, we take a parent compound, lanthanum cuprate, and we replace one lanthanum O layer, atomic layer, with strontium atomic layer. And while this compound is insulating and antiferromagnetic, we generate superconductivity in such artificial heterostructure. However, when we look in microscopy, characterized with microscopy, we find that this is HDF images. We see that these atoms, strontium atoms, are not sitting in one line. So there is certain distribution. How far this strontium distribute depends again on the dopant. So, for instance, for calcium, we have very strong distribution on the downward interface. However, for forward interface has almost same distribution. And you see the profile of the dopant is asymmetric. So the bottom interface is much sharper than the top. So this is the conclusion. So nominal interface look like this, but the real interface look like this. So, and this distribution of dopants are induced by diffusion, by segregation, and probably some electrostatic interaction, and so on. However, now we go to extreme case. Extreme case means before we work with 214 system, and we just change only dopant. Now we go to the system where we contact 2,1,4 phase with 1,1,3 phase, lanthanum manganate. And we insert also one strontium layer on each side from the lanthanum manganate 1,1,3 layer. We did different heterostructures. We call this, in case of cuprate, this is homoepitaxy because it's the same crystal structure, only chemically you insert some layer. But now we are dealing with heteroepitaxy. And result is again perfect epitaxy, perfect atom arrangement. However, two interfaces are different. And the other result is we have also distribution of the elements across interface. So, for instance, on this slide, you see a distribution of copper and manganese. So you have area where this profile overlap. So this and here you also can see interface nominal, where we put 113. This is these two inner error, and this is actual interface. So we extend basically, if you count these atoms in a cubic structure, 113 structure, we get extra unit cell on each interface where we have intermixing of the copper and manganese. And of course, we have overlapping with strontium distribution. But the interesting part comes here when you measure transport measurements. So here you see resistance measurements of this manganese cuprate interface or heterostructure and mutual inductance. So this is the real part of mutual inductance. This is imaginary. What is come out? You see onset in resistance is around, it's a little bit reduced compared with bulk or thin film. It's only around 30K, because in normal film, we can get up to 45 in these conditions. However, screening is completely suppressed up to 7K. And it's only the start screening, so it's not complete screening. So implication means that we have elementary superconductivity at the interface. Which interface at this moment, interface A or B, I cannot define. However, this is the cartoon, and we have intermixing, we have extra 113 phase, and this is basically how we consider that we have superconducting filaments or nanopatches at the interface due to interface intermixing manganese copper. And minimized size, I can conclude from screening mutual inductance, it's in the range of more than coherence length and less than screening length. However, the other question, can we somehow measure in other way this inhomogeneity? We did this experiment. We make a bridge or whole bar with dimension like 5 micrometer width, 40 micrometer length. Then the structure was this overdoped, undoped cuprate. It's homoepitaxial superconducting interface, but with two interfaces. Therefore, between two interfaces, we have insulator, and this insulator should increase our percolation effect if we have a percolation in the interfaces. And indeed, we get IV characteristic, which is nonlinear, of course, with critical current. But if you make a derivative, you get a lot of steps. So this is derivative steps correspond, of course, small steps, which you can see in IV characteristic. And this tell us that we are dealing with a certain array of, let's say, Josephson junction or whatever, and interface is not homogeneous. So this is the message from this curve. Now I come to the second point of my talk, which I want to deliver. This is information which we get from read. Read is reflection high energy electron diffraction. It's provide us feedback about growth quality. So the principle is simple. You have electron beam with 25, for instance, electron volt with small angle which come into the sample during growth, and you get the diffraction pattern like this. This very good feedback provide us information about initial quality of our film. So, for instance, this is read correspond to this resistance and mutual inductance result. So 42, this is single phase film, by the way, 42 Kelvin, sharp transition, but here you see some broadness. However, if you get a read like this, you get very sharp transition even in mutual inductance. Here, by the way, is schematic of mutual inductance. Okay, so this I skip because read gives us different information about surface quality, but important is that read also gives information about surface reconstruction, how atoms are arranged on the surface. Here you have read image, read image and lead image. So we use also lead to define. So from read we say that we have some superstructure with 5A periodicity, but from lead we say that this is one-dimensional stripes of atom arrangement. Then we check correlation with epitaxial strain. There is correlation, for instance, this is optimum doped cuprate on different substrates, tensile strain, compressive strain. We look on the influence of the chemical pressure, strontium doped, calcium doped. You see different number of superstructure lines. So for calcium is less by 1. And then also we find correlation with oxygen content. So we can grow in condition of complete oxygenation when we deliver ozone, and we can deposit copper in vacuum condition. And we see that we switch in vacuum, we have 4 lines, in ozone we have 5, and we can switch up and down by just re-annealing in ozone. So at the end, and additionally, we find that this superstructure depends on the doping level. So in overdope, we start seeing more. But important is, read give information not about electronic structure, it gives crystallographic structure of surface. So we come to this conclusion that during growth, we have ordering of dopant, strontium dopant, for instance, or calcium, in certain chessboard position, but additionally, with each position of the dopant, we have arrangement of oxygen vacancy, which we see in read. And this is why we have effect of the annealing in ozone and vacuum. Interesting also that this 5i correspond to optimum doped level. So this is crystallographic information, but recently there was a paper from Chinese group who did STM, and they do STM on STO, and as you remember on STO we have periodicity for superstructure 4A, not 5A. 5A is for compressive strain, and surprisingly, the correspondence with electronic structure and our crystallographic structure very, very good. So for A, for STO. So this is a very intriguing part for us. So this is basically my two main points which I want to deliver, that ITC interfaces are not homogeneous due to chemical intermixing, and ordering of the dopant can be responsible for electronic ordering, because dopant is the main player for phase diagram. And perspective, of course, wishes to develop new experimental technique where we can combine characterization in crystallographic and electronic properties, including also point defects, oxygen vacancy. Of course, the theoretical approach is very, very welcome. And at the end, okay, this my small team. These two guys are engineers. These two guys were PhD students. Thank you for attention, and
thank you for a very interesting talk and really beautiful results. I have a quick question. In the first part of your talk, you showed these two interfaces, top and bottom, where I believe the strontium intermixing was different. There was this asymmetry. Do you have a guess, an explanation why the top and bottom interfaces are different?
different is due to strain.
It's strained.
Strain, because LCO has larger in-plane lattice constant than overdop.
But in the same sample, the top and bottom.
In the same, yeah. This was reported in this first paper with Ivan Bozovic. When you inverse structure, it's different to see.
Great, thank you.
Is there any way you can compare these results with the inhomogeneity seen in STM experiments to see if it might have the same origin?
No,
this has been a question for STM.
No, this is my question. I just demonstrate this STM result.
Okay.
To say that this is correspond to our crystallographic result.
So it does. I was looking at all those stripes and some got lost.
Yeah,
okay.
Yeah.
This is a quick one. In Rome with my group, we have been working on inhomogeneous superconductivity at oxide interfaces, like lanthanum aluminate and strontium titanate. So you correctly point out that you have a minimum size for a domain to become superconducting, which is larger than the coherence length. But then to have zero resistance state, you need to form a percolating path. So the idea is, what do you think? Is this filaments or more or less homogeneous distribution of these superconducting paddles across your own system? Do you have an idea?
No, my idea is the following. In principle, this is my idea. Why I ask about size. I say that filamentary come from extrinsic, but intrinsic is in this small side. In principle, if you take conventional superconductor, you also can get nano grains where you have superconductor, but you don't have screening effect, right?
Yeah, right.
So my suggestion to theoretician, look just on small side and calculate 5 by 5 unit cell and find mechanism for for glue.
Okay, thank you. Thank you.
Okay, so let us thank the speaker once again.
Thank you.
And let us move on to the next speaker, Maria Vittoria Mazziotti. Where is it? Is this one? This one? No? No, this. Oh, okay.
Good morning. I thank the organizer for giving me the opportunity to be here today. In this talk, I present our recent results on multi-gap superconductivity at unconventional Lifshitz transition in three-dimensional heterostructure with tunable Rasbach spin-orbit coupling and electron-phonon interaction. This work was made in collaboration with the professors Antonio Bianconi, Andrea Perali, Antonio Valletta, and Gaetano Campi, and the Rickmas Institute at Roma Tre University. In order to explain the high critical temperature observed in many different compounds in the last 50 years, different theoretical approach was being proposed. In this work, we start from the BP-Boot theory proposed in 1993 by Antonio Bianconi, Andrea Perali, Antonio Valletta, in which the innovative idea was to consider geometry in which the quantum size effects are reflected in a multi-band electronic structure where the critical temperature can be amplified by a shape resonance due to configuration interaction between different gaps in different coupling regime. The amplification of the parameter then define the superconductive phase is obtained by changing the chemical potential around an isolated Van Hove singularity associated topological Lifshitz transition. In this theory, there is a very important limitation because the BP-Boot theory study only system without the spin degree of freedom. So using the Schrödinger equation in order to obtain the electron wave function without spin-orbit interaction. On the other hand, the Rasbach-Orcon theory of the superconductivity with the spin-orbit coupling is limited to two-dimensional systems and a single band metals. Another limitation of a previous theoretical approach is to consider energy scale in which the Fermi energy is greater than the spin-orbit interaction energy pairing. And in this theory not include the effects of the elasticity parameters variation. In this work, we consider a three-dimensional system, and for the first time, we did the spin degree of freedom in order to take into account a Rasbach spin-orbit coupling. So they need to solve the non-relativistic Dirac equation in order to obtain the correct shape of the electronic wave function. We will see that in this situation, there is an unconventional Lifshitz transition associated with an unusual Van Hove singularity extending on a circle in negative helicity states. Another central new aspect of this work is to overcome the previous theoretical approach in which an adiabatic limit was considered, because the most interesting physical effects take place when the Fermi energy is about equal to Rasbach spin-orbit coupling and the energy pairing. We will see that the combined effect of Rasbach interaction and the proposed three-dimensional geometry make it possible to change the critical temperature accurately. In a context such as that of the BCS theory, in which the effect on the variation of the crystalline parameter was not taken into account. Here, instead, we will see that it is possible to change the Rasbach spin-orbit coupling by changing the modulation of the superlattice structure. The three-dimensional geometry proposed in this work is schematized in this figure, and we have a three-dimensional heterostructure quantum layers with periodicity D made of two different metals of amplitude W and L. In this system, the electron in the XY plane are free, but there is an anisotropy due to confinement of the electron along the Z direction. So in this system, the quantum size effects are not negligible and the spectrum appear split in n subbands. The central new aspect of this work was to take into account for the first time that the interface electron exhibit a strong Rasbach spin-orbit coupling due to the breaking of inversion symmetry. This breaking is reflected in a spin flip with a null magnetic field. A very important aspect of the Rasbach spin-orbit coupling is that this spin-orbit coupling can be tuned through a transverse electric field. The difference between the Rasbach splitting energy and the Fermi energy of the two possible eigenstates define a length scale LRSOC about equal the periodicity of the superlati. This means that unlike a bulk system in which the Rasbach spin-orbit coupling can be only compared with the Fermi wavelength, in this case it can be compared with the modulation of the heterostructure. So it's possible to change the intensity of the Rasbach spin-orbit coupling by changing the periodicity of the system. The system proposed can be described by the following Hamiltonian, in which H tilde R is the single particle non-interacting Hamiltonian due to potential confinement potential along Z and Rasbach Hamiltonian, whereas alpha is the Rasbach constant defined by the following equation, in which alpha SO is a dimensional constant linked to the strength of the Rasbach interaction in units of D. In order to take into account the superconducting phase, we have added this Hamiltonian standard interaction Hamiltonian by the following equation. In order to study the normal phase, numerically the normal phase, we have chosen a two-band system and the following parameters for the model. This figure shows the dispersion along X for the first and for the second subband, where delta Z is the dispersion along the confinement direction, and delta RSC is the shift Rasbach defined by the following equation. First, we have studied the dose for the second subband. We have plotted the total and the partial dose for two helicity values as a function of the Lifshitz parameter defined as the chemical potential minus R up omega 0, where R is defined by the following equation, as a function of alpha SO, in order to obtain three different cases in which the dispersion along the Z direction is greater or equal and less of the Rasbach spin-orbit coupling. For the positive helicity, the dose shows a typical trend of three-dimensional system and a trend very similar to the trend obtained without Rasbach spin-orbit coupling. In the case of negative helicity, we can be observe a peak in the dose. This peak appears at value of beta R equal to delta RSC up omega 0. This quantity, depending on alpha, this peak shift to the left increases as the Rasbach spin-orbit coupling increases, shift to the left. In order to highlight this variation with alpha, we have plotted R up omega 0 as a function of alpha SO for the first and for the second subband for two different helicity values. In order to understand the peak in the dose, we have studied the quasi-particle dispersion and we have plotted the isoenergetic curve in the KZ-KX plane. The Fermi for the first and for the second subband, only for the negative helicity eigenstate. For alpha SO equal to 0.4, because for this value, the dispersion along the Z direction, the energy cutoff, and the shift Rasbach is equal. According to several work of Bianconi et al., in which this condition represents an optimal condition for the amplification of the parameter then define the superconducting phase. The Fermi surface can be obtained by rotation of the isoenergetic curve around the KZ axis. The peak in the dose is linked to unusual variation in the topology of the Fermi surface for negative helicity states. In particular, when the chemical potential reaches the bandage of the subbands, a three-dimensional Fermi surface begins to form. The system is then subject to a first Lifshitz transition. When the chemical potential reaches the top of the subband, there is a Lifshitz transition on the second type, in which the Fermi surface goes from a three-dimensional to a two-dimensional geometry. For large value of the chemical potential, the Fermi surface becomes two-dimensional. In the second Lifshitz transition, we can be observe an unusual van Hove singularity in which the Fermi surface shows an interior curve or nodal point and no isolated singularity, which explains the appearance of a peak in the DOS. The radius of the curve increases at the Rasbach spin-orbit coupling increases, and this is reflected in the shape of the DOS to the left. In order to study the superconducting phase, how this unusual property in the normal space are reflecting the parameter that identify the superconductive phase, we have studied the total Hamiltonian using an approach, and standard Gorkov-Rashba approach. After long complex analytical calculation, we have obtained the self-consistent equation in which the firing potential has a dependence on the momentum through the phase factor due to the Rasbach spinor and a dependence on the ETC index through lambda factor, while the quantity delta MKZ does not explicitly depend on the ETC index nor for the momentum. The self-consistent equation has a shape similar to the BCS self-consistent equation, but shows a very important difference, because in this equation appear an overlap integral due to interference between electron wave function in different subbands. So the coupling, the superconductive coupling, is not constant, but has a matrix structure whose elements depend on the band index on the wave vector along the zeta direction. So it's possible an unconventional intra-band coupling, electron-phonon coupling, but also an unusual interband coupling due to an exchange interaction. The possibility to change each matrix term allows to study the superconductive phase when different condensate coexist in different coupling regimes. In order to study numerically the superconductive phase, we have studied the self-consistent equation in two limits, for temperature equal to 0 in order to obtain the gaps, and for T equal to Tc in order to obtain the critical temperature. In this figure, we report the gap at the critical temperature as a function of the Lifshitz parameter for different value of alpha SO. And in this figure, we have put the energy cutoff about equal to 30 MeV, equal to dispersion along the second subband. In this figure, we can observe an unusual behavior and amplification of the parameter that identify the superconducting phase around an unusual van Hove singularity. But the gap and the critical temperature are a symmetric function of the Lifshitz parameter and show the typical shape of a Fano anti-resonance, with a minimum at the first Lifshitz transition and a maximum at the second Lifshitz transition when the Fermi surface change from three-dimensional to a two-dimensional geometry and the DOS shows a peak. So is it possible to observe an amplification of these quantities as alpha SO increases, but we have a limit condition about equal alpha SO about equal 0.4, because for alpha SO less of this value, the critical temperature grows slowly, and the gap for the first subband is greater than the gap for the second subband. And for alpha SO greater than 0.4, the critical temperature grows faster and faster, and the gap for the second subband become greater than the gap for the first subbands. So we have an optimal condition for the amplification of the critical temperature when the shift Rasbach is greater than the dispersion along Z and greater than the energy cutoff. In this figure, we have plotted the gap for the second subband for alpha SO equal to 0, alpha SO equal to 0.4 as a function of Kz. This figure shows a variation, a small variation, the gap for the second subband around an unconventional Lifshitz transition. where the rule of the change integral become very important. We ally this change, this variation on the Fermi surface in proximity of the unusual Vanove singularity, using the same color of the gap, for the gap. According to the choice of parameter phase, the left panel shows the maximum possible value for alpha SEO is 0.7. Above this value, there is a partial overlap of the band, and we can be work of energy cutoff about equal 60 MeV, 60 MeV, and to reach the typical critical temperature observed in the cuprate. According to this choice of the parameter, we can be describe many different compounds, in particular MGB2, by choosing omega 0 that about equal 15 to MeV. But we have taken into account that according to the Mingdal theory, there is a relation between the renormalized cutoff energy and the par cutoff energy, described by the following equation, and due to the screening of electron. In this figure, we have plotted the critical temperature as a function of the energy for alpha SO equal to 0, 0.4, and 0.7, as a function of G and omega 0 according to the Mingdal theorem. For alpha SO equal to 0, the critical temperature increases as the superconducting coupling increases. For alpha SO equal to 0.4 and 0.7, the maximum of the critical temperature can be amplified by the Rasbas-Spin-Orbind interaction. But with the Rasbas-Spin-Orbind coupling, exists a validity limit for the Mingdal theorem that correspond to G equal to 0.4. Value for value of G greater than this 0.4, the critical temperature to start to decreases. As now in high critical temperature superconductor, the critical temperature does not have a single value, but describes a dome at pressure, the charge density change. In this work, for the first time, we have reconstructed the superconducting dome. For this end, we have plotted the critical temperature as a function of the Lipschitz parameter, which is equivalent to change the chemical potential, therefore the charge density, as a function of the pairing energy. Is equivalent to change the pressure. The results, the projection, this dome in the plane G eta R, is shown in this figure, and on this dome there is many possible paths, and this make our model highly predictive. In order to reach critical temperature close to the room temperature, we have tuned the parameter then define the geometry of the heterostructure. In particular, we have seen that by changing the amplitude of the potential barrier and keeping the periodicity of the lattice fixed, put the alpha SO equal to 0.7, is it possible to reach energy cutoff about equal 90 MeV, and so critical temperature close to the room temperature. Indeed, in this figure, we have plotted the maximum the critical temperature for omega 0 about equal 90 MeV, and this choice of parameter allows to reach the same critical temperature value observed for the H3S compound. In conclusion, the main aim of this work was to theoretically and numerically study the electron structure of the superconducting property of a superlattice of quantum layer with Rasbas-Spin-Orbit coupling. A very important conclusion that the Rasbas coupling induces an unconventional Lipschitz transition associated with an unusual Vanove singularity in the negative helicity state. The complexity in the property of the normal phase is reflected in an amplification of the gap on the critical temperature for precise energy range. In particular, the amplification improves when the chemical potential is made to change around an unconventional Lipschitz transition. In this situation, in addition to the Cooper coupling, must be taken into account the key role of the quantum configuration interaction that appears in the equation the gap, and which can be calculated considering the change interaction between pairs of singlets in subband with different number and different helicity. So exists an optimal choice of all the parameters involved in order to obtain a critical temperature close to room temperature. Indeed, the amplification of the superconducting phase parameter improves when the Rasmussen spin-orbit coupling band shift is greater than the dispersion along Z of the highest energy subband and the cutoff energy. In such condition, the possibility of changing the intensity of the Rasmussen spin-orbit coupling, changing the periodicity of the system, become very important. This provides indication for possible practical realization. I thank the Professor Antonio Bianconi, Roberto Raimondi, Sergio Caprara, Andrea Perali, Antonio Valletta, and Gaetano Ciampi. Thank you very much for your attention.
Thank you very much for a nice talk. I have one question. So as far as I understand, you introduce in your model the superlattice structure in one direction, and then you treat the two-dimensional electron gas in the perpendicular direction as free electron gas, so with p square over 2m dispersion. How much more difficult would it be to take into account the lattice periodicity in these planes perpendicular to the superlattice structure, so including a dispersion in this direction, like a band dispersion, not a parabolic dispersion? How much more difficult, in your opinion, would be this?
Allora, sì,
if you go back, for instance, to the slide where you introduce your model, okay. Yeah. So taking into account that the band may have a kind of cosine, say, dispersion, would it be technically more difficult or just a matter of
analytical difficulty? Very reader. Yeah, we
the reason I'm asking this is the following. If you take free electron, then as you say, there is a full circle of degenerate state once you introduce the Rasmussen spin-orbit coupling. But in a lattice, this circle is no longer degenerate. You remove this degeneracy, so somehow you weaken those singularity that you see as an entire circle of degenerate points. So this is the reason why I'm asking. There you plot a full circle of degenerate point, and this is only fully degenerate if you have a free electron, so a parabolic dispersion. In the presence of a cosine or of a sine-like Rajda spin-orbit coupling, you partially lift this degeneracy. So of course you have a very shallow region where the states are nearly degenerate but not really degenerate. Okay, but I understand that it would be much more difficult because then you would have to solve equations that are no longer
along the Van Hoek singularity, yes.
Okay, thank you very much.
Thank you very much. Thank you.
It's better probably. We have a few very interesting talks today, and I would like to ask the speakers to keep in time so that there is time for questions. And the first, not to waste any time, let me announce the first speaker. It's Vladimir Dobrosavljevic, and he will talk about metal insulator quantum criticality in TMD bilayers.
So, first of all, I would like to thank Antonio, he's still drinking coffee apparently, for bringing us all here. This is my first conference after COVID. And I heard that at a recent conference, someone asked Tom Devereaux, what is the talk that you like the most? He says, I don't care, about talks. I only care the fact that I'm back in real life. And so I say the same thing, it's really great to be here, and thank you for coming to this talk. So my main interest in life has been mental and social transitions, and I would like to share with you today some very recent development that has taken place actually during somehow just before and during COVID times, new discoveries in this area which have sparked a lot of new activity. So this is work done with my two graduate students, and I particularly like to stress most of the work was done by Yuting Tan, my student who is now finishing soon and will be looking for a postdoc. She's a wonderful theorist that I think has a very bright future, and Luke Rademacher, who is my more senior collaborator in Geneva. So the mental and social transition is a very old problem going back to the early days of solid state physics. Everyone wants to know if it's a metal or an insulator, and in absence of change of symmetry, as you tune some parameter going from a conductor to an insulator, you may ask what are the mechanisms that will stop electrons from moving. And there are two main mechanisms that have been proposed. One is the interaction effects, as emphasized by Mott, and Anderson emphasized the role of impurities in scattering. Which one of the two is dominant depends on the material, but this is a problem that hasn't been understood very well, and part of the reason is because we didn't have very good platforms to study this very carefully, which has changed very recently. So today's talk will have a focus actually on the regime where disorder plays a big role. We have worked on this problem for a long time, in particular in the context of strongly correlated systems like heavy fermion and others. And there are some review articles that I wrote here. But this preprint here that's on the archive is about the work that I'll be describing to you today. So anyone who wants to know the details, which I won't be able to explain, then they can have a look at that paper. So the big discovery that has taken place in 2018 was these bilayers. Everyone probably knows, I'm sure, of what they are. First discovered in graphene, but graphene had the property that it's actually very complicated, and there are some very intricate topological effects associated with the Wannier functions in graphene. However, a couple of years later, these people and some others, this group at Cornell and some other people have discovered that transition metal dichalcogenide bilayers, like this one where you take tungsten selenium-2 and tungsten molybdenum tellurium-2, such bilayers actually turns out that when you put them together, this creates a very narrow band. That in fact can be modeled by a simple triangular lattice and a simple Hubbard-like model. So it's much simpler, and it's a platform to test many ideas from the past. And so that's what I'll be discussing today. They also developed some wonderful new tools. This excitonic sensor, this group developed the excitonic sensor. You can measure magnetization and many other properties in great deal. And another very important thing is that there are these metallic gates on top and the bottom of this device, and that allows you to tune both the bandwidth of these narrow bands and the band filling, which is very difficult to do in almost any other material studied in this field. Now, much of the early work on these materials, including this particular work by Shan and Mack, has actually focused on the regime where the strong correlations are playing a dominant role, and that happens when the narrow band, which is about only 20 millivolt wide, is half-filled. When it's at half-filling, that's when the strong Coulomb repulsion plays a dominant role, and they find a Mott transition that can be tuned by keeping the electron density at half-filling and then tuning the bandwidth. So this has been studied. The curves are shown on the right, and what I would like to stress here is that if you look at these curves here observed in this Moiré device, you see the metallic curves, you see these maxima, and then crossover to an insulated state. These curves are almost identical to those seen in another platform to model the triangular Hubbard model, which is the Mott organic materials, totally different in chemistry and energy scale, and the 2D electron gas in semiconductors. All of these systems show essentially the same features, which is really remarkable, because if you can identify some common themes, then you can really start to understand something that is universal. I'm actually not going to be speaking about this regime today, even though we have this review article here on the archive that's been posted a couple of weeks ago that discusses similarities between these systems and discusses various theoretical scenarios that have been proposed. My take here is that one particular theory, the one that is my favorite theory, dynamical mean field theory, actually seems to explain most of the observed features in all of these materials in a rather successful fashion. But what's remarkable about these devices is that you don't have to sit only at half filling. You can go to any filling you want. And there's some very interesting physics at other fillings. So in particular, so if you have a half filling, you have 1 electron per side of this triangular lattice. But if you go to lower fillings, then these electrons they repel each other. And it turns out that the intersite and the on-site Coulomb repulsion is in fact larger than the bandwidth. So this is a very strong coupling regime. And they find in the experiments by Shan and Mack, done through this oxytonic sensor, they find insulating states at many fillings, ranging between 1 filling where you have a Mott state down to 0. So you have all these Wigner crystal states at commensurate fillings, which is a remarkable discovery. And now it's a challenge for theorists to study. We actually are working on this with Luke Rademacher. We have some results that are going to be posted very, very soon. But I just want to say one word about this. Many people have discussed these periodic crystals, which happen at filling 1/3, 2/3, and etc. Here you can see the energy of these states, commensurate states versus filling, and you can see some of them are winning at different commensurate fillings. Now, one thing that we discovered that follows our earlier work on theta organics is that they are, in addition to these periodic states, which is the ground states, there are metastable amorphous states even in absence of disorder. So this is like a self-generated glass, and they can be found in this purple strip at any filling, and it's very likely, and there's some preliminary evidence that, in fact, you can study this glassy physics here in great detail, and this may be dominating many experimental features. Again, this is something for the future. We have some results on this, but today I would like to focus on yet another regime, which is completely different than what I just mentioned. And that's the regime where you take a narrow band that's split from the broad band by a broad gap, and you go to filling 2 electrons per unit cell. So this is a full band. You can think of it as a band insulator. And then by broadening these bands, which they can do, you can close the gap to the other bands. So this would be like a band transition. And then you can ask, if we go through this transition by tuning the bandwidth at integer filling 2, then what is the nature of the metal insular transition, which you can think of it as a band transition. And this is shown in these curves. This is, in fact, you can download these data from the supplementary material on their Mott paper of Shan and Mack published last year. And what you see is that the family of curves, from the airplane, they look similar, but if you look in some detail, you'll see that transport signatures are completely different than in the Mott regime or in the Wigner-Mott regime. So let me just run you through some features that you can observe. On the metallic side, far from the transition, you see remarkable linear resistivity over a broad temperature range. That gets reduced in temperature. The range where you see this shrinks as you approach the insulator, and it's shown here by this T star line. So T star is the temperature below which you see linear behavior. So the linear behavior is not a feature of the transition, it's a feature of the metal. Second, if you look at the residual conductivity, which you can easily see here that it's finite here in the metal, it drops. And if you plot the residual conductivity as a function of this displacement field, which tunes you to the transition, you see that it actually drops smoothly down to 0. And you, at some point, it extrapolates at some point here. On the insulating side, there is activated behavior, and the gap goes to 0 exactly at the same point. So this is a continuous transition. We can exactly see here very clear where the transition is, but here's an interesting feature. If you look at these curves, you'll see that the slope of the linear resistivity changes sign, and it becomes 0 at some point here, which is shown by this dashed line before the transition. It's not the slope changing sign, that's not the metal insular transition, in contradiction to what many people outside this field think. But this is a phenomenon which Mui first found in the 70s, that the change of slope of the resistivity or coefficient of temperature coefficient of resistivity changing sign, that's something that happens before the transition and not at the transition. So all these features to people working in disorder-driven metal insular transitions are very familiar. They've been seen, similar behavior has been seen in many, many alloys and doped semiconductors and in other systems. And in particular, this change of slope is shown here. It's interesting here that if you plot that slope as a function, as you approach the transition, as a function of the residual resistivity, it first goes up, the slope goes up, and then it goes down, changes sign, and to minus infinity at the transition. So these are some very pronounced features, and they're very similar to everything that you see in disorder-driven transitions. So that caught really my attention. This is all completely different than the mod regime. So you may ask, well, what's the disorder doing here? And how can we understand this from a simple physical picture? So the simple model that we used is just a model with few bands. And then as you tune the bandwidth, these bands can either overlap or not. If the bands are narrower, then there will be a gap. So what is actually creating a gap is not disorder, it is just the band overlap. However, when the bands do overlap, there are very small pockets, electron hole pockets shown here. And these pockets, they have a small Fermi energy. So once these pockets become small enough, just before the band split, then there's a small energy scale associated with carriers, and that the system becomes vulnerable to both disorder and interactions. So the resulting of the density of states is shown here. You can see the gap as we approach from the insular inside. The gap closes at some point, and then we have a metal. So one thing I would like to emphasize is that once these pockets are small and you put some disorder, then the pockets, the Fermi surface becomes ill-defined because the two bands are starting to mix due to interband scattering, and you can no longer think in terms of the band picture. And this is where the disorder and the interactions play a dominant role and modify the transport properties in the vicinity of this transition. So the simplest theory that can be written down to describe this model. So, I didn't say what is the model. So this is a tight binding model. We have disorder here, random site energies, and then we just add some boson, described here by the Holstein term. This is an unnamed boson, but we needed to describe at least the linear resistivity on the metallic side to describe the thermal properties. And in addition, this boson can perhaps be affected by disorder as well in some cases. So the simplest theory is something that you can think of it as a Landau theory for this kind of problem, where you basically have to ask how the interactions in disorder modify the electronic states, and not only at zero temperature, but also how the scattering at finite temperature is modified and we can calculate this in a self-consistent way, where the self-energy is computed in a local approximation. That becomes exact if the coordination number is large, but I think the correct way to think about this is like a Landau theory that is the simplest consistent theory. It's a conserving approximation in the sense of Bateman-Kadanoff, and it can be applied to any model in any regime. This theory has in fact previously been used to describe how interactions, bosonic correlations can be affected by strong disorder, and this Mui phenomenon a few years ago, where you can actually show that the same model and the same theory can be in fact used to describe polarotic effects, where once the electron becomes not so mobile, then the coupling to these bosons renormalizes the random potential dramatically to completely change the behavior of the system. So this is a very simple theory describing how scattering can be described in a disordered systems with moderate interactions. And now let me show you some results of this theory. So this is the experimental result that I've described to you just a few minutes ago. And this is the theory that we have found in a simple two-band model by adding this bosonic term in the model. And as we change the bandwidth and we go from a metal to the insulator by shrinking the bandwidth, we can see now all these features are exactly reproduced. Here are the families of curves. You can see the temperature T star below which you have linear behavior. You can see it in the experiment, and this is theory. You can see the residual conductivity going smoothly to zero at the transition, the gap shrinking to zero at the transition, and the slope going up and then down. The reason why that happens is because far from the transition, the disorder is not as important, but as you're reducing the Fermi energy of carriers, then the phonons are more affected or are more effective in the slope coming from these bosons, scattering due to thermal excitations becomes more effective than if you have a larger Fermi energy. So all these features we can understand in the simple theory we can solve these equations numerically, but in various limits, We can also solve it analytically, like these critical exponents that we have found here from the numerics. We can also obtain them analytically. And the procedure that we do this is by expanding the equation in powers of the relevant order parameter, like in the Landau theory. And we basically have a very simple but complete understanding of everything that's going on. So we can go a little bit further. And the fact that this is a continuous transition where all the energy scales vanish when you further transition from either side in a parallel fashion, that suggests that like in standard critical phenomena, we have now a quantum critical phenomenon where in addition to just plotting these energy scales, we can in fact take the whole family of curves and collapse it on a scaling plot. People who are familiar with classical or quantum criticality, they know that in this case we have to divide the resistivity by the critical resistivity curve, which is the resistivity plotted at the transition as a function of temperature. And in the experiment, you can see that on the log-log plot, it diverges as 1 over t. In our theory, we also get 1 over t. And then once we divide it, then the rest is the scaling function of temperature. And this temperature scale, crossover temperature scale T0. You can scale the data, the experimental data, to demonstrate this. And when you do that analysis, you find that scaling is beautiful, almost perfect. And not only this, but the scaling function that describes the experimental data shown in with dots falls right on this theoretical curve for the scaling function. So we have complete understanding of scaling. The crossover temperature displays parallel behavior as expected and vanishes as the power to the distance of the transition with an exponent mu z. And here is the phase diagram that you think has plotted. But this is not artwork. This is, in fact, the resistivity plotted R over RC, plotted on a logarithmically stellar coded scale across the phase diagram. And you can see how each segment is another order of magnitude in resistivity. And you can see they all converge here. This is a beautiful example of quantum criticality. You can see the quantum critical region. And you can see also the MUI region, where the resistivity slope changes sign, which is outside the strict quantum critical region. So everything is shown in the experiment and in this theory to obey the hypothesis of quantum criticality. And so this is perhaps the first example of a mental insular transition where we had so much experimental control that we could map the entire phase diagram, demonstrate quantum critical scaling. And not only this, but in fact develop a theory that can reproduce this not only qualitatively, but even quantitatively in the sense of the universal aspects of the theory are numerically in agreement with the experiment. So I just want to say a couple of more words in the last few minutes. And the question is, how general is this description or the validity of this physical picture? I told you that here the insulator is obtained by splitting the bands. But not all the transitions driven by disorder having involved band splitting. So you may ask, well, is this picture specific to this particular band structure or it's more general? Well, this is a kind of question that Anderson talked about in his Nobel Prize winning lecture. And he said that the effects of modern Anderson, the interactions of disorder, they supplement each other. So he anticipated in a poetic way at the time that when you have strong disorder, the interaction effects will be enhanced. And so perhaps even if you don't have two band splitting, but if you have a partially filled band, then you crank up the disorder to approach the insulating state due to disorder, you may wonder what happens. Is it completely different? Is it the same? There are STM experiments on all kinds of systems. I only show 3 examples. All known systems show that pseudo-gap opens at the transition. That's not what we expect if you only have bound states due to disorder. Anderson localization will not open gaps. So that means that interaction effects have to come in and play some role to overwhelm the transition region. And in fact, the physical mechanism of this has been anticipated by none other by Anderson himself in 1972. And he discussed what happens when you have strong disorder such that you have bound states, but then you turn on the deformable lattice of the interaction with some bosonic mode. And he said, well, the occupied states will simply be shifted down due to some kind of polaronic effect. If you have a bound state, the system surrounding the bound state will sag, just like you're sitting on an old mattress. to lower the energy of occupied states, but the empty states will not be affected. And generally, this will open a gap at the Fermi surface. People who work in strongly solar systems, people who know about magnetic polarons, for example, are well familiar with this phenomenon of gap opening. And it has been discussed in a different context also by Gorkov in more recent years, but it's a very general physical picture. I just wanted to mention that the theory that I have just shown you, applied to this particular band structure, has been previously shown to, in fact, also capture this effect. And I don't have time to go into details, but I just want to tell you that if we solve that theory for partially filled band with strong disorder, we again find that this polaronic mechanism will split the bands, will open a gap, and the critical behavior and the scaling function, the critical exponents are identical to what we have. So my message here is that this Murray material at this integer filling can be considered as a prototype for a disorder-driven transition, but the universality class that we discover is in fact probably much broader and the conclusions will apply to a broad class of disorder-driven transitions in a rather universal fashion. So this is my last slide with conclusions. I've shown you that several examples how this wonderful Moya material can be used to study completely different regimes and universality classes, mechanisms for the metal insular transition. My favorite DMFT description seems to, our Landau theory description, seems to work remarkably well in all these regimes, but there are many questions left. For example, we need to explore further the role of glassy physics that Dragan Mihailovic also pioneered in these dicalcogenous materials. So this is something that seems to be very prominent in many cases. So you can have amorphous electronic solids even without disorder. So this is something that people didn't believe it, but apparently now there is good evidence that this really happens and that this may be really important in these modern materials. Also how these bosonic modes or general polaronic effects are affected by disorder. How universal is this behavior? Not only phonons due to the lattice distortions, but maybe plasmons, electronic polarons of the Jodorowsky type, magnetic polarons, and many other examples. We are suggesting that our physical picture will capture all of them in a universal fashion, but that remains to be demonstrated. So I'll stop here and thank you very much.
Thank you for that, for a very stimulating talk. These questions.
I think that you can answer this question in the following way. DMFT is just, you know, when van der Waals wrote his van der Waals equation, he had some random reasons, right? Later, Landau explained why, you know, no matter how you formulate the mean field theory, you always find the same critical behavior. And we know now that in high dimensions, above a certain critical dimension, this becomes exact. In lower dimension, it's not exact everywhere. There exists a Ginzburg region, which can be very narrow in some cases. But outside that region, there's a broad region where mean field theory and Landau theory in general applies and describes 90% of the experiments. I believe that this is the case here as well, because, you know, one thing that caught my eye about 30 years ago is that if you look at some of these signatures in the known examples of metal insular transitions, especially with disorder, you see that, for example, this behavior that conductivity behaves linearly with the distance. That is seen over an enormously broad range of parameters. That smells like mean field physics, like Landau physics. So we today, because of the theory of Wilson and so forth, we understand why is it that Landau theory works over a broad region. There exists always a narrow region. It may be difficult, challenging to see experimentally, but I forgot to say one thing about our theory. It can be derived as a settle point of a field theory. And so we are planning to do systematic corrections, a loop expansion, and an RG description to describe also the narrow region. That remains a challenge for the future, theoretically and experimentally.
Okay, there don't seem to be any pressing questions. That was a good answer. So I suggest we thank the speaker again and welcome Bert.
First of all, so first of all, I would like to thank the organizers for giving me the possibility to be here, for inviting me. It's also my first conference. after Corona. Antonio already mentioned that I had also the pleasure to be part in the first Superstripes conference back in the 90s, taking place in the center of Rome in a fantastic place. I will never forget this conference. It was great time at that time. And I spoke during this conference on a peculiar cuprate. It was this neodymium doped lanthanum strontium copper oxide, very strange thing, tiny change of structure, could switch between magnetism and superconductivity. And of course, we know that it's connected to stripe instability. It's still an open issue. We are currently doing ongoing research also on these cuprates. But today I will talk on a different class of materials. I will talk on pnictides. So different compounds, iron-based superconductors, different names, orbitals, and nematicity. But in essence, it's somehow a similar thing. There's a very strong coupling between lattice degrees of freedom and electronic degrees of freedom, which influence both magnetism and superconductivity. In that sense, it's related. So this brings me to the outline of my talk. So there are three parts. I will first discuss this 1111 type, so lanthanum oxide, oxopnictide superconductors. I will discuss pneumatic fluctuations, which are at the end of the day structural fluctuations, lattice fluctuations, the dope systems. I will show you some data on strain-dependent measurements of more complex transport properties, first attempts in this direction. And if time allows, I will share with you some very recent results on another class of iron-based superconductors, lithium iron arsenide, where we have clear evidence from photoemission that we have pneumatic superconductivity, but there are a lot of puzzles, a lot of question marks which we can understand. So these are the people involved. So we have a broad spectrum of experimental techniques which we use to study this material, starting from photosynthesis, and I think in particular for this this 1111 type compounds, Rea Kappenberger, this lady here, was very important because there was a real breakthrough in getting crystals in this direction. And then I will show a lot of transport data, which were basically measured by Federico Carrieras and Georgian Chong. And of course, the ARPUS studies are coordinated with Sergei Boridenkovich. Many of you know one of my group leaders. So iron-based superconductors, are these bad or good metals? And even this simple question can be answered in an easy way. I show you two examples here, which I will address later on. This is lithium iron arsenide. It's a beautiful metal. It's a small residual resistance, a large RRR resistance ratio, sharp superconducting transition. So one would really argue that this is a very nice metal. On the other hand, if you go to the first iron-based superconductor, this lanthanum oxygen iron arsenide, these are the data shown in the first publication. The parent compound, so chemically from the doping, exactly the same, even the structure is very similar to this guy here. It shows a behavior that looks like an insulating thing. There's an anomaly here, and then even at low temperatures, it's somewhat localized. I think there is no real theory explaining this difference between these two similar materials, similar structure, similar doping, but it also tells you that this material is somehow strange. And this is now a picture, as far as I know, the smallest resistivity ever measured in a crystal of this compound, a tiny nanostructure even. And still here you see this tendency to localization. And then you see these sharp anomalies, which are phase transitions. This is a structural phase transition, a pneumatic phase transition. The orbital occupancy of XZ and YZ orbitals becomes different, followed by a magnetic one at lower temperatures. There's a strong decrease of resistivity. Here, what is known, there is a partial opening of a gap. So you lose charge carriers. Nevertheless, the resistivity drops down, telling you that the mean free path becomes much, much larger here. Or in other words, this tendency of localization here is a strong scattering. It's intrinsic, not extrinsic. So you have a bad metal, or nearly a localized system due to strong interaction with other degrees of freedom, which changes the phase transition. I will argue that this is basically change coupling between electrons and the lattice. And you have to do a lot of doping to get rid of this. And this is, again, very old data on these compounds. You see, and this looks, in some sense, looks like cuprates. You start here from this material where you have this strong interaction. You go to an underdoped phase, there's still some tendency of localization. And only if you go to overdoped compounds, you have something like a T-square behavior, which looks like it. And I should emphasize, these materials apparently have a strong interaction with other degrees of freedom, but it's also a very interesting material. At the end of the day, it's a material showing the highest TC in these iron-based superconductors. And again, but if you replace lanthanum by some iron, you add some chemical pressure, you end up with a TC of 60, which is a factor of 2 larger than that what you get in this very beautiful, whatever barium 152. So that's a motivation to have a closer look on these materials, trying to understand in particular the strong interaction between electron degrees of freedom and other degrees. So this is a revised phase diagram which we worked on last years. You see the main characteristics are the following. Maybe this works better. That you have a magnetic transition here, which is strongly suppressed. There is no coexistence of magnetism and superconductivity here. And then you have this nematic, this orbital order or nematic phase transition, which decreases upon doping and then disappears. The signatures of the long range order disappear. This is again data obtained on polycrystalline samples. Since so far as I know, there is no way to have a controlled doping via fluorine in single crystal. What we get now, what we can do is now parent compound crystals, and that was a breakthrough. It's a different way of crystal growth. It's a solid state crystal growth, leads to this very nice faceted single crystals of lanthanum oxygen iron arsenide. And in the second step, what you can do then is you can co-dope cobalt. So you use cobalt now to dope charge carriers into these iron arsenide layers. This is possible, but it's also not great because we know that these cobalt doping induces electron, but it also induces impurities, and it also induces scattering, and we expect lousy superconducting properties, which is also known since we have this material strongly interacts with other degrees of freedom. This also plays a role. And that's also shown in the data. So the superconducting range, so somehow this figure is damaged. Okay, superconducting range is much smaller than it is in for fluorine doping. So in plane doping, TC is smaller. It's well below 10,000, but still the main features are the same. So we have suppression of magnetism. We have no coexistence of magnetism and superconductivity, and we have the structure phase transition, which is okay. I should emphasize that we are still working in this direction. We're still improving the superconductive properties. The next step was then to go to samarium dope single crystals. Again, now there's the first series of crystals where we dope with cobalt. And here now superconductivity becomes a little bit stronger. Studies of these crystals are just started. We also try to get this fluorine doping under control. So there we are still in the process of getting more and better single crystals of this material. Now, let's have a look on the materials themselves. So now for the first time we have the single crystals, we can have a closer look on their properties. And the first thing which we measured is transport, or better, transport under strain. How does the electrical resistivity change when we apply a tiny strain? This is a technique which has been pioneered by Aaron Fisher and co-workers. So you glue your single crystals on a piezo crystal, and using this piezo crystal you can apply tiny strains. You can do that in different directions to check the symmetries of this. And from this, you can measure the nematic susceptibility, or you can measure the change of the resistivity on uniaxial strain. And in the parent compound, you see this strong increase. That's not a big surprise. You have the structural phase transition. Before that, we have this increase of this nematic susceptibility. It follows a co-revise behavior, more or less co-revise behavior, with a divergence close to this 40%. And these measurements you can now do on all these crystals, and we did that for all these crystals, and for all these systems, also for systems far away from the structural phase transitions, we still see this strong change of the resistivity on applying this tiny strain. The first compounds, you still see this phase transition, which then disappears, but you still see this co-revise behavior, but there is a substantial change now. If you analyze, take these curves, take the fitting, you see that the characteristic temperatures, which you see here, which you can see here from these lines, become smaller, systematically smaller. And actually it crosses 0, close to 6%, it's called optimal. That's the situation where superconductivity is best. And if you go to overdoped compounds, then this becomes negative. Or in other words, we have such a behavior, so we plot these Curie-Weiss temperatures, measuring somehow the strength of the thematic interaction, thematic susceptibility as a function of doping. We have more or less a straight line, crossing 0, close to 6%, and that's exactly the situation. That's exactly, again, damage curve here, exactly the doping where we see the best superconducting properties. We can also do something else. We do not need to analyze the data. What we can also plot is just the amount of the nematic fluctuations. If you just look at the numbers here, you see we have a nematic susceptibility or strain dependence of resistivity, which is pretty large here. In the optimally doped compound, it becomes much smaller if you go to overdoped compound. If you just take these numbers, take the raw data, plot them as a function of doping and temperature in such a color plot, you immediately see two critical regions. And both of these regions telling us we have very strong interaction between lattice and electrochromic degrees of frequency. We have slow lattice fluctuations which strongly affect electronic properties. And both are very clear to interpret. The first one is the region where magnetism is. So here you see the coupling in some sense between this lattice and slow spin fluctuations, which you expect since the spin order is a stripe-like spin order. The second one is more surprising. So just from this normal state quantity led to coupling between electric resistivity and strain, we can mimic directly the superconducting doping. And this gives you, okay, apparently a problem with the figure, gives you a direct say that we have really this most robust superconductivity in this class of compounds is really occurring just at the instability of this nematic or quantum critical point, if you want, of this nematic instability. And this is now different from the other systems. So if you go to barium 1 to 2, these two regions are merged together. Here we can clearly separate between this. And of course, we can continue now. I can now argue that here we have this strong coupling. We have evidence for polaron behavior, which we have from NMR data. We have also very strange magnetic behavior. Here, there's also expected to have slow lattice fluctuations, which also couple to magnetism, leading to, in the second order, to very strange magnetic behavior, which we discussed very often 5 or 6 years ago. But the main message for you is now here, at least in this class of materials, it's possible to separate these two instabilities. And we clearly see that there's a very strong relationship between strain and superconductivity in these compounds, or lattice degrees of freedom and superconductivity in this compound. And of course, we can continue now, having this crystal, we can continue to do more than just looking at the phase diagram. Can we learn, can we understand also this coupling? And the first attempts which we are doing in this direction was measurements of more complex transport properties. So again, we use our piezo stack, we use our sample here. Now we apply a heater, which allows us to get a temperature gradient over the sample. Thermocouple measures the temperature gradient, and then we can measure the Seeberg effect, and we can measure the Nernst effect if we apply, in addition, an external field as a function of strain. So we can really go to more complex transport properties, giving us information on details of the Fermi surface and their change as a function of strain. Again, the maximal strain which we have is tiny, 0.1%. And the first, really the important take-home message is these effects can be measured. So though the strain is very small, we can see clearly changes of these complex transport properties. And again, telling us that the whole electronic structure which we have here sensitively depends on lattice degrees. Maybe just a remark. We started to do these experiments also now on 2D materials, tungsten diaterite. Again, we find that. So that's really something like a technique to learn more on this compound. Having now a look on the data. So what we do here, so we switch on the heater. This is the thermal power. We switch on the piezo. This is the strain effect. Switch off the piezo, strain effect disappears. Switch on the heater, then again the thermal power. And then you see if you go to different temperatures, the thermal power changes sign. The strain effect does not. So I have a closer look on this in a minute, and the same you can do here for the Nernst, for the more complex Nernst effect, which I will not discuss in more detail later. So the main message again, very strong change of very strong influence of lattice degrees of freedom on electronic behavior. So Seebeck effect, typically, if you wanted to model this, Seebeck effect is typically connected to, using the mod formula, is connected to the logarithm of the conductivity, the derivative with respect to energy. At the end of the day, it measures energy derivatives of density and mobility, tiny changes of Fermi surface. In undot compounds, you expect more or less the same amount of holes and electrons. Therefore, Seebeck effect is close to 0. If you dope, it becomes 0.35. So for the parent compound here, even the sign change, which you saw in the raw data a second ago. And then if you then again look at this change as a function of the strain, you see this divergence, which is not a big surprise. That's what you also saw in the resistivity. What you already see that the sign of the charge carrier does not matter. In both cases, you see it's positive. Either thermal power is negative or positive. In both cases, this strain derivative is positive. Already giving you some hint that this coupling to the lattice might prevent selectivity of cinematic fluctuations. We have Curie-Weiss behavior here, which we see which is smaller in the dope compound, so the absolute value is smaller in dope compound than in the parent compound. So there is it's a different concentration dependence than the resistivity. So we measure something different, and this is also telling us that it's worth having a closer look. It's also remarkable that when you do the same experiment on a 1 to 2 compounds or another iron-based superconductor, shows very similar behavior here. So that trend seems to be generic. So can we do more? Can we go beyond just looking at the Curie-Weiss behavior? Can we do more? Learn on this. We did that by just analyzing this Seebeck effect using this formula. We have a Peltier tensor and a resistivity tensor, and then taking this, we can also write the Seebeck susceptibility as a sum of the strain derivative of the Peltier tensor and the strain derivative of the resistivity. So this is measured from the resistivity. This is then obtained from the Seebeck effect, and both are of similar size. So resistivity, also scattering plays a role. Here it's also the Fermi surface. Also this formula didn't make it on this computer. So we can also take these results and take from the experimental data, we then can model the Nernst effect. And this is the result that you can really model the Nernst data from measurements of Seebeck effect and resistivity. Telling us, it's just the first steps. For details, you can also look at these recent publications. First steps that you can really learn more how really lattice and the electronic structure really interact by doing such kind of experiments. And doing that on more samples, doing that on different systems. And that's work in progress. So still I have some time, as far as I know. Then I will move on to the last. This is switch gears, completely different topic. Lithium ion arsenide, I told you, it's tetragonal, no structure phase transition, no evidence it's a good metal. It's a super material for photoemission because you can measure superconducting gap with ultra high precision, very nice surfaces. And this we did for more than 10 years meanwhile. But the real surprise is if you look at the symmetry of the gap function, it shows a clear C2 symmetry. The lattice is C4 symmetry, the gap is a C2 symmetry. And this, okay, I can now show you a lot of data. It's not only the gap function, it's also the Fermi surface size signals a C2 symmetry. And we did that as a function of temperature. This is for different pockets. It's seen in the hole pockets. It's seen in the electron pockets. Always a C2 symmetry in the electronic structure in the superconducting state. Did that also as a function of temperature, and then you see at high temperatures you basically see a C4 symmetry, or see no deviation from the C4 symmetry, whereas at low temperatures in the superconducting state is. And we repeated it with different machines, and we'll skip this, which even allowed to measure that with the laser outputs, different sample, different setup, different place in the brilliance zone, and again, at low temperatures, you see this clear difference between these two directions. Again, this change from a C4 symmetry to a C2 symmetry. So the schematic symmetry of this experimental observations for these compounds, that in the normal state we have C4 symmetry. 3D matters, so KZ changes a lot of the details, but everything is consistent with the C4 symmetry, which you see from the average structure. If you go down to low temperatures, you see this clear change towards the C2 symmetry. And this is a big surprise. And what we did now is to look whether we can see this also in the other quantities, in pneumatic, something like a pneumatic instability in other systems. And the answer is no. So we did a lot of experiments now. We did these resistivity measurements as a function of strain. At the end of the day, the pneumatic susceptibility is very small. So that's just for different compounds. We put in doping, we try to change things, and there's basically nothing. So this is another 111 compound where we have this typical pneumatic susceptibility, and these are all these lithium-based compounds. We did also measurements of NMR under strain, so we put a lot of strain in there. And again, if you do that for other iron-based superconductors, you see a strong change of the electrical field gradient coming due to this orbital redistribution or the different orbital occultation. If you do that for lithium iron arsenide, it's nothing. And the third thing which we measured the lattice constant, or lasting high precision measurement of the lattice constant. To see somewhere here, we do not see any clear anomaly going on here. So somehow, and just for comparison, if you do the same experiment for a barium 1 to 2 compound, even far away from any phase transitions, you see this very nice phase transition here. And here there is nothing going on. No evidence for pneumatic order from all these properties. And this is, of course, a big question mark now. We have this clear C2 symmetry seen in photo emission. We do not understand what's going on with twinning. That was also what the referees told us. And we lack any clear evidence here from these typical anomalies which you expect from a lattice degree. So this brings me here to the summary. The take-home message for the first part is there is a very strong coupling between the lattice and the strain. And we see that the superconducting dome coincides with the quantum critical point of the pneumatic fluctuations. We have a clear separation between magnetism and pneumatic fluctuations here. We have a lot of possibilities now to study these in more detail. And then there is this question mark with lithium iron arsenide. So thank you very much for your attention.
Thank you very much for a wonderful experimental talk. I'd like to invite questions, please.
A very simple comment, because for us, the system that you studied, the diagonal case, was the most important one to study from the theoretical point of view, as a case of tetragonal symmetry. And all the beautiful results that you have done are really important, because it's really a very, very simple system. And your results agree completely with our way of thinking, that you have two gaps. With the strain, you change the percentage of the two, and you have a Seebeck effect. So all you described can be simply described in the two-gap scenario in a very simple way. What is interesting to understand that is related with other tetragonal system is the fact that when you have some precipitations, you can have a nanometer domain in one direction, and it's enough to break the spectral symmetry of everything because you have a strain in very weak strain, non-symmetric one. So it's in ruthenium superconductors also has been observed by Maeno, and we have seen in tetragonal mercury compound. So it's the same. You have some wires of oxygens that breaks the symmetry of the crystal, the nanoscale.
Thank you. So, thank you. It is like Jorgen.
I have two questions. One is from, maybe before. So where you see that before becoming superconducting, you have at some, sample compositions, just drop of the resistivity around the same temperature, but doesn't quite go to zero. So what do you think is the thing causing the resistivity reduction? Yes, so for example, for that compound 0.06 and.
Oh, here it goes to zero. That's just shifted. That's just shifted. Just for clarity, shifted. So it goes to zero. So that's the superconducting state there. It's usual.
Now, the other question is, do you have any guess of what is causing that twofold, Fermi surface that you showed at the last part, but nothing else is showing that kind of behavior?
Okay, if you ask theoreticians, so Shubikov is also co-author on one of these papers. They say we have complex intermixing of different kind of superconducting order parameters, which can lead to this thing. I'm not so sure. So still, I would like to have more ideas to understand maybe this way of thinking that this inhomogeneous superconducting state. Of course, we have no evidence for that. Lithium ion arsenide is studied a lot from this STM. It all looks very homogeneous surfaces. There is some evidence for nematicity from STM in some cases from vortices. So it's not clear what's going on, but it's not the usual nematicity which we have in the ion-based superconductors. I think this is maybe the main message. There is some kind, again, pointing towards stripes or nematicity, but it's not explainable with respect in terms of this usual way how we
Okay, short question.
This upturn about temperature, what does it mean and how does it depend on doping?
This upturn here comes
at low temperature, at the lowest temperature.
This is okay. This is something I really don't know. I think so. How does it depend on doping? It disappears on doping. It's certainly connected with this organ in some sense, but it's also deeply, but it's intrinsic. You always see that in all the I think it could be very well related to things you are discussing. We have a strongly interacting electrons with lattice degrees of freedom plus this organ. And then, of course, if you go a little bit to dope systems, then it disappears.
Does this slope come down? Slope? What slope?
I have to admit, I cannot tell you this with the precision necessary to answer your question, because we cannot control the charge carrier concentration too much.
We're running a bit over time, so if you have a quick question.
So the answer to the first part of questions, at the moment, so I showed you already our attempts to look for similar things in other quantities, and so far we have no clear indication. In the magnetic field, there is some funny behavior in the thermal expansion, which could point to one-dimensionality, but I have to say we have no clear confirmation from another probe. But doing some measurements as a function of field orientation of specific heat or something like that is, of course, something which we would like to do in order to see at least the gap function as a function. I think it's a good time
to wrap up. Thank you very much, Bert, for an interesting talk. And the next speaker is...
Thank you very much. My name is Claudio Mazzoli. I work at BNL, NSLS2, the National Synchrotron Light Source on the East Coast. and I'm here to talk about some density wave in 214 nickelates from the perspective of resonant X-ray diffraction. The outline of the seminar is here. So we talk about density wave in strongly correlated materials and the case of some cuprates and nickelates in particular. A quick view through the coherent soft resonant elastic X-ray scattering, which provides reciprocal, and we added recently real space microscopic information, as I will present. The case of cuprates as a quick recall. I thank you very much, the organizer, for this new opportunity of presenting further results. I already presented cuprates a little while ago, and now we add nickelates, and we're highlighting similarities and differences indeed. First of all, acknowledgements, apart to the conference, also to people at BNL, at the synchrotron, at CFN, Center for Functional Nanomaterial, and as integral part of this work, Condensed Matter Physics and Material Science Department, in particular, Ian, Mark, and John Tranquada. And obviously our precious collaborators as Physics Department of Oxford University. So, we heard about high temperature superconductivity a lot. We are interested in this part. Apologies for not showing the most updated, let's say, critical temperature versus CR diagram, but we saw it enough during the last days. And what is quite surprising is the commonality induced by the copper oxide planes through structures that are actually very, very different around, along all the families here. And in spite of this, we have similarities in the phase diagrams, although we saw several versions of them over the last days, in particular today. And we will talk about the 214, which at a magical composition of 1.8 present this strong depression in the superconducting temperature dome, and it's known that it's due to charge-density wave. The point is always the same, which mechanism is under the high-temperature superconductivity, and we would love to have a look from a different perspective, as I said, from the coherent soft X-ray resonant elastic scattering to try to provide some further details. In reality, it's we know now that charge-density wave is really something really important. It seems to be ubiquitous across the whole of the families that were investigated, and it started everything with X-rays and neutrons, and then we gave some resonant, let's say, kick, discovering the existence of charge-density wave in the 1 to 3 compound as well. And then many other people contributed, and actually today it's very clear that they are more or less everywhere. What are the roles, their roles, if they are static, dynamic, what is the role of the domains across the different structures, and the percentage of the charge density wave correlated or not correlated, dynamic or static, is indeed an open question. And this is more or less what we want to go through. So to do this, we need a specific point of view, and we identified a good candidate in emergent spectroscopy and scattering through resonant elastic X-ray scattering, that in our case is used through diffraction. So nothing else this is nothing else than a standard diffraction where the atomic scattering factors are modified by the fact that you work in resonance. And as the quantum mechanics allows us to calculate through the Kramer-Heisenberg dispersion formula, which is indicated here short of a delta to preserve the energy, obviously, it's something that by knowing exactly which operators you're talking about and which state in particular the excited one, you can calculate what you expect out of the atomic scattering factor. This is a major challenge in reality, but it's not necessary to do it completely. A lot of information can come out just analyzing the symmetries, the dependence on the polarization incoming and outgoing, and depending on your setup, some subset of them. In reality, we have to remember that everything comes out in terms of photons, so the elastic is one of the components. The inelastic is typically prevalent, except if you use Bragg to enhance a lot the elastic component, which is exactly what we do. The symmetry of the process and the components that are in are not known in principle, and it's one of the challenges to try to understand. In the case of soft, it's particularly easy normally, and we are dealing only with operators that are dipolar, but in general, you have to ask yourself what you're dealing with. So up to here is for standard, let's say, diffraction, again, standard sources, let me say, although in resonance. What if we add further investigation by using beams that are coherent? Essentially, apart for, instead of, if you want, the normal diffraction, which is here sketched in a very well-known paper out of standard powder diffraction, where at the price of controlling the average parameter of the radiation, you are making impinging on your sample. In this case, is the wavelength. You can extract through a geometrical parameter, in this case, an angle, the microscopic parameter in your sample, the average distance of the scattering planes in your powder sample. If you do better and you control better the wavefront that is impinging on your sample, in particular limiting the illumination function, and being sure that locally your K vector is always the same, you will see something that goes essentially in focus in your initially diffuse ring, and this is the formation of speckles or speckles pattern, as we said, and it contains the Fourier, in principle, it contains the Fourier transform of the arrangement in space of your targets, in this case, the collection of the single grains of the powder. So it's possible to have those kind of sources, yes. In principle, any kind of source can be made coherent by spatial filtering and energy filtering, as the coherence has two obvious components. One is longitudinal to the propagation of the light, and the other is transversal. The problem is how many photons you're left here for your experiment. And with the modern synchrotron sources, we have enough to perform beautiful experiments, as I will try to show. So this is just to remember and to remind you about the expressions of the coherence in beam, where apart from geometrical parameters, the solid angle under which you look at the source being the sample, or the monochromator resolving power or equivalent, everything scales linearly in lambda. So the softer the radiation, the easier to get a coherent source. And that's the reason why it's particularly, one of the reasons why it's particularly productive to make it in soft X-ray regime. We all have experienced more or less of this fact of the speckles. Indeed, if you take a laser pointer, this one is green. If you take the red one, obviously, exactly because of the lambda relations, it's easier to see. You typically make it reflecting out of something that is not perfectly flat, and you will see this kind of interference fringes, which is called speckle pattern, as I said. Same, different regime, optical versus X-rays, but same principle. We want to exploit this phenomenon to understand better what we are dealing with in our samples. That's the message. Okay, so as I said, I already reported in the recent past about cuprates, in particular family 214 LBCO magic composition of 1.8. We know what to look for charge density wave through all their experiments, neutron and standard X-rays, let's say hard X-rays, no resonance. And our beamline is sketched here in a cartoon, is extremely simple: ondulator, couple of mirrors, monochromator, extraction of the coherent fraction, and limitation of the illumination function on the sample by a 10 micron pinhole just in front of it, opening up the detector at 2-dimensional CCD, fast CCD, in collaboration with Berkeley. And if you go on one of the, let's say, positioning reciprocal lattice that are supposed to contain the Fourier components from charge density wave, here you are. It appears a nice peak, which shows speckles. If you make an horizontal cut, you see an envelope and the fluctuation of the intensity across it because of the speckles. The average, the smoothed peak, that is the average, let's say, of images that we have here, follows perfectly in temperature the order parameter and the full width maximum as shown by other measurements. So we are sure that we are exactly where we should be, no problem. The point is that we want to understand better, as we said, on the microscopic information that is brought in by these speckles. So these are two movies side by side. One of the two is sample fixed in position under fixed temperature. And you see that there is no dynamics, where you see speckles are still there. Probably if you are far enough, I have to tell you that this is a movie, otherwise you would not notice, apart for the tiny jitter in the noise of the detector. And instead here, we made an artificial translation of the sample by a total of 10 micron, as much as the pinhole is. And you see that step by step, the redistribution in intensity is continuous, meaning that any kind of motion, right, either induced, as this is the case, or in the rearrangement of the domains on the level of tens of nanometers, is essentially capturable by our technique. So we want to work in this condition and try to understand if we can induce dynamics in these guys or not. It means intercepting an intrinsic dynamic on the sample, for example, versus temperature. Obviously, any cryostat changing the temperature would move along would expand in space. So we want to prevent it. And so to make a charge density wave versus temperature investigation, you need to apply a kind of mask to your sample. In this case, you see that there is an array of pinholes, and you made multiple because not all of them come as they should. So at the price of a painful realignment per temperature, you are sure that you illuminate the same position of your sample in the same conditions. And these are the results versus temperature. As your eyes cross-correlate the images perfectly, and you see that where you started with intensity or no intensity, as long as the signal to noise on the detector allows, with a fading order parameter versus temperature, obviously, you still see that you have intensity surviving exactly where it was, and you don't have where there was not. So essentially, long story short, there is no change versus temperature of the speckles. Right. So this is interesting for two reasons. First is because we need to understand how this is possible then. And the second is because before or later, these guys should change. At the limit, if you make the transition of the charge density wave to happen, what happens if we come back, right? So we melt the order, we come back, and what do we have? So normally one would expect that when you melt an order, you come back and nobody tells them how to retain a memory. And instead, if you perform a return point memory experiment, this shows that it's not the case. So all the measurements that we present here are performed at 25 Kelvin, which gives us a very nice and strong signal. And we have a before and an after with a temperature here. That means we take an image, we cycle the temperature of the sample up to the temperature that is indicated here. We take another image. Your eyes cross-correlate once again, but we did it for you in mathematically, obviously, and you see that even at very high temperature, you still have a nice correlation in the position of the speckles. But if you insist, finally, you see a change. So this is quite abrupt, and it's happening at very high temperature, right? So this is 200 Kelvin, which is here, 240, which is here, and 260 is down there. The cross-correlation, the mathematical cross-correlation of the images show you that you have to make always measuring at 25 Kelvin, as I said, but you have to warm up the sample quite a bit before actually being able to change the landscape that forces the charge density wave to reappear the same. Notice that to have the same speckle pattern, you require the same position, the same intensity, the same phase. Otherwise, they would not appear the same. So it is really something that is engraved into the sample quite deeply, right? We believe that correlating with the structural transition that are known in the 214 family LBCO in particular, this happens at the transition between the high temperature tetragonal phase, which is depicted here, and the low temperature orthorhombic phase, which is characterized by this oxygen redistribution, in particular tilting of the octahedra around the copper in the plane. So this is sketched in the screen here, where we went so close to the transition, but not across. You have the same speckles. You go very close, you start to see that something is changing. You go across, you change definitely. You don't go across anymore. You keep the same but new speckle pattern. So this was quite conclusive in our opinion to say that the lattice has to have a very strong role in pinning, and it's happening at very high temperature actually. So something is left written in the lattice, although the charge density wave appear only here at 50 Kelvin, right? So all this space, it's not sufficient to erase, let's say, the information that appears at this transition somehow. Okay, so what is the take-home message on the charge density wave in 214 cuprate LBCO18 in particular? We have only static. Domain must be breathing versus temperature, otherwise we could not reconcile with this thing happening. I will comment more in a second. The domain pattern seems determined by the lattice, and there is this concept of high temperature structural transition that is happening, and it seems to write what's happening actually into the sample. And to have this breathing mechanism, better to reconcile the staticity of the speckles versus the fact that you have a full width and maximum that is changing over a factor of 3 roughly between low temperature and close to the transition temperature of the charge density wave order. There are only two options. Either there is an exclusion principle that allows the charge density wave domain to grow without touching one with the other, so avoiding one with the other. But how to organize it in space in 3 dimensions is not obvious to understand. Or they have to occupy a negligible volume in the sample. And this is sketched in this simulation that shows you that if you take negligible bubble-like small charge density wave domains arranged in a certain pattern, you make the Fourier transform, you expect these speckles at your detector. You can make them growing over factor 3, but as long as they don't touch, you have the same speckle, so the same Fourier transform. As soon as they start to touch, instead, you change completely the Fourier transform of the speckles. So the speckles will change. So this means to us that to account for a factor 3 in growth in full width and maximum across this temperature, you need to have something that is able to breathe, but not to merge with the others. So they have to be separated in space. Or we have to explain how they can avoid one with the other. So just to reply a little bit better to these questions and to profit of a similar but different system as the nickel 214 is, we went to this specific composition as it has a charge density wave and the spin density wave in this case that are both reachable for our experiment. The structure is exactly the same, where nickel substitutes copper. Right. In the meantime, we improved our capabilities of dealing with the samples, and the samples have now a small little platinum mask that is directly deposited at Center for Functional Nanomaterial at BNL on their sample, so that our illumination function can sit essentially across the sample here, and we are sure that we can do things in a very, very clear and nice way. Charge order, spin order give two signals in different reciprocal lattice position because they have slightly different reciprocal lattice vector, and so we can pick them up both. One is much stronger than the other, and nice speckles are present in both of them. The geometry, for geometrical conditions, let's say here we have some roundish speckles, and those are a little bit more elongated in one direction. It's all understood. The crucial point is you make change in the temperature, and you see that as speaking just about the average envelope of this peak, you see that they breathe a lot in correlation length, both in plane, blue symbols, and out of plane, yellow, or orange, or whatever it is. There's a strong difference between the two, right? There is roughly a factor 3 or 3.5, and they go all together, essentially. Right, we can do better. We can use speckles and treat them in a mathematical way with a one-time correlation function, as it was already shown yesterday by Suzhou Roy. And we can determine the dynamic, we can extract the dynamics that is related with these speckles. In this case, we do have a dynamics at variance compared to cuprates, and you see that the charge order is always dynamical, and this is a log scale in seconds. It's always dynamical, and the change is you start from low temperature, you warm up, it stabilizes a little bit, 70 is the maximum, and then you cool down and it becomes more dynamic again. Spin order is the same in principle, but with some relevant differences. It is much faster, so the same scale, it drops much more and much before. Low temperature, you warm up, it stabilizes, it's practically stable at the limit of being stable as the beamline is, so it's difficult, it's probably of the hour, and a good fraction of an hour, let's say. And then you warm up further, and it increases the speed of the change, so it becomes more dynamical, and it's way more dynamical than the charge order is. So charge order are these symbols, and they live here, that are much less correlated than spin order, those symbols that are live here. So charge order is less correlated than spin order in the nickelates, and the spin order has a much larger dynamics in principle than charge order on average, except that it can freeze better, it slows down more around 70 Kelvin, which is exactly the top of the curve here. Right, so it's a little bit complex. Let's try to go gently through it. In particular, let's try to repeat the return point memory, always measuring, in this case, at 70 Kelvin, which is the most static condition that we have for both the orders, right? So there is a completely different behavior compared to before. The spin order is static, and then it drops quickly and it disappears. This let's say, gray area marks the transition of both spin and charge order. The charge order instead, you can bring it everywhere that we were able to measure, and it comes back always principally, not completely, you see, it's not recorrelating to one, but it has strong, let's say, features that are coming back, as if there was something that was still pinning, let's say, the principal part of the speckles to reappear more or less in the same condition with the same intensity. Notice that when we speckle correlation, we are anyway dealing with intensity of the speckle. That means that we are looking for intensity point-to-point correlation, right? Pixel-to-pixel correlation. All right, so let's try to make, to sum up, charge density wave and spin density wave in nickel-8 214, as we saw. The correlation of spin versus charge is 3.5 in both directions, in plane and out of plane. So spin is more correlated by wave, by a relevant factor compared to charge. Both of them are dynamical, but in slightly different ways, as we said. The charge part is always dynamical. Instead, the spin is always dynamical, but essentially, it's almost frozen at 70 Kelvin. Spin density waves show a sharp transition in the return point memory, and once magnetically disordered. Charge density part, absolutely not. So at that point, we said, okay, the situation is slightly complex. Let's try to go directly in real space instead of reciprocal space, and try to see if we can get some information more. Profiting of the fact that at 70 Kelvin, the spin order is pretty stable, we perform at 70 Kelvin ptychography. So we were illuminating our LSNO sample by our illumination function, and then we were moving the illumination function across the sample, being sure that there was a large enough recoverment of one illumination to the other, such that the phase retrieval approach that is intrinsic to ptychography could work. And thanks to the experience of Ian Robinson, we got with this very beautiful and quite unique results. What you see here is the distribution of spin density wave domains in LSNO. It's done without rocking the sample, so it's not a full CDI, but the penetration depth of our beam is small enough compared to the size of the domains that allows us to treat everything in a two-dimensional approximation, so that no information is lost. This is the reconstruction of the beam, which gives us good confidence because it's exactly what it should be, as this is an SEM measurement of the pinhole that I was actually used for the experiment. And you see that we are fast enough to perform this ptychography experiment that we can have information at various moments. And given the stability of the spin order versus time, we can see by eyes immediately in this phase amplitude color bar that we have here, that essentially there is no motion of domains. There is only a small little breathing once again, or principally a breathing of some domain borders around. So the anisotropy in plane, out of plane is confirmed, the limited breathing as well, and the fact that essentially it happens at borders. So everything is consistent with what we got before. And we do a little better now because we have a real space image, as I was saying, and we can actually plot the correlation length out of plane versus the one in plane, and we see that they are perfectly correlated, which means that it's not just that we have two distributions and they have a 3.5 factor one compared to the other, but it's the fact that if you have to make them grow in one direction, they want to grow also in the other, right? Which is not immediately evident or trivial, and it calls for a three-dimensional somehow pattern in determining the shape, the position, and everything else of those domains. So, what can we learn out of the real space at 70 Kelvin? Domains are packed, but they are separated indeed. The changes are dominated by the frontier evolution. So there is no bubbling, there is no gemination, there is no sliding, right? It's only essentially or principally, frontier evolution. Means that the envelope changes slightly, but only outside, there is no slide, right? Correlation length and the ratio is confirmed. We know that we are looking at the good things, there's no problem. Real and reciprocal space see the same thing through our technique, see the same thing. But relative correlation reveals, the relative correlation between in plane and out of plane is revealed, so that a 3D nature has to be taken into account, which is not immediately what you expect, because the structure itself has a very different anisotropy. So plane and out of plane are naturally very different, as we were saying. So what can we conclude if we compare the two cases? Well, coherent soft resonant elastic X-ray this material, both in reciprocal and now spin density wave have longer correlation, but they are weaker in temperature. And note that there is a frustration part that comes from the fact that if you lower the temperature, they tend to disappear. So there is obviously something more complex there. The lattice spinning on charge density wave is obviously confirmed. It is massive in copper, in cuprates, due to the fact that it exists an high temperature tetragonal to low temperature orthorhombic transition, and it is what I shown in terms of this change of the speckles versus temperature in the return point memory measurement. The same applies to the nickelate case, shows some memory, but in a slightly different way. Probably because this transition is there, is not present, although short-range, low-temperature orthorhombic phases have been recognized by other techniques, namely PDF, for example. So, altogether, the centrality of the role of charge density wave seems confirmed. And this gives even further relevance to the variability in cuprates. Now, the question is always the same. Status versus dynamic and the relationship with the high temperature superconductivity, that's a work in progress. Thank you very much for your attention.
Very nice work. Thank you.
I can repeat your question if you want.
Thank you. Wonderful talk. Just to clarify sort of the technical question, to distinguish the charge density wave, spin density wave, you know the triple L3 edge, is it the polarization? Do you use circular polarization?
No, they appear at different position in reciprocal lattice, so it's physically different the angles that you use in your end station to see one or the other. That's the reason that I was saying. One of the two shows roundish speckles and the other is more elongated just because you cut through the reciprocal lattice in a different way.
Is there a point in using different polarization in these experiments?
There would be, if we were able to make polarization analysis. It's not the case at the moment if you want speckles to appear. So the only polarization that you can use destroys essentially the existence of the speckle. If you prefer through a polarization analyzer with the current available means that we have, there is no way to preserve coherence.
I see.
Not that I know of this.
I see. And just a comment for a future perspective, this would be perfect experiment for the newly functional LCLS2. Yeah.
Thank you.
Okay, so Antonio.
What do you think about the space distribution of charge density waves paddles and spin density waves paddle? They coexist in the same place because it's not homogeneous. So they coexist in the same place?
This is a very good question. Let's say that if I have to infer from their similarities of behavior, I would say I would expect them to. But as a matter of fact, we didn't perform the experiment yet. So the next thing that we want to do is probably to repeat this experiment at charge density. Unfortunately, as I was trying to point out, there is a limitation in the fact that the system is intrinsically evolving much faster. And so it's more difficult to obviously have something that is meaningful in the sense that we don't have a static picture of the spin density wave, a static picture of the charge density wave that we can compare because time passes and there are limitations in this way. But we are trying hard to extract something, yes. I can repeat the question if you want to stay.
Puzzling is, if you look at the, reciprocal lattice space, locations of the charge density and spin density, they seem to be coupled. It's not like they have a totally different periodicity and so on, right? So there's some kind of, relationship between the two. But I find it very puzzling that the behavior of the two are quite different, like how the domains, one, right. the time scale and yes. all that stuff being different. I find it puzzling because I would think that they would be coupled, and they seem not to based on your measurements.
Let's say that what we, I mean, this is obviously only a sub-part of all the investigation that we are doing. And what we think is that probably they have a nucleation part somehow that is linked, probably is dominated by charge density wave. So charge density wave can grab the lattice somehow, which this was shown very clearly in the cuprates case, right? Also, the nickelates have probably the same underlying mechanism, although the structural transition is never diverging, right? So it's only local. So this is sufficient, however, for the charge density wave to grab at least principally a little bit. They slide a little bit in the case of nickelates because it's only incipient, this transition, but they can grab there. On top of them, probably the spin density wave are very happily developing, right? However, the fine details on how the panorama around them, so how the potential of the lattice is exerting this kind of pinning, leaves them to develop and to relax or to dynamically behave in a slightly different way. Obviously, there's plenty of details that I cannot, unfortunately, reply to, and it's exactly what we are trying to understand more. Thank you very much.
Yeah, go ahead.
I want to ask a couple of things. First, if it's possible to make ratios of maybe the characteristic length scales of charge and spin modes, and maybe also their characteristic times, so as to see, in principle, it seems that the characteristic lengths are roughly proportional. I mean, they have another factor why this is not the same for times. Right. This may help us to understand what kind of processes dominate relaxation.
Yes.
And the second was exactly about relaxation. So now you may think in usual critical phenomena, divergence of characteristic length and times is ruled by the same parameter, the distance from criticality.
Mm-hmm.
So maybe it would also be enlightening to plot the ratio between the characteristic time and length scale for spin and for charge separately to see if there are similarities or differences.
I see. By eyes, I find it difficult with the behavior that we have here and the similarity that we have here to find something common. But you have a very good point in suggesting this approach. And for the rest, yes, they scale 3.5 one to the other, and they are one on top of the other. So that's the reason why we tend to think that there is lattice produces a kind of potential where charge density wave can grab. They can grab only partially, but they can. On top of this, the spin can evolve, and there's no problem. They're happily filling the space almost practically in a packed way, but they do not feel the same potential. They are only on top of the charge. So this allows them to move. So not to slide, because the charge says, I'm going to sit here and that's it. But the evolution of the domain border is sufficient to provide this kind of relaxation. Why at 70 we don't see it is something we don't understand yet at all.
Thank you very much.
Thank you.
Thank you very much.
Thanks.
Very nice work. Yeah, thank you.
Good afternoon. We start the third session. First speaker is Angelo Di Bernardo.
Yeah.
Please.
Okay, thanks a lot, Chairman. Yeah, and also I would like to thank, of course, the organizer and Antonio Bianconi for inviting me here, like to give me this opportunity to talk about our recent work, basically where we demonstrated evidence for the existence of surface magnetism in the unconventional superconductor strontium ruthenate 214. So this is a very recent piece of work that we carried out in collaboration with other groups, and I will have an opportunity to thank them at the end of my talk. What are basically the motivations, behind this study? A few people already mentioned, like this morning, strontium ruthenate, and yesterday as well. The idea, is that this compound has been interesting since the first time that superconductivity was discovered, demonstrated, in this material by Yoshi Maeno in 1994. And in particular, the interest was kept high for several decades because right after the discovery of this material, several studies showed evidence for the existence of time reversal symmetry breaking in the superconductor. And this was quite exciting. These are both, these are two different sets of experimental data showing evidence for time reversal symmetry breaking with muons. And I will talk about muons in particular in this work. And then also using NMR. So looking at the night shift of the oxygen 17. But these studies basically supported evidence for the possibility that in this compound, the order parameter, the superconducting order parameter is of the type chiral P wave. So meaning that it's an order parameter that breaks time reversal symmetry. And in particular, if you look at the spin symmetry of the Cooper pair of electrons, basically the two electrons are aligned in a spin triplet state, which is the reason why the material became so interesting, because a lot of people thought, okay, then we can use this material as a source of spin triplet supercurrent. This is a current that carries a net spin in the superconducting states, and therefore use it for superconducting spintronics, which is basically the field where I come from. And there's been a lot of interest, but the interest, as I said, like, has been going on, has been kept high for several decades. And more recently, there has been a few studies that have questioned actually these P-wave chiral symmetry of the order parameter. In particular, like there was this study that recently managed to disprove this earlier study that I showed in my first slide, because as you can see here in this study that was done more carefully, like they still used NMR, but you can see that what they proved is that at TC, the NMR shift, so the shift in the NMR signal basically is not non-null as the previous studies showed, but there is a decrease in the NMR signal, as you would expect basically for a conventional spin singlet superconductor, whereas before, like I showed that the signal was going flat through the transition. So these basically disproved these first studies, and it turned out that the first studies were probably done in a condition where the NMR pulse was hitting the sample above TC, so were not really done carefully. And more recently, there is done other studies that were also published where they started to argue that possibly the order parameter is a two-order parameter that is chiral in nature. So this was done by ultrasound velocity measurement. So they observed a sharp change in the shear elastic constants below TC. So this has, of course, made the interest in the compound even more, even higher, because people started to wonder, okay, what have we looked at for the last 30 years? Was it really like a chiral P-wave order parameter or a different type of superconductor? And last but not least, I would like to point out this study that appeared before ours, where basically they looked at, in this case, using muon spectroscopy, which is the technique that I will describe today, and on which my results are based as well. So they used muon spectroscopy on single crystal of strontium ruthenate under strain. And what they managed to observe in this case was a splitting between the onset temperature of, if you want, the superconducting transition. So this is the susceptibility here. So this blue curve refers to the increase in susceptibility, as you can see, and the onset instead of the time reversal symmetry breaking component of the material. So they started basically to distinguish between these two transitions, inside the materials, and possibly this is consistent according to the authors of the paper, with also an order parameter that is chiral in nature, but not of the type P-wave. So this is the background. Now, what we decided to do, in this study that I'm going to present today, was instead to look at the normal state of strontium ruthenate, because there were several suggestions, in particular this study here, that appeared in Science at the end of this century, in 2000, basically suggesting that on the surface of strontium ruthenate, because you have this reconstruction due to a rotation of these ruthenium oxide octahedra, you may have the appearance of a magnetic surface magnetism. So this is conventional ferromagnetic state predicted by ab initio calculations, and they predict in this paper a signal, a moment of the order of 1 Bohr magnetron per ruthenium atom. So a pretty strong ferromagnetic signal. And several groups tried to find evidence for the existence of this magnetism, because it was predicted, as I said, almost 20 years ago, based both on scanning squid measurements and also with ARPES, but evidence for the existence of this magnetism was a bit inconclusive. What we decided to do was basically to do this study using low energy muon spectroscopy, because the sensitivity of this technique is much higher than the one of the techniques that I showed before with respect to magnetic dipolar fields. It's also a technique that allows you to differentiate what happens close to the surface compared to the bulk of the crystal. So this is low energy muon spectroscopy, so you can really tune the implantation energy of the muons within a few nanometers, from the surface of the material. And why we decided to do this? Because of course, you understand that the normal state is the background in which these pairing correlations, so these Cooper pairs of electrons form. So it's really key to understand the normal state in order to understand better superconductivity. So this was our motivation. And we published this work, and basically this is, if you want more details, I put a reference here because I will not be able to cover everything, but I will try my best to do it. So this is the article that you can read, or we can just talk later. Briefly on the technique, I know there are some people doing routinely muon measurements here, probably not everyone, but very, very briefly on the technique, this is a technique that we use at PSI, at Paul Shanner Institute. We start from a high energy proton beam like that bombards a graphite target. This triggers a series of decay reactions. So there are some pions that get generated. These decay very rapidly into spin polarized muons. And these are the particles with a lifetime of 2.2 microseconds that get implanted into the sample. Now, after interacting with the sample, the muons basically emit a positron, and this is like a key thing, as I will show later, like to understand what's going on inside the sample. But what is more important for these experiments, because there is a lot of mu-SR studies that were done on single crystal, is that we used low energy muons. This is a unique facility that exists at PSI, where they start from a high energy muon beam with an energy of 4 megaelectron-volt. They stop completely the beam, like, by using what is called a moderator. This is nothing else than frozen van der Waals gas, a mixture of nitrogen and argon frozen on top of a silver foil. So you stop basically the muons through this moderator and then accelerate them again through a system of lenses, electromagnetic lenses, as you can see here from the sketch. And then by tuning the high voltage on the sample plate, you can basically tune the implantation energy of the muon by tuning the energy in this range that is basically between like a few kiloelectron volts or a small fraction of a kiloelectron volt up to 30 kiloelectron volt. Depending on the density of the material, this normally means like, between a few nanometers up to tens of nanometers from the surface. So almost like hundreds of nanometers from the surface. So it's a slightly different technique compared to bulk, where you have no specific differentiation between surface and the bulk contributions, contributions coming from the surface of the material and the bulk of the material. And as I said, what is key in this experiment is the emission of the positron, because the muons, as this diagram here is showing, comes at a very well-defined spin polarization angle. Then it precesses about a local field inside the sample. So you can see there is a change in polarization depending on the field that the muons experience inside the samples. And when the muon stops, it emits a positron along the direction where the spin stopped at the end of this precession. So since at t equals 0, so at the initial time, the polarization of the muons is known, by working out this change in angle, you can work out, because you know from which direction the positron came, so you know where the muon spin stopped, you can work out what is the change in field that the muon experience in the sample. So the change in precession frequency corresponds for the gyromagnetic ratio of the muons to a change in field. So experimentally, what you collect is what is called the asymmetry signal. So there is normally not a set of detectors as this picture here is showing, but two sets of detectors, and you basically work out what is the difference, if you want, between the counting rates of the two sets of detectors. These are these blue points here. So this is the asymmetry signal that, as you can see, consists of an oscillatory component plus a decay component. Now, this is like the time evolution of the signal. If you take the Fourier transform form of the signal, what you see is that you get like a distribution, that it's peaked basically at the average field that the muons experienced at that depth inside your sample, and as a width. And this width is basically corresponds to the inhomogeneity, is proportional to the inhomogeneity of this field distribution. So the larger is this lambda or sigma, depending on the type of model that you are using to fit this damping, the larger is the more inhomogeneous is the magnetic field that the muons are experiencing in the sample. So that's basically how the technique works. And we use it already, this was the work that I did in Cambridge during my PhD, for a variety of systems. I will not go into the details here, but the point is that, for example, here we use muon spectroscopy to find evidence for what is called an inverse Meissner effect. So that appears when you generate spin triplet correlations, so at a superconductor ferromagnet interface. You can see that in the superconducting state at 5 Kelvin, in the gold layer here, the field, other than being below the applied field, so other than being in a diamagnetic Meissner state, here you have an increase in the field above the external applied field, which is the field in the normal state at 10 Kelvin. Niobium superconducts, as you know, around 9 Kelvin. And more recently, we've done another work where we use the same technique to show that if you have, this is a standard niobium sample. Here is the substrate, so you have this deviation from the standard cosine hyperbolic profile that you expect for the local field as a function of implantation depth of your muons. But if you observe now a monolayer of chiral molecules on the surface, again, like you see some deviation from this standard cosine hyperbolic profile, and there is a change in screening. So there is a screening that becomes more intense, so more diamagnetic if you want close to the surface, and less intense deep inside the material. So these are just studies to show that you can do this, like, you know, in a multi-layer system with a very good resolution. Now, the system that we studied is this one. So this is as you can see here, there's the nickel plates where you mount the samples at PSI, where we made a mosaic of strontium ruthenate single crystals. And we did these studies like with using two different configurations. So this is called transfer field configuration, where the field is applied perpendicular to the precession plane of the muon spin. And then, like, we did also this experiment in the longitudinal setup, where basically the field is applied parallel or anti-parallel to the muon spin. In the same configuration, if there is no field applied, this is called zero field setup. And I will show this data in a second. So they give you different types of information about the magnetism, like implantation energy of the muons. You can basically tune your implantation energy of the beam inside this strontium ruthenate crystal, going from a few nanometers, like at few kiloelectron volts, up to like tens of nanometers at, like, if you want 6, 10 kiloelectron volt. These are all like simulated muon stopping profiles. So the first thing that we observed in this study, these are measurements done in a transverse field configuration, so field applied perpendicular to the precession plane of the muons, is that when you are at 6 or 14 kiloelectron volts, so tens of nanometers, several tens of nanometers or hundreds of nanometers far from the surface, as you can see here, here we plotted delta lambda, that is the difference in lambda, so in the depolarization rate of the muon between the highest temperature and a given temperature. You can see that the higher temperature, basically the delta lambda is just increasing, like as you decrease temperature, so it looks like a paramagnetic background. But when you go like at 3 kiloelectron volts, so close to the surface, now these are the red points, you can see there is a spike up of the curve. So there is a change in slope that happens between like 50 and 75 Kelvin, if you want, so in this temperature range. Now, the fact that lambda is changing means that the muon, the field distributions that the muons are experiencing is changing. And this normally is something that happens when you have magnetism kicking in inside the sample. So if you just look at this set of data, like the red data on its own, like tell you like that there is something magnetically active in the material within the first few nanometers from the surface. So only at the surface, with a temperature onset between 50 and 75 Kelvin. I also want to stress that we measured these on 3 different sets of samples, 2 different cryostats, and so on. So this was like reproducible, this result. Other thing that we did, okay, we also started to study a little bit more the field dependence of these effects. So these are now data taken with the field applied of 1500 Gauss. The previous one were obtained with a field of 100 Gauss. And now you can see that as you go like close to the surface, so these are again like some temperature scans. So you fix the energy and collect points at different temperatures. There is a shift like in the curve that you measure like at low energy compared to the one measured at high energy. And this shift like resembles a little bit the signal that you get if you do like an NMR experiment. And NMR experiments give you information about the susceptibility in the material. So in a way, like, you know, it's suggesting that you have an enhancement in susceptibility, which is again consistent with this idea that there is a stronger magnetic activity like on the surface of the material. The other thing that is plotted here like is the delta lambda corresponding to this field profile, like so for these same data points. And you can see again here that the variation in lambda between the low, so delta lambda again is the difference in lambda between the highest temperature, here is around 200 Kelvin at a given temperature. And here you can see that at 14 kiloelectron volt, everything is flat. Instead at 3 kiloelectron volt, like things start going up around the same temperature that I showed in the previous slide, so between 50 and 75 Kelvin. You can do, of course, also energy scans to better resolve, like, you know, where this magnetism is located inside the sample, because now you fix the temperature, you basically work out what is the variation at the lowest temperature, which is 5 Kelvin, and the highest temperature, which is 300 Kelvin, as a function of energy. So at different implantation depths in the sample. Now, the variation in local field in small fields is basically flat. In higher field, you can see again this increase that triggers like around 4 kiloelectron volts. So only at low energy you observe this increase. Once again, consistent with the fact that you have something magnetic only close to the surface. Here, I mean, it doesn't mean that we don't have an increase. It's just that if you think about it, this is just 0.5 Gauss out of a field of 1500 Gauss. So it's less than 1%. Less than 1% here it's like not resolvable with muons. It's below the sensitivity of the techniques. So it's probably like hidden by the sensitivity of the technique here. And for delta lambda instead, you can see that again, that there is an increase in delta lambda that kicks in around 3 kiloelectron volts. So only at extremely low energies. So the other like thing that therefore that we can infer from this set of experimental data is that you have an increase, like systematic increase in the local field and also in the variation of lambda, so in the shift in the depolarization rate, also at higher applied field. So it's independent on the applied field. Last piece of information like that we get from the experimental data is basically from the zero field or longitudinal field measurement. This is the other setup that I showed in my previous slide, where you have the field either present, and this is longitudinal field, and parallel or anti-parallel to the muon spin, or not present, and this is called zero field. Now, what you can see is that in zero field, the asymmetry has a sort of damping, so it decays as a function of time, but as you apply this field, and this field becomes of the order of 10 Gauss, you manage to completely decouple the damping from the signal, okay? So this basically tells you that the magnetism in nature, so the kind of magnetism, the surface magnetism that I showed you in the previous slides, also has to be static in nature, cannot be due to spin fluctuation, due, for example, to spin lattice relaxation. Because if it was the case, then like the exchange energy, you know that in a field of 10 Gauss, should be like basically much lower than the thermal energy at 5 Kelvin. So it should do nothing like if this was the real nature of the magnetism. So 10 Gauss like completely managed to decouple this damping from the asymmetry, which tells you that the magnetism has to be static in nature. And now if you work out what is like the structure of strontium ruthenate and basically do a simple calculation of the dipolar field that the muons would be experiencing at their average implantation site, you can work out that this 10 Gauss corresponds to a magnetic moment of a very small intensity of the order of less than 0.01 Bohr magnetron per ruthenium atom. And this is like the other outstanding like result of this study, because altogether, like basically the other thing that of course you can also see is that the muon distribution is completely like homogeneous. So there are several features here that I want to stress. First of all, like you get that the magnetism only exists on the surface of the material. The onset temperature is between 50 and 75 Kelvin, so it's very high, the onset temperature, but the moment like that you measure is extremely weak. It's of a fraction of like 1/1000 like Bohr magnetron per ruthenium atom. So which immediately tells you this cannot be conventional ferromagnetism or antiferromagnetism, okay? And also we know that it's static in nature and it's homogeneous because the muons give you no spatial resolution in the AD plane. So this means that whatever you're observing has to be homogeneous for the sample. It has to be consistent with the structural, the crystal structure of SRO, and things have to correlate. So whichever are the sources of magnetism, they have to correlate on a scale that is comparable to the unit cell, so on the atomic scale. So these are the features, the pieces of the puzzle that you have to put together. So as I said, like you can exclude conventional ferromagnetism, but also antiferromagnetism. I mean, and SRO is tetragonal. So if it was something antiferromagnetic generating what I showed you before, there is no reason why the magnetic moment like should be so low. In fact, with in compound doped with calcium, they've measured like a moment, like but it's of the order of 0.1 Bohr magnetron per ruthenium atom. The other thing is that it cannot be due just to impurities on the surface because again, the samples are randomly cleaved, so there is no reason why always this magnetism appears there due to surface impurities. And we also did scanning squid experiment with the group of Bina Kalinsky to disprove the presence of surface contamination. So if you think about the correlation between long-range ordering between, for example, spin impurities like inside the material, again, this would require, like in a metallic Fermi sea like the one of strontium ruthenate, an extremely high RKKY interaction or a very strong crystalline isotropy. But again, this should result in a very high magnetic moment and not in this very tiny moment that we observed. So it's a very weak magnetism, although it has a high onset temperature. So to explain these results, I mean, we asked for help to Mario Cuoco, like that came up with this model. So the idea, like, you know, behind this magnetism is that this is generated by a reconstruction, like so basically the reconstruction on the strontium ruthenate surface induces some electronic like instability, if you want, at the Fermi level. And these ones like basically result in what are called orbital loop currents. So orbital loop currents have been proposed for other materials like cuprate, iridates, but people have never really found evidence, strong evidence for their existence. In our case, we think that these orbital loop currents generate from Coulomb, from these electron instabilities due to like Coulomb type interactions between electrons of the p orbitals at the oxygen, planar oxygen sites and the d orbitals at the ruthenium sites. Now, if you calculate like these, we just consider this asymmetric case where, as you can see, the orbital loop currents are flowing like within each plaquette, like in two opposite directions. So on one side of the plaquette clockwise, and the other side like counterclockwise. So the thing that you can see here from this theoretical calculation is that, first of all, compared to the non-magnetic case, which is the straight line here, the orbital loop current phase, like, you know, is energetically favored. So this is like the free energy of this state. And also like the kind of shift that you measure between these, the free energy of these states and the non-magnetic one is of the order of like, you know, a few milli-electron volt, like, you know, 10 milli-electron volt here. So corresponds to the type of onset temperature close to 100 Kelvin that we observe. Okay, apart from this, like you can also calculate the field that this orbital loop current generate, like, and this also is consistent with the 10 Gauss that we measured experimentally. I can give you more details if you're interested during the discussion time, but the point is, because I'm running out of time now, but the point is that we found evidence for this unconventional magnetism on the surface of strontium ruthenate. Again, we think that it's due to orbital loop currents, this magnetism that we observed. Why is it interesting? Because, I mean, this now magnetism on the surface triggers a whole bunch of questions about SRO, because you have something that even before going into the superconducting state breaks time reversal symmetry due to the surface magnetism in the normal state. So the question is, how does superconductivity basically react to this state breaking time reversal symmetry on the surface? Does the order parameter, for example, reconstruct to accommodate the presence of this normal state time reversal symmetry breaking? And the other thing is that this field, as I said, that in the muons experience of the order of 10 Gauss. Now 10 Gauss is slightly higher than HC1 of SRO. So for example, one could speculate that this homogeneous surface magnetism is setting the whole SRO into a vortex liquid state that also breaks time reversal symmetry. And this, for example, can explain some of the earlier muon studies done on bulk, where they show evidence for time reversal symmetry in the superconducting state. Unfortunately, we cannot go lower with the low energy muon setup to track, like in temperature, what happens like below TC. Because the base temperature is 2.5 Kelvin in this system. So with this, I would like to thank the collaborators, like, and also my group, and in particular Roman, my PhD student that did part of the work here. So I'll take any questions, and thanks for your attention.
Thanks, speaker.
Yeah. Yeah, I mean, as I said, like this is an interesting question, but we cannot track, as I said, what happens to this time reversal symmetry break as the superconductivity gets in, because the base temperature of the system of this low energy muon setup is 2.5 Kelvin. So we are 1 Kelvin above the TC of strontium ruthenate. So there are like plans to implement this, you know, a low temperature cryostat and PSI, but these are like long-term plans. So it would be interesting to see what happens, of course, on the surface at low temperature. I can hardly hear. Well, I mean, a spin density wave, as I said, like, I mean, I would assume that a spin density wave is more dynamic in nature, no? I mean, like, yeah, but I mean, like the temperatures here, like it's really low, and the moment again, like I mean, the temperature is like 50, 70 Kelvin, but the moment is extremely low. I mean, yeah. Possibly not, but I mean, I'm not aware, like, if they try to look for it as well, like, you know, doing other type of studies, like this spin density wave. My guess is that people have tried also to look for that. Yeah, exactly. Yeah, it's extremely difficult, yeah. I mean, people have tried, like, okay, of course, scanning squid is not the way to look for spin density wave, but I mean, they've also tried ARPES, which is again not the way probably, but I don't know.
Maybe you can
yeah,
discuss.
Yeah. Okay. Thanks.
Okay, thanks again.
Thank you.
Ke-Jin Zhou. 20 minutes.
All right, good. So yeah, good afternoon, everyone. First of all, I'd like to thank Antonio Bianconi and Claudio Marcelli for the nice invitation. I'm really honored to be back to Frascati again and to present our latest work on the infinite layer nickelate superconductors. I realized that although there's a few talks about nickelate earlier in the morning and this is one of the few talk about the infinite layer nickelate, which is in the form of D9. So I just want to highlight this is quite different to the 214 or 113 perovskite nickelate. So, but yeah, I just want to extend that discussion a bit more towards the spin and charge dynamics in general. So this is the outline of my talk. I will give you a brief summary of the history of the infinite layer nickelates. And then I will talk about the spin dynamics, which is the magnons we discovered in this group of materials. And also most recently, the charge dynamics, namely the charge density waves observed in the same group of families. I will only show you some of the brief results, but for more systematic work, and please refer to these two works as mentioned here. So needless to say that I think that cuprate, superconductors is probably the most exotic families in the condensed matter physics from the point of view of the fundamental research and the practical application. So we have seen this phase diagram many times over the last couple of days, so I will skip the detailed explanation of the rich phase diagram. But I just want to highlight that these unconventional high TC superconductors are derived from a magnetic insulator with a perovskite structure. So since the first discovery of the cuprate in 1986, that people have been trying to search the superconductivity in a structurally similar 3D transition metal oxides. But however, there's no superconductivity discovered so far. And one of the obvious things people have been trying is nickelate, because as we know in the periodic table, nickel sits next to copper. So in late 90s, that theoreticians have been looking into these systems that in this work that Anisimov and co-workers, they predict that the nickelate analogs to the cuprate in the form of a 1+, meaning that if one could drive the nickel ions to force into a planar corner coordinated system with oxygen ions, and then a spin half, a magnetic insulator could be realized. Although, structurally this could be difficult. So this was the first theoretical prediction that people were hoping that a structurally similar nickelate analog could potentially achieve superconductivity like that was realized in cuprates. However, a few years later, that Lee and Peckett, they provocatively reported that the system is actually quite different to the normal cuprate, meaning that first of all, that there's a substantial overlapping or the hybridization between this nickel D Z square with the lanthanum 5D the square orbitals, meaning that there are sizable contribution of the rare earth 5D electrons towards the Fermi level. And secondly, that there's a substantial reduction in the charge transfer, meaning that the electronic hopping between the oxygen towards the transition metal ion become largely reduced. So Experimentally, this can go all the way back to early 80s. These people have preliminarily looked at the potential to reduce the form of perovskite 113 phase towards 112 phase. And a more in-depth study from Hayward and co-workers, they found that using the sodium hydrate as a chemical reducing agent, they could deintercalate the apical oxygen from the perovskite nickelate in order to achieve the infinite layer nickelate. So this work, they reported that they could form a bulk structurally 112 phase. However, the system is non-superconducting and potentially due to structural defects and these contributions towards the material. So then, as we all know that in 2019, that people from Stanford University finally successfully found superconductivity in the infinite layer nickelate. So what they essentially found is that in the form of 112 phase with a nickel 3D9, superconductivity can be realized. So I think this is a very profound discovery, I would say. And as a simple physics that meaning that the 3D9 in a two-dimensional metal oxygen 2 planes, and this concept works, that seems like superconductivity can be realized. But you may wonder why it took 20 years to come, because the bulk form study has been done in late 90s. So I just want to show you a simple diagram that, from the chemistry point of view, that we all know that nickel element is most stable in the form of 2+, as we learned in this morning from Claudio, that in the 214 phase, also in the nickel oxide, if you drive the nickel system from 2+ to 3+, it becomes unstable. However, people can still realize that in a bulk or in a film-like forms. If you drive the nickel 3+ towards 1+, the material becomes extremely unstable, and usually it deforms, and there's defects, and that is why potentially that the early study from the bulk form point of view, it cannot be realized in terms of superconductivity. So it seems like the group people from Stanford, they really understand the key. So what they actually did differently is that they grow the perovskite 113 phase on a strontium titanate substrate. And particularly the film is only a very thin tens of nanometer in the form of 10 to 50 nanometer. One thing worth mentioning that if you grow the perovskite film to like 30 or 50 nanometer, the superconductivity becomes extremely difficult to realize. So this again tells you that structurally that it seems like the 112 phase can be better realized on a support of the substrate. So a few years later that the picture become clearer, namely as we see here in this phase diagram that people have been able to realize that not only the neodymium, strontium nickel oxide and 112 phase, but also the lanthanum praseodymium counterpart, they all show superconductivity. If you look at the phase diagram, it looks like there's a dome-shaped doping dependence, similar to the cuprate, although there are differences in terms of the two end parts, which show different electronic properties. If you look at the TCs, as we just see that, it is more moderate in the order of 10 to 15 Kelvin. It's almost order of magnitude lower than the cuprate. And most recently, there's a study looking into the rhodochrome pulper phase that people have seen that the superconductivity can be also achieved. So this is again saying that when you drive the nickel state towards D9, superconductivity can survive. So you may wonder that what's the similarity and difference between the two groups of materials. So as we know that, that cuprate is a charge transfer type, meaning that the on-site Coulomb repulsion is much greater than the charge transfer energy. The parent compound, a strong insulator with antiferromagnetic long-range ordering. As we can see that there's no presence of the rare earth 5d electrons, and the system is largely described by a single orbital or single band system with a character of in-plane dx square minus 1 square. For the nickelate, as you can see here, that the system is much closer to a Mott-Harbor type, meaning that the on-site Coulomb repulsion is much smaller than the charge transfer energy. And there's strikingly that some presence of the rare earth 5d electrons across Fermi level, which makes the parent compound as intrinsic metallic-like or weakly insulating-like. And interested, there's so far no long-range ordered antiferromagnetism being found. As said, because of the presence of the rare earth 5d electrons, the system behaves like a multi-orbital system with the coupling of the 3d from nickel and rare earth 5d electrons. So here are the questions. Are these non-magnetic ordering intrinsic or extrinsic? Because I said earlier, the materials is very unstable. And could this missing long-range ordering is due to defects? Or is this more due to the intrinsic presence of 5d electrons? And is any short-range ordered antiferromagnetic spin fluctuations if we so far haven't successfully, see the long-range ordering? And how strong are they? As I said earlier, the TC of this material is order of magnitude lower. Does that mean that super exchange value is similarly order of magnitude smaller than the cuprate? So with these questions, we start to look into one of the thin films, the neodymium nickel oxide 112 phase using Rick's technique, as shown here. We did experiment at Diamond using the Rick's machine. Just to want to mention, highlight that Rick's is probably the most suitable technique for looking to the spin-spin charge correlations in this group of materials, particularly because that Rick's tuned towards the nickel LH with the penetration depths of tens of nanometer. So it's ideal for looking into this, thin film-like systems. And for the experiment, we've done that we have basically the material having the z-axis line, the scattering plane, and most of the measurement is done at cryogenic temperature of 20 Kelvin. So here's the main result. So yes, indeed, we see the strong antiferromagnetic short-range fluctuations. So as you can see here, coming out of the zone center, that the magnons disperse quite clearly along the pipette direction, approach the maxima around the zone boundary, and then bend back. Along the pi zero direction, the magnon go all the way up around 200 millivolts. And there's also sizable dispersion in the zone boundary directions. If you extract the energy position of the magnons as a function of Q, you can plot in this plot then. And using the linear spin wave theory, we fit the dispersion. What we extracted out of the curve is that the next super exchange J is around 64 millivolts, and the next nearest J is minus 10 millivolts. So immediately you see that, first of all, this is actually quite comparable to cuprate. It's about half of the cuprate typically. And on top of that, we see that it's antiferromagnetic-like next nearest neighbor and ferromagnetic-like in the next nearest. This hints that a similar kind of magnetic structure, if they are, comparing to cuprate. So we see some interesting physics coming up here. And secondly, that as we see here, that the forward half maximum is slightly bigger than the energy resolution of the instrument. However, the magnons are still well defined. And this result signals strongly there's a bit of quite strong correlation physics happening in this group of materials. And finally, if you start doping the material, we can see that the magnon gets suppressed and also softened as a function of dopings. So I just want to plot again that the dispersion besides the cuprate. And you can see that this is astonishing similarity between the nickelate and cuprate. Again, highlighting the potential, the same antiferromagnetic ordering between the two systems, and implying that if there's a long-range order, that the wave vector should be stabilized at half-half positions. Secondly, another key message is that the magnitude of the superexchange, J, of the infinite layer nickelate is actually comparable to that of cuprates. So this again suggesting a strong Coulomb repulsion and maybe potentially a higher TC if the quality of the materials can be better controlled. So most recently, I just want to mention that the magnetism of the infinite layer nickelate has been looked at by the MUSR and across a group of materials, as you can see, the neodymium, praseodymium, lanthanum, and all these kind of showing that the system is actually all magnetic, and some of them may approach an ordered magnetism in the low temperatures. So highlighting that this material is indeed intrinsically magnetic material. So in the next, that we basically answer the question that so that the antiferromagnetic fluctuation does exist in the infinite layer nickelate, similar to the cuprate. And as we know that there are a lot of exotic phases existing in the cuprate materials, for instance, the charge density way. So a natural question to ask as a next step is that, do the infinite layer nickelate possess the similar ordered phase or not? So having this question in mind, and we start to go back to the neodymium 112 material again. So just as a few spectroscopic evidence, just to highlight that, as you can see, this is the nickel L3 absorption age. There are two peaks, and the main peak is, as learned from the previous work, on a similar system, which is lanthanum 112 phase, that corresponding to mainly to the nickel 1+, which is D9 excitation. There's also the pre-peak, which is assigned to the hybridization between the nickel 3D and neodymium 5Ds. The hybridization is mainly confirmed because of the in the RIG spectrum, that if you look at the excitations around 0.6 eV, that this resonant at the pre-peak as a signature of the hybridization. So if you look at our result from the neodymium case comparing to the lanthanum case, there are a strong similarity between the two. First of all, that the DD excitations is happening at the same energy scale, around 1.3 EVs, like the lanthanum nickelate, and also this pre-peak thing, as mentioned, the signaling the hybridizations. So basically that we confirm that the systems between the two are very similar from the electronic structure point of view. So we then went away to look at the RIGs in terms of the Q resolution. So to show you that one of the typical RIG spectrum, that, as you can see here, we took a Q of 0.2 along pi0 direction, and this is how it looks like. So then we start to do the Q dependence and integrate the energy scale around the elastic peak. So what we see here is by scanning along the gamma X direction and gamma M direction, and we found some interesting diffraction peak appeared along the pi0 direction. If you scan along the 0K direction, similarly, we can see another diffraction-like peak. And all these peaks seem to exist around 1/3 of relative unit. However, if you scan along the gamma M, which is the nodal direction, there's no such peak formed. To ascertain that the robustness of the diffraction peak, we scanned across multiple samples, and we found that all these diffraction peaks do exist. So what are they? Are they from the structure or from the electronic? So here we just did a bit of detailed study that we look at the polarization dependence, and we found that the signal enhanced much strongly in the sigma polarization than the pi. We then fixed the Q value at the wave vector and scanned across the absorption. And interestingly, we found that the two resonance peaks appeared in the energy detail, meaning that there's a strong coupling to the electronic decrease freedom. We also went to the off resonance, and the peak disappears. So as we all learned from cuprates, and these are the typical ways to differentiate the signal, whether it's structural or whether it's electronic. More in detail, we went to compare the CW signal from the cuprate. So here's just a detailed study. I just very briefly mentioned that. We plot the polarized signals in terms of the sigma pi ratio and plot on top of cuprate, and we can see that the intensity follow nicely along the theory curve. So, and this is one of the strong evidence showing that indeed the signal we see here are from the charge density degrees of freedom. So if you look at the correlation length, the CW has a typical value of around 60 angstroms, and they form along the pi0 direction. And this is very similar to the cuprate. And I want to highlight that in the normal 214 perovskite, the nickelate, the CDW is formed along the pi-pi diagonal directions. If you look at the resonance behavior, that as I mentioned earlier, there is a strong correlation between the neodymium 5D and nickel 3D. So if we excite at this pre-peak, interestingly, we found almost the same diffraction peak with the similar correlation length. If you go to the neodymium MH, which is probing the 4F state, we can see that the signal become much weaker. And this tells about basically that in terms of degrees freedom, that the 4F state participate much weaker in the low energy physics of this group of materials. And this is just a bit of detailed studies, which I will not go into to explain that. Basically, what we found is the strong correlation of the CW intensity with the hybridization strengths of nickel and neodymium. And what we found basically is that the weaker of the hybridization, that the weaker of the CW, which again tells something about the role of the neodymium 5D electrons in this group material. If we go to the superconducting material, CW disappears. We also did a bit of temperature dependence, and as we can see here, that the intensity goes exponentially weaker, which is again a similar behavior like people have seen in the cuprates. And finally, we also did a bit of the L dependence. As you can see here, it looks like that the system shows some non-negligible L dependence as the intensity changes as a function of L value, as plotted in this 2D map. So it seems like the system, there is some contribution because of the neodymium 5D electrons that the CDW behave is more 3D-like than the cuprate systems. So before I finish that, I just want to mention that almost in the similar time that there are two independent reports that the CDW signal was also discovered in the lanthanum 112 phase, and also in another, the neodymium 112 phase, which again highlight the CDW physics is indeed a more generic thing in this 112 phase nickelate systems. So to conclude that, I hope I have showed you that there are strong magnon dispersion in the inclinated layer nickelate, and that the J value is actually comparable to the cuprate. And the dispersion along the zone boundary has the same profile as those of cuprate, indicating that if there is a antichromatic order, which should be centered around the same Q vector as a cuprate. And I have shown you the CW is indeed common in the nickelate again, and there are similar, the temperature dependence as a cuprate, but there are also a strong difference that namely the 5D valence states play a role in this group of multi-orbital physics. So before I finish, I just want to quickly acknowledge my people from Diamond Light Source and the collaboration from China on the high quality nickel thin films on the CW study, and also the close collaboration with Stanford group on the Magnum studies. And with this, I'd like to thank you for your listening.
Thank you. Thank you for a nice talk.
Yeah. Okay. Yeah, thanks for the interesting question. So I said it's close to Mount Hubbard. I think it is close to Mount Hubbard with the form of that charge transfer energy is much greater. However, there's a strong evidence that there's a very sizable, strong hybridization between the nickel and oxygen. I think from most recent oxygen cage studies, meaning that initially people have thought that oxygen does not play a role, but I think most recent data suggests that it actually does. So I think to be more accurate, the material is probably more like in the middle rather than really at the most Hubbard, but more like in the middle between the charge transfer and most Hubbard. Yes. Yes.
One of the arguments here, which I don't quite understand, is bad metal weakens sweater behavior as evidence for Mott Hubbard. Now, I don't exactly see, I mean, many different people use this word bad metal in different way.
Yeah.
What?
Sorry, yes, I just want to, so let me just have a look whether I have some spectroscopic data. So yeah, you're right that the definition that in terms of just because of the energy diagram is not, really accurate enough, but there are strong evidence of the spectroscope evidence.
I mean, first of all, when you say bad metal, some people call bad metal when it's metallic, but it goes as high, the resistance is high at high temperatures. That is what Kivelson calls bad metal.
Yes, but
when it's the opposite, when it goes up at low temperatures, that is different. So which one are you?
So I'm referring the bad metal is if you look at the
yes, red. Right?
If you look at the red, yes.
Right. Yeah. So this is something that is seen in cuprates also in the pseudogap phase. In fact, there is a logarithmic temperature dependence in which
But
whether
this is
whether this is Mott Hubbard or something else, that's very hard to say. What in my talk and in general, when people see something like this, it usually has something to do with homogeneity of some kind.
Sure. I totally agree with you. I don't think I claim that this is Mott Hubbard based on the transport property. There are a lot more spectroscopic data suggest that conclusion. However, the one key difference between infinite layer nickelate and cuprate is this is the parent compound, not the doped case.
Can I just ask, what is exactly the temperature dependence here? I was just curious. What is the temperature dependence of the red curve at the lowest temperature?
So it goes towards, well, as you can see, it's diverged. It's more kind of like insulating
Is it actually
type.
diverging or not diverging?
I think one is look at the details, how much when it's closing to the
not,
table.
it's not activated, it's weak, right?
Yeah, it's weak,
But it's not logarithmic either.
I'm not sure. I think one is look at the detail. I think one of the things in this new group of families material is that the transport properties largely depend on the quality of the material. So suggesting that there's growth from the defects. So yeah.
I suggest to finish this talk and send speaker again. Next speaker is Dragana Popovic.
All right, so before I start, I would also like to thank Antonio, who is not here right now, but anyway, for organizing, again, a successful Superstripes conference. It's really nice to be back here in person. I would like to acknowledge my collaborators, who include former and current members of my group at the National High Magnetic Field Lab in Tallahassee, Florida. In particular, Ke-Jin Zhou, who is now at Suzhou University, made major contributions to most of the work that I will discuss today. Of course, none of that would have been possible without really excellent single crystals that were provided grown by Takao Sasagawa and more recently also by Shinpei Ono. So I'm sure everybody's getting tired of this phase diagram, but here it is again. Basically, to point out that some of the key questions in the physics of whole-doped cuprates that motivated our work are the question about the nature of the ground state if superconductivity is removed, what is the role of the interplay of charge and spin orders with superconductivity, and of course the origin of the pseudo-gap regime. So the focus of this talk will be on what happens in the limit of zero temperature when magnetic fields are high enough to fully suppress superconductivity. What are the properties of such field-revealed non-superconducting state? And we are going to focus on the materials on cuprates that exhibit strongest charge and spin orders, in particular those that exhibit stripes. So we are really looking at the regime around 1A doping where TC is suppressed. So the reason why I'm giving this talk is because you will see that in this field-revealed normal state in the zero temperature limit, there are some new intriguing properties that are surprisingly robust. So we focused on these two materials, LSO with partial substitution of by europium or neodymium of lanthanum. These two materials are very similar to LDCO. They have the same structure, and below certain temperature, charge and spin stripes are stabilized in copper oxygen planes such that they are rotated by 90 degrees from plane to plane. And we focused on these dopings shown by the vertical lines. So in LNSO, we are at 1/8 doping, and in LESCO, the doping is somewhat lower, 10%, so stripe correlations are weaker. And you can see that the TC is very low, only 4 or 5 Kelvin, which is much lower than the onset of spin and charge stripes, and also much lower than the pseudo-gap temperature, which is of the order of 150 Kelvin. We define TC as the temperature where resistivity becomes vanishingly small, or where it falls below the noise floor. So, okay, so first we need to know when the superconductivity is completely suppressed. And this issue, the question of the upper critical field, was actually under debate for decades, which is why we needed to put some time and effort into resolving this question. So the phase diagrams of these two materials that I just mentioned summarize the results of our linear and nonlinear transport measurements. So note temperature is on a logarithmic axis. The black symbols show the values of TC. So below this temperature, resistivity is 0. And you can see that by very small fields of about 5 Tesla, TC is suppressed to 0. So our vortex solid melts by the magnetic field here. And this vortex solid is separated by the field-revealed normal state by a wide range of fields of the order of 15 Tesla at low temperatures that we have identified from linear and nonlinear transports, in other words, measurements of the voltage current characteristics, as the regime, as the vortex liquid regime, and at low temperatures, this vortex liquid moves in the presence of disorder. So basically here we have finite linear resistivity, which with decreasing temperature drops to 0, so the material becomes a superconductor here only at 0 temperature. And at high temperature, and the boundary of this region is given by these red points. So it is below, on the left side, at lower fields of this boundary, we find non-ohmic transport for finite applied DC currents, and everywhere else, transport is ohmic. So here we have ohmic transport, but we still have positive magnetoresistance, which is attributed to the suppression of superconducting fluctuations. This is identified as the vortex liquid regime, and I will come back to this later also in the talk. So basically the physical picture is that at high temperatures, thermal fluctuations melt these vortex solids. So we have this vortex liquid. As we reduce the temperature, the thermal fluctuations are, become smaller, but the effects of disorder become more relevant. So vortices, it's becoming more difficult for vortices to move. They become slow, sluggish, and eventually this vortex liquid freezes into a vortex glass at 0 temperature. And finally, we have these open blue symbols here, which indicate the onset of Gaussian superconducting fluctuations determined from magnetoresistance measurements at these high temperatures. And you can see that this extrapolates at zero temperature to the same field that represents the boundary between non-ohmic and ohmic transport, which further supports our identification of these fields as the upper critical field. So you can see that even though the TCs are about 4 or 5 Kelvin, the upper critical fields are fairly high, about 20 or 25 Tesla. So these phase diagrams, you can see that they are qualitatively the same, even though the strength of stripe correlations is different. And we also compare this to LBCO at 1A doping. So this is the phase diagram for this paper. Note that the field axis is reversed. But basically, qualitatively, the same results are obtained when you melt, after you melt the vortex solid, there is a region in the phase diagram where non-ohmic transport is observed, just like here. So moreover, qualitatively same results we obtained some years ago in highly underdoped LSCO, both in single crystals and in MBE grown thin films. And in this material, this range of dopings, there is no clear evidence of any charge order. So this sketch just shows is a summary of the findings from this paper. So here again, we have a vortex solid where resistivity is 0, TC is suppressed by the field, the relatively low field. And then we have this wide intermediate regime range of fields where resistivity drops, it turns out in a power law fashion, to 0 at 0 temperature. And only at higher fields, there is a quantum phase transition to an insulating regime. So what this means is that vortex phase diagrams are qualitatively the same regardless of the strength or the presence of charge orders. Vortices don't care, and what's important in the 0 temperature limit are quantum phase fluctuations and the presence of disorder. Now, what about spin order? Does that matter? Well, recently we studied underdoped bismuth 2201 at essentially the same hole concentration. And this material has no spin order, very weak charge order, and we find qualitatively the same vortex phase diagram. So this means that, you know, spin order is not important for this as well. Also, there have been recent studies of nonlinear transport in YBCO, and basically the data are also consistent with general expectations for the vortex matter. So what is the nature of the field revealed normal states? Now we're looking at the region above the upper critical field. Now what people obviously have been trying to figure this out from the early days of high TC, and it was reported years ago by Ando and Bobiger in underdoped LSCO that the temperature dependence of the resistivity at high magnetic fields is insulating, but it exhibits this peculiar logarithmic temperature dependence in both in-plane and out-of-plane transport. So you can see it fits maybe the range of about temperature, about an order of magnitude. Here at higher doping, it's about an order and 1.5 orders of magnitude in temperature where this unusual logarithmic temperature dependence is observed. And there is still, up to this date, no good understanding of the origin of this behavior. Later, there were also some studies of a very underdoped LSCO, and it was found that at lower temperatures, temperature dependence becomes stronger. So, you know, there is general agreement that the high field ground state in underdoped LSCO and also other hole-doped cuprates is insulating. And after this work, also logarithmic temperature dependence was also observed in other cuprates. So this has remained a mystery. So it was even more surprising for us to see what happens in these stripe-ordered cuprates at fields above the upper critical field. Actually, this is the regime that has not been explored at all in these materials so far. So we found, again, this peculiar logarithmic temperature dependence in both in-plane and out-of-plane transport. These figures show the in-plane data. So what is unusual here is that as we increase the field here from 18 Tesla to 35, we see that this temperature dependence actually becomes weaker. So it becomes less insulating. The slopes decrease with the field, and they're shown by these black symbols here in these insets. So if one could, we extrapolated very simply this decrease of the slope to high fields. We don't have the data there, but it seems that at some fields high enough, the slope would become zero. So this means that at zero temperature, the resistivity is finite. In other words, this data suggests that high field normal state of these striped cuprates may be a metal, in contrast to what has been believed so far. So we do not know, still do not know the origin of this peculiar temperature dependence, but it seems that the presence of stripes does affect the nature of the normal state. So in order to gain a better understanding of this unusual regime, we have also performed studies of the Hall effect, and measurements of the Hall coefficient are important because in principle, Hall coefficient reflects the degree of particle-Hall asymmetry in the material, so it provides insight into the microscopic picture of the material. So in the simplest case of in a single band metals in the limit of high fields and zero temperature, Hall coefficient is just a constant, and it depends only on the concentration of sign and charge and sign of charge carriers. But in general, it can be affected by various effects as shown here. So in practice, it often depends on the magnetic field and temperature, and the interpretation is difficult, or let's say challenging. Nevertheless, Hall measurements have been widely used to probe cuprates. And for example, it is now well established that in all Hall-doped cuprates near 1A doping, the positive Hall coefficient decreases with decreasing temperature. And in some cases, as shown here, also changes sign, becomes negative. And this has been broadly or widely attributed to Fermi surface reconstruction, the appearance of electron pockets in these Hall-doped cuprates. Now, in these striped order materials that I've discussed, the Hall coefficient has not been studied much, and in particular not in the regime that we are interested in this high field revealed normal state. So we have performed those measurements. There has been a study of LBCO, which I said is very similar to our LESCO and LNSCO. And here on the left, you can see in LBCO, the Hall coefficient as a function of temperature at very high field, 34 Tesla. It decreases and it changes sign at low temperature, similar to what I showed you on the previous slide for YBCO and LSCO. On the right, we have a field dependence of the Hall coefficient in different temperatures, and you can see that there is a very weak field dependence of the Hall coefficient at all temperatures. So this may not seem surprising, but it is if you contrast this to what's been found in YBCO, where field dependency is very strong, and also in LSCO, in the absence of, so in these materials, they do not have charge and spin stripes, so it seems that the presence of spin and charge stripes affects the behavior of the Hall coefficient also. So what do we find in LESCO and LNSCO? So here are some of our data for the Hall coefficient. If anyone's interested in other data, I can show you all that later. So on the left, we have the results for the Hall coefficient in LESCO as a functional field. On the right, it's for LNSCO. You can see that just like in LBCO, at all temperatures, the field dependence is relatively weak. Just like in LBCO and other materials, as we decrease the temperature, Hall coefficient decreases. And at low fields, it changes sign, it becomes negative. But if you look at the high field regime, it decreases to 0, and then we keep decreasing the temperature, but the Hall coefficient remains 0 for all temperatures below some temperature T0. So this is actually the key finding of our study, and it is understood better if we kind of try to make a phase diagram of the different regions of different behavior of the Hall coefficient. So here at high temperatures, we have this positive Hall coefficient, which decreases to 0, and it reaches 0 at some temperature T0 that does not or depends very weakly on the field. So this is similar to what has been found in other studies in other cuprates. Then we have this wide range of fields where the Hall coefficient is negative, and finally this big region of phase space where it is 0. So what does it all mean? It helps if we superpose these results on the vortex phase diagrams that I showed you earlier. So we can see, so here again, this is this region of the positive Hall coefficient which decreases to 0. And we see, what we see next is that the region of the negative Hall coefficient practically coincides with the vortex liquid regime that we identified based on other measurements. So this suggests that, you know, these negative Hall coefficient, at least in these two materials, may be due to the motion of vortices. And we actually checked that because there is a prediction for that in this paper here, and our results do agree with this prediction. So this supports our identification of this region as the vortex liquid, and it also tells us that the origin of the negative Hall coefficient in these materials is dominated by the motion of vortices, even though some other effects may be present, but they do not dominate. So the question is now, what is the origin of the vanishing Hall coefficient in the rest of the phase diagram? Well, in this region here that we identified as the viscous vortex liquid, where it's very difficult for the vortices to move, this can be attributed to the freezing of the vortex motion. But this leaves us with this huge region of fields and temperatures, huge part of the phase diagram where the Hall coefficient is 0. Now I have to say here that vanishing Hall coefficient in stripe other cuprates have been reported years ago in these two papers, and these arrows show the points in the phase diagram where this was observed. So we can see that this corresponds to the region where, you know, here Hall coefficient drops to 0 when it gets close to this vortex liquid. And here we are very close to the freezing of the vortex motion. So it seems that this is really, these findings, observations are related to the behavior of the vortices. So on the other hand, we have so this region here has not been explored yet, and it is a huge regional phase space where the Hall coefficient vanishes. So again, this is the main finding, and the question is why? So let me just, before I discuss several possibilities, let me just mention the observations in LBCO. Here we also found a region in the phase diagram where the Hall coefficient vanishes. But here we also found evidence like non-ohmic transport, evidence for some superconducting correlations that persist. So it seems that this region kind of corresponds more to this region where we have a vortex liquid. So it's not obvious that this is the same. I mean, at least in these two materials, we see that this is a completely different regime of phase space, and here we have no evidence of superconducting correlations from any of our measurements that I mentioned and that I have not mentioned. So these are the new properties of this field-revealed normal state in the presence of stripes. You can see that this region here is more pronounced at 1A doping, so it seems that this vanishing of the Hall coefficient is crucially related to the presence of static stripes. So what can be the origin of this dependence? Because normally, if one sees a 0 Hall coefficient, this is only at for us, you know, one temperature and field, not in a huge, one region, a big regional phase space. So the first possibility that comes to anyone's mind is that maybe this is due to some still superconducting correlations that may persist, even though we may not be able to detect them in our measurements. However, so we do not see any, but I also want to point out that standard models for superconducting fluctuations all give non-zero Hall coefficients. So this is highly unlikely. Another possibility that has been, as I said earlier, discussed in the context of other cuprates to describe the change of sign of the Hall coefficient is that there are multi-band effects. However, to explain this, this means that we would have to have a near cancellation of the contributions from different bands over a wide range of fields and temperatures, as well as change in doping and rare earth composition. In other words, the robustness of our results tells us that this is an unlikely possibility. Our data also, standard localization mechanisms also cannot explain this because they do not agree with the data. And since I'm, running out of time, I will just mention that maybe the most viable scenario at the moment is the so-called smectic metal phase, which was a model proposed for striped cuprates, a model which features an approximate particle Hall symmetry for dopings less than 1/8. And also then there are some more general models for doped MOT insulators that feature emergent particle Hall symmetry. But additional experiments and different types of experiments are also needed to be able to see which of these scenarios might be able to explain this robust property. So to summarize, I have shown you that the vortex phase diagram for underdog cuprates is very robust, doesn't care about all these orders. What matters in the limit of zero temperature are, quantum phase fluctuations. So as I said, we also have unpublished data on bismuth 221 that support this. And the main finding are these peculiar properties of the field revealed normal states in these striped order cuprates. So I thank you very much for your attention.
Thank you, Dragana, for nice talk. Now time for questions.
Something you showed where this logarithmic divergence of the reflectivity flattens with increasing the magnetic field. And then you extrapolate to where it would vanish at some high and accessible, maybe so far, magnetic field. And then what? It's somewhat unexpected because magnetic field may freeze the mechanism, the scattering mechanism giving rise to this log, but then this would appear as a cutoff in the log. Apparently you have no cutoff in the log, but you kill the pre-factor. And then what if you go further? You find...
Well, okay, this is a very rough extrapolation,
yes.
And we obviously, it would be nice to have more experiments, I agree. So this is why there is a question.
Maybe you have an idea, but for me, it's really, I cannot imagine what, so maybe this flattens. And
I think it may flatten. I mean, my feeling is that actually perpendicular field may rotate the stripes. So maybe at high enough fields, we'll just have, this will stop and, but we don't have the data to support that.
I wanted your opinion on
that.
Thank you very much.
Yeah, thank you.
Any further questions? So if not, it seems to be a solution to online presentation by John Tranquada.
There is remote. There is a remote.
Where is remote?
I don't know. Who is the next?
John Tranquada. It's online.
Oh, okay.
Can you share?
Not yet. I'm trying.
Because it says
It says someone else is sharing. Ah, now I can do it.
Okay. Next speaker is John Tranquada. He is online speaker. And John, you have 20 minutes talk and 5 minutes questions. Please go ahead.
So thank you very much. I'm grateful to Antonio for the invitation to speak. I'm just sorry I can't be there in Rome with all of you. So I'd like to talk about pairing through charge order in cuprate superconductors. And before I go on, I should thank the US Department of Energy for their support for this research. Okay, we've already heard a bit about charge stripes, but I'm going to say a bit more about this. Here's the phase diagram for lanthanum barium copper oxide. We see that the bulk superconducting transition is a minimum at 1/8 doping, which is also where spin and charge stripe orders are maximized. So the charge stripes are defined by antiphase spin stripes that neighbor them. And while this is bad for 3D superconducting order, we actually find that charge stripes coexist with 2D superconductivity. So here in the lower right, you can see resistivity measurements. The green circles show in-plane resistivity, which is metallic in the normal state. It drops by an order of magnitude at 40K where the spin stripe ordering occurs. It goes down to a small value that keeps decreasing. And consistent with nonlinear transport, there seems to be a Brzezinski-Koszulec-Salas transition to superconducting order at 16 Kelvin. The C-axis resistivity, in contrast, is large and insulating. It keeps rising until we get down to a temperature below 40K. Eventually turns down, but it's quite significant still at the Koszulec-Salas transition. So that anisotropy is consistent with this being an onset of mean field 2D superconducting order at 40 Kelvin. If we look at the diamagnetism, first consider in green the response when the field is along the C-axis, so that the superconducting response is in the planes. If I put this on a log scale, you'd be able to see that there's a small onset at the spin ordering transition at 40K. But on the linear scale, what you can see is that this is becoming bulk-like already at the Koszulec-Salas transition. It keeps increasing as we go down in temperature. In contrast, if we put a field parallel to the planes, perpendicular to the C-axis, so that we need Josephson currents running between the planes to shield the field, we see essentially no diamagnetism until we get down to the bulk transition at 5 Kelvin. So there's also the impact, the observation of how the holes respond in high magnetic field. Dragana just talked about this, so I don't need to say much. But here are the results on 1/8 doped LBCO, magnetic field versus temperature. And here is the Hall constant as a function of temperature, covering the full field range. So as she mentioned, the Hall constant at low temperature and even up to high magnetic fields stays negligible within these error bars, which suggests particle hole symmetry. And particle hole symmetry is natural in the superconducting state because of pairing, but this suggests that even when we lose the phase coherence, the holes in the charge stripes are still paired, even though they can't move coherently with each other as they move between the stripes. Okay, so there's been a lot of work on charge stripes and superconductivity, especially by the Rome group. As I understand it, their perspective is in terms of fluctuating charge density waves. So the idea would be that quasi-particles could interact with fluctuating charge density waves, which could drive superconductivity. There's been some talk on related topics here. An approach that I've been more interested in over a long time is that of Emery, Kivelson, and Zachar. They argued that one could consider a charge stripe as a 1D electron gas. Then if there's a spin gap in the environment that can be transferred by proximity effect to the charge stripe, that will induce pairing correlations. Now the problem is that that cannot explain superconductivity in 1/8 doped LBCO because we have spin stripe order and no spin gap. So I want to argue that the answer is, the solution here is to think of the charge stripes not as a 1D electron gas, but as a doped two-leg spin ladder. So let me remind you a little bit about two-leg spin ladders. So here's a schematic of antiferromagnetic spins in a ladder. We're assuming we've got superexchange J along the rungs and along the legs. Now, this system is actually fluctuating, not static like this, so it's better to think of singlet correlations between pairs of spins in the ladder. And if J is comparable on the legs and rungs, then we'll get resonating valence bond behavior in the system, singlet correlations in both directions. Now, if we dope holes into the system, if those holes go in different places, they will end up breaking singlet correlations, which cost significant energy. Therefore, it's more favorable for the holes to form pairs in order to avoid breaking the singlet correlations of the spins. Now, this concept for pairing was first proposed by, as far as I know, by Delgado, Riera, and Scalapino back in 1992. There's a nice paper by Delgado and Rice talking about spin ladder physics from Science in 1996. For neutron scattering measurements, it's relevant to think about the magnetic dispersion within a spin ladder. And this was a calculation from Barnes and Riera in 1994. This is the dispersion along the spin stripe at the antiferromagnetic wave vector. If you have a superexchange J, the bandwidth will be approximately 2J, and the gap will be about J over 2. So before I get to the excitations in LBCO, let me talk about a lesson on how to think about decoupling charge stripes. It came from a somewhat unexpected place. This is from the case of stripe order in lanthanum strontium nickel oxide. This is the 214 system, not the 112. So we know we have diagonal stripe order in the system. The stripes are insulating, so very different from the superconducting case. But they've got an antiphase character around the charge stripes. And at 1/3 doping, we have a 3 lattice spacing charge period along the diagonal direction. Now, with inelastic neutron scattering, we can measure the magnetic excitations of the system. They are dominated by the spin excitations of the spin stripes. So here's dispersion of these excitations rising out of the incommensurate spin stripe order wave vectors. This is at low energy. This is at higher energy. It's a little challenging to see the dispersion on top of all the phonons that are crossing through here. But if we take constant energy slices through here and look at them as increasing energy as we do on the right here. Here at low energy, we see basically peaks at the incommensurate spin order wave vectors. And as we rise in energy and they disperse out, the slice looks like circles that expand as we go up in energy. Now that's just to contrast with an extra component that can be seen at low temperature and low energy. These are measurements at an excitation of 3 millielectron volts. This plot was obtained by taking a measurement at 5 Kelvin and subtracting a measurement at 70 Kelvin. Besides the excitations from the spin stripes, which are associated with these incommensurate peaks, and then there are phonons around fundamental Bragg peaks that are these big circles, you also see one-dimensional streaks in the system. In fact, these aren't just one-dimensional, they're sheets of scattering, as we've checked. They're running in two directions because we're averaging over two stripe orientations. We've got twin stripe domains. The fact that these are sheets of scattering indicates one-dimensional correlations in real space. These excitations were first detected by Boothroyd and collaborators in 2003. To understand them, we have to think about spin excitations on the charge stripes, because that's the only thing left in the system. We've seen what the spin excitations from the spin stripes are like. If we think about a site on a charge stripe, say a nickel site, it has two downspin neighbors and two upspin neighbors. So in terms of spin correlations, it's geometrically frustrated with respect to the spin stripe environment. We start out with a spin 1 on the nickels. If we have one hole per nickel site within the charge stripes, then we can still have spin 1 plus a spin half, giving us a low spin a half along the charge stripe. And these can couple along the stripe to give us 1D spin fluctuations. We find that these spin excitations along the insulating charge stripes are gapless and relatively low energy. The point is that there are spin degrees of freedom on the charge stripe. So now let's think about what that means for lanthanum and barium copper oxide at 1/8 doping. So we've measured the spin excitations in the past. This is the effective dispersion that we see. There are incommensurate excitations at low energy coming out of the magnetic superlattice peaks. These merge together at about 50 millivolts, and then we see an upward dispersion. It looks anti-ferromagnetic-like. In fact, this red line is the predicted dispersion for a two-leg spin ladder with a J of 100 millivolts. So you get a bandwidth of 200 millivolts and a gap at the commensurate antiferromagnetic wave vector of about 50 millivolts. Now, if we think about the nature of the correlations, if we take constant energy slices through these excitations at low energy, we see sharp peaks, which suggest long-range correlations. But as we go up in energy, the excitations become quite broad, which suggests that we've only got very short correlation lengths at high energy. So let's think about how to make sense of these excitations. Here's the effective dispersion. We should really take into account the widths of these excitations, which are sharp at low energy, broad at high energy. That's still consistent with this sort of dispersion. But now let's think about what's going on at low energy. At low energy, the spin excitations are dominated by the spin stripe order. Within the charge stripes, let's think of them as two-leg ladders. There's spin degrees of freedom in the charge stripe, but they have singlet correlations, so they're gapped at low energy. We don't see anything at the commensurate wave vector. If we go up to high energy, at high energy, above 50 millivolts, an excitation along the charge stripes will flip a spin singlet into a triplet. This will delocalize the holes in the system, which can now move through the system. And we end up with a system with very short spin correlation length, consistent with the strong damping in here. So we have deconfinement at high energy, but the important thing is we have confinement at low energy, which gives us the pairing. Now, let's think about what that means for superconducting order. The spin stripes are great for decoupling the charge stripes and allowing pairing to form, but that behavior also gets in the way of trying to get uniform D-wave superconducting coherence in the system. So here's a sketch at the top of uniform D-wave order. I've used orange and blue on orthogonal bonds to indicate the sign change in the pair wave function when you rotate by 90 degrees. When we have spin stripes in the system, it means that we can get uniform D-wave within the charge stripes, but it needs to change phase as we go from one stripe to the next. The way we can get phase coherence in the system is in terms of a paired density wave modulation, which changes sign from one charge stripe to the next. It actually has the same period as the spin modulation, but it's shifted in phase. Now, this picture of a paired density wave order can explain the lack of three-dimensional superconductivity, because 3D order depends on establishing interlayer Josephson coupling. And given the paired density wave modulation in each layer and the rotation of the stripes from layer to layer following the structural anisotropy, the Josephson coupling will average to 0 for these layers, consistent with 2D superconductivity. Of course, most superconductors don't show simple 2D superconductivity, but show 3D superconductivity. So let's think about how we can use the same picture to understand that. Let's consider lanthanum strontium copper oxide. The blue symbols here indicate the superconducting transition temperature. The symbols above indicate measures of charge stripe correlations. The red symbols are from hard X-ray scattering. They aren't indicating an absolute onset of intensity, but rather where the correlation length is growing longer. Now, these measurements integrate over fluctuations, and I suspect that the charge correlations here are actually fluctuating. And the intensity actually goes down in the superconducting state. So the key isn't here that we have charge order, but have charge correlations. We also have spin correlations, incommensurate spin correlations that are seen by neutron scattering. Here is the weight of the dynamic susceptibility at the incommensurate wave vectors as a function of frequency in optimally doped LSCO as measured by Christensen and collaborators back in 2004. And the key point is that as you go from the normal state to the superconducting state, you develop a gap in the spin fluctuations. It's this gap that's key for getting the uniform superconducting order. So we've extended some of this. We've looked at 17% and 21% LSCO. We've measured the dynamic susceptibility versus frequency. If we take the difference between low temperature and normal state, as we see in the bottom here, at low frequency, we see a loss of spectral weight. We see a gain of spectral weight. At higher frequency, we define the spin gap as the point at which this change goes through 0. We get similar energy scales of about 9 millivolts for both of these samples. We've looked in the literature for measures of the coherent superconducting gap, which is the energy scale below which superconductivity looks uniform in the planes. That is a very similar energy scale for these compositions. So that led us to look for related results in the literature for other cuprates. Here's a plot of the coherent superconducting gap scale versus the spin gap scale. If these were equal, they'd follow this dashed line. What we find is that the coherent gap scale is less than or equal to the spin gap scale. So this suggests that the spin gap limits the coherent superconducting gap in the system. On the other hand, I've argued that it's the energy gap at the antimagnetic wave vector that provides the limit for pairing, because that is the singlet triplet excitation gap within the charge stripes. The magnetic excitations in a variety of cuprates have a very similar behavior. There's an upward dispersion at high energy. Some downward dispersion tends to show up at lower energy. I'll call this midpoint of the hourglass E cross. It's got an energy scale of about 4 times J, where J can vary among these systems. It's interesting to compare this among the absolute values of E cross for different cuprates as a function of doping. So here are results for lanthanum strontium copper oxide in green, yttrium barium copper oxide in blue, and mercury 1201 and bismuth 2212. If we follow this trend and compare with measures of coherent gap scale and antinodal gap scale and bismuth 2212, we find that they all fall below E cross, consistent with this being an upper limit for the pairing scale. And the fact that it's a maximum in the underdoped region is consistent with the fact that this is where the highest range of superconducting fluctuations occurs in cuprates. So with that, I get to my conclusion. The spin gap on the charge stripe sets the limit on the pairing scale in cuprates. The spin stripes are important for defining the charge stripes, but spin order on the spin stripes gets in the way of uniform superconductivity. The spin gap on the spin stripes is what limits the coherent gap scale. So effectively, we have a spatially modulated pairing gap in the system. And so with that, I will stop and thank you for your attention.
Thank you for nice talk. Now time for questions, and I suggest you come here so that the speaker can see you. Huh? Speaker can just here.
Hey, John, hi from Rome, or for Scotty. Question for you. So it seems to me like you would need fairly extensive correlation along the stripes for this mechanism to work. How long do you think the stripes would actually have to be for this, in terms of unit cells?
So the spin-spin correlation in low-D systems like this tends to be relatively short, on the order of 6 lattice spacings. So to develop the correlations, the stripes don't have to be long, but they're, I think the experimental measurements are certainly compatible with stripes being long enough to develop such correlations.
Okay, thanks.
If anybody further questions, you know, maybe in online, any questions? So far, I don't see. Okay, then again we thank speaker, and we close this session.
Right, okay, welcome back. So it's my great honor to chair the last session. My name is Ke-Jin Zhou from Conradson. So we have the first speaker, Francesco Stellato. So you have 20 minutes to speak and 5 minutes for the question. Please go ahead.
Okay, so thank you very much, and really let me thank the organizer for giving me the opportunity of being here in this conference, in particular Marcelli and Professor Bianconi. And I'm sorry that my talk is going to be a bit off topic, in the sense that I've heard describing wonderful scientific experiments, while this talk is going to be about a source that might allow you in the future to perform these experiments. And the reason for me being here is to collect ideas and questions and criticism from the community on things that can be done or that will be able to do in the next few years. And I'm Francesco Stellato, but I'm talking on behalf of the Eupraxia Spark Lab collaboration, which is the one leading the conceptual design report of this machine. So let me get does this work? Apparently not. Okay, I'll do. The laser, yes. Okay, yeah, okay, sorry. So what is the idea about? It's about high brilliance X-ray sources. No, everybody knows in this here that we started from X-ray tubes, and then we had first, second, third generation facilities, and then which are the so-called synchrotrons or storage rings, and then we have the free electron lasers, which are typically known as fourth generation facility. What is the point? My example is about structural biology, but really the same applies to solid state physics. So the more brilliant the sources became with time, the more complex and more interesting were the systems that people could study. So limiting ourselves to structural biology, we started from radiography of a hand in the late 19th century, and we ended up with DNA double helix and very complex structures that have been solved in the latest era. The source I'm going to talk about is the so-called free electron laser. So just to get everybody on the same page, what are the ways in which people typically generate X-rays? They can have bending magnets, that means having particles following not linear trajectories, accelerated trajectories. And then they have straight so-called insertion device, which are wigglers or undulators, in which the particles, which are typically electrons or can be positrons, go through a sinusoidal trajectory. Or we can have the free electron lasers. And what is the difference? How is the radiation generated in free electron lasers? In free electron lasers, there is the interaction between the particle beam and the photon beam generated by the particle themselves. That means that one has an undulator in which electrons are going. These electrons are emitting photons, as in a standard undulator, but then these photons are interacting not only with the other undulators, but also to the photons emitted previously in the previous bunches. And if things are done properly, then there is a coherent emission of radiation. That means one gets very bright pulses and very short pulses. So what are the main differences between free electron lasers and synchrotrons? This is a plot that shows the brilliance, the peak brilliance, to be honest. That means the number of photons emitted per unit of time in the end in a given bandwidth at synchrotrons and free electron lasers. So you can see synchrotrons have typically continuous spectra, while FELs, which are these ones, have point spectra. But we'll comment on this in a while. So what we can notice is that FELs have higher brilliance with respect to synchrotrons, that they emit shorter pulses, and they also have typically higher degree of coherence. They are both tunable in terms of wavelength polarization, but for what concerns the wavelength, maybe we have to discuss some details afterwards. So the main point is that if we just think about the average brilliance, that is the average number of photons that we have in the not in the unit, in a large unit of time, then FELs and synchrotrons have pretty much the same behavior. So, okay, I don't have the scale here, but it's about, I don't know, 10 to the 12, 10 to the 13 photons per second. But the difference is that at the synchrotron, these photons are emitted almost continuously or with very long pulse, where long means some picoseconds. While at FELs, they are sent in very short femtosecond pulses. That means that in principle, we have a new source, and we can also think about different experiments to perform with this source. Okay, since you are sitting here, let's talk about this Eupraxia project. So, as everybody knows, particle accelerators are used in physics to study fundamental physics, particle physics, but also to serve as photon sources, as we discussed in the last few minutes. And as I described you, they typically exploit the accelerated motions of particles to generate photon beams. But the point is that one way to generate more brilliant beams is to build larger machines. If you think about particle physics, you can think about LHC at CERN. If you think about photon science, you can think about the LCLS, for example, which is an accelerator that is 3 kilometers long, or the European XFEL in Hamburg, or also the synchrotrons, which are quite large machines. So, of course, there is a technological and scientific interest in building more and more compact accelerators that need different acceleration scheme. Eupraxia is an European project that has the goal of designing a plasma accelerator facility. What does plasma acceleration mean? In plasma acceleration, in classical acceleration, we exploit, as we said, undulators to accelerate the beam, or electromagnets to accelerate the beam, the electron beam. In plasma accelerators, instead, what people do is that they produce a bubble in a gas. This bubble is essentially a plasma, so there is separation between electrons and nuclei. And if you send a particle beam inside the bubble in a proper way, then this electron beam, this electron bunch, will experience a very strong acceleration in the wake field of this plasma. And then the acceleration power of these devices can be 10 or even 100, maybe 1,000 order of magnitude larger than in classical acceleration schemes. So it means, okay, that's another plot showing the same story. So it means that in principle, one might be able to produce particle accelerators to be used for high energy physics or for photon science that are 10, 100 or 1,000 times more compact than classical or standard present sources. So does this work? Yeah, the short answer is yes, because people are already working on this in several places around the world, but also here in Frascati. In particular, the Spark Club group just showed that this plasma acceleration scheme can actually work and can produce electron beams of good enough quality to feed a free electron laser source, but in the infrared. So the goal of the Eupraxia is to move from the infrared region towards shorter wavelengths. Okay, so there is a project about building, so we are sitting somewhere here, I think this is the Tuschek auditorium where we are, and this is the rendering showing the building hosting this accelerator where it should be in the next few years. So if you just go for a walk in this area, you might see where the things would be. Let's go a bit more into the science. What is, I said, okay, synchrotron and free electron laser have different beam properties. So what can we do? Well, we can do a lot of things. The main point is that in principle, since free electron laser are pulsed sources, one can have one pulse and one measurement. The point is that typically the FEL pulses are so bright that whatever sample you put under them is destroyed or damaged. So it means that one has to be able to collect a detectable signal before the sample is destroyed. And this technique has been shown to work. The first pilot experiment was performed by Chapman and co-worker at Flash in Hamburg in 2005, if I recall correctly. And since then, I mean, many experiments have shown that this can work. This principle is generally known as diffraction before distraction, or in general, signal before distraction, diffraction, if you think about whatever signal. And I have a short movie showing how it works. So this is an imaging experiment, for example, but the idea is quite simple. You have one sample, you put it under the beam, then you shot your sample with the free electron laser and acquire some signal. In this case, it's a diffraction pattern. It can be whatever. What is this whatever? So where are, in which energy range or wavelength range are FEL sources working? Well, there are FELs working in the hard X-ray regime, FELs working in the soft X-rays or VUV regime, and the Eupraxia Spark Lab should work in the water window, which is the region between carbon and oxygen K-edge, so between 2 and 4 nanometers. So that's important because, for example, if you have an experiment, some of the experiments that I've seen might benefit from having radiation in this specific range, please, let's discuss about that. There is already a conceptual design report out describing this machine. In principle, we are thinking about having a single beamline, but I will give you some more details later. And this is the time scale of the project. Of course, I mean, things got a bit more difficult because of coronavirus and stuff like that. But the idea is to have the first FEL beam in 2028 or something like that. So just to provide you with some figures, the wavelength is going to be about between 3 and 4 nanometers, more than 10 to the 11 photons per pulses, with pulse duration of 50 femtoseconds, and the repetition rate that was initially thought to be 10 Hertz, but actually might be even higher, or like 100 Hertz. Okay. Science. What can people do? Well, for example, I mean, in this range, you can perform coherent imaging experiments, but you can also perform X-ray absorption spectroscopy experiment or emission experiments in Niemann Raman. Why that? Because, as I told you, the energy of the FEL pulse is given, but in these acceleration schemes, it jitters a bit between one pulse and the next one. So it means that if one acquires for a sufficiently long time, the person might be able to scan over, for example, an absorption edge. And the samples, okay, can be biological samples, but can also be metals, semi-metals, semiconductors. In general, whatever experiment would benefit from a very high intensity and a very high time resolution, given by the short time duration of the pulses, would benefit from performing experiment in FEL. So for Eupraxia, we are thinking of designing a multi-purpose experimental chamber in order to be able to perform, okay, diffraction, but also absorption or emission experiments and time of flight measurements, so measuring particles emitted during the FEL exposure, and to perform pump probe experiments where the pump can be a laser source or the pump can be the FEL pulse itself by using a so-called split and delay element, in which you have an FEL pulse that you split into two pulses with a given delay. So you first hit your sample with the pump pulse and then you probe it with the remaining part of the pulse. Okay. Maybe I will go very fast about coherent imaging. Coherent imaging is particularly interesting because it can provide information on samples, and it's particularly interesting because the FEL is working in the so-called water window. As I was saying before, I mean, it's the region, the energy region between carbon and oxygen K-edge. Why is it particularly interesting for biological samples? Because since in this region, water is essentially transparent and biological samples, here I have a picture of coronavirus, but that would be a bit too small for this kind of experiments. But for example, you can have a cell or a nucleus or an organelle, a bacterium, and that could be actually provide a very good signal. In this region, I mean, the water surrounding the sample would be transparent, while the sample would scatter a lot. And so one can perform, as it has already been done, coherent imaging of biological samples in their living native state. Another interesting point is that in the energy region of Eupraxia, one can access L and M edges of heavy atoms and also K edges of light atoms. So X-ray absorption and or emission experiments can be performed. Another point is that one can also perform photofragmentation experiments in which you have an FEL pulse breaking a molecule or impinging on a molecule, and then you collect the fragment, and from the fragments, the way the fragments reach the detector, you can understand what was the electronic state of the sample before eating it. And so also this is a quite active field of science. As I said, I mean, in principle, the design started with one beamline that we call aqua. It's the Italian word for water. That's because it lies in the water window. But there is also space and technical possibilities of having another beamline, which we will call aria, which is the Italian word for air, and the reason will be clear in a moment, to produce photons, still FEL photons, in a different energy range. This beamline would be seeded. It means that the energy of the FEL pulse, the wavelength of the FEL pulse will be defined in a wavelength range between 50 and 180 to 100 nanometers, continuously tunable, so it's also good for spectroscopy. And it can have tunable polarization, and it's a bit easier to operate from the machine point of view. That's one of the reasons why we would like to have it. It's called aria because in this energy range, the main samples that can be studied are samples in the gas phase, so aerosols, molecules and gases, but also proteins in the gas phase. And so that's aria, so air, for example. That's techniques, still photoemission spectroscopy. One here excites the samples with the FEL beam and then looks at the photons emitted by Raman spectroscopy, or again, photofragmentation of molecules and time-of-flight spectroscopies. So, just to conclude, what is the point? The point is that of this project and of this talk and of me being here, what we wanted to design a compact FEL source to perform ultra-fast, possibly time-resolved studies. It can also be used for static studies, but typically the question when I look at the project, I forgot to mention that within the Praxia project there will be two plasma-based FEL accelerators. One will be here, and that's known, and the other one will be somewhere else in Europe, and that is I cannot comment on that. I am therefore putting together a future user community, and that it's important to note that the India is to collect the information and the potential users to the rest. This is the reason why the resources need to be ready. But the time is now to tailor the first membership to aspects that mental needs, because I don't know, I said that we will work between 3 and 4 in China. But the machine here would be more flexible, would have different sources. For example, there will be also a high-power laser for high-power lasers. Which is never everything thanks for the
So we don't want to duplicate what is existing. We are just looking for new ideas because from the ground of this plasma accelerator, there will be new opportunities, even on the
If not, let's send to the So our next speaker is Oriana Mikhailova from University of Hamburg. So you have 20 minutes to speak and 5 minutes for questions. Please go ahead.
First of all, thank you to the organizers for providing these results and numbers. Let me acknowledge the contribution of my supporters. With Jean Carlo, Joachim, Roberto, we have developed a project on pipeline calcified minerals. Mainly and So, here to go with the superstripes. I will try to explain this by introducing to you the structure and chemistry of mineral supergroup and key considers like mineral stripes. Then I will present which is called Buchner. High temperature Raman spectroscopy, and by high temperature I really mean hot, so above room temperature. Reminder about the selection rules and the resonance conditions, and the results from density control theory calculation of the correlation of the minerals. After that, I will discuss about the composition and activation implications. Well, every self-respected physicist does not consider geology as a science. And I have to admit that was also me back then when I was graduate physicist, I started but with time, I realized that I was different from geology, but having arrived to a great extent by studying the chemistry, structure, properties, actually learn how to synthesize better crystals and how to synthesize new functional materials. For example, the famous perovskite structure intercalated with metal oxide is practically the classical superstructure. Doing the intercalated one-dimensional samples, yes, we have plenty of such minerals, and these can be considered to two major groups, silicates and antiballs. And if you look at the structure of antiballs, these are natural stripes, stable in a wide temperature and pressure range. So up to 1,400 So let's have a closer look at the structure of antiballs. Why is it so stable and such a The major building unit oxygen, metal oxygen. So in this octahedral strips, we have predominantly magnesium and divalent ions. And then the I-beams are linked to each other via the so-called dication, where we can have also different chemical elements and form channels which can be empty or filled with sodium or potassium. A very important feature of antibodies is that hydrogen anionic site, and that means that very important for the hydrogen. So hydrogen can be released from antibodies and very destroying the structure if there is ion divalent ion in the structure. Because then all the strength in oxygen chemistry correspondingly with divalent ion and trivalent ion. So while we're studying the method process in antibodies, so the Raman heat, which is related with the Earth's structure, the heat will disappear at a certain temperature, and after that, cooling down to room temperature, completely recovers. And the same is happening with the Raman signals, which are related with vibrations of ion 2 plus oxygen. So what's going on? Apparently, we have a temperature where we have the so-called reversible filtration. In this case, we have a dual of the electrons and pure combination of hydrogen, but they still remain inside the principal ball. And that means that we have charge carriers at this temperature. And only when we increase temperature, then we have ejection of hydrogen and electrons from the principal, and then we have irreversible reduction. So that the future in order to understand better this phenomenon, we decided to study more independent minerals, first of all because it is trivalent ions. Also, we decided to do experiments in air and nitrogen in order to check the role of external oxygen. And finally, because of different reasons, we simply were searching for such phase transition. We decided to do the Raman experiment orientation when the octahedral strips were perpendicular to the polarization of the laser beam, when the strips were parallel to the polarization of the laser. And then we observed small feedback. In this horizontal strip at a certain temperature, not only the orange peak disappeared, but all peaks which are related with the physical vibration. And now we're thinking to think, okay, finally, we've done the antibody, we destroyed the structure, but orientation, we have our perfect subject. Let me remind you that interaction process. So we have a photon, a phonon, and electron. And that means that when we consider the selection rules, we should take into account the symmetry of the irreversible reproducible representations of the phonon, but also of the electron, so the symmetry of the electron orbital. And then this process is chemistry specific. So when we are talking about the enhancement of a certain phonon mode, we are telling that there is electron transition associated with this vibrational unit social. In ionic crystals, resonance lines occurs where the solids have interactions that will get an enhancement of and in the case of centrosymmetrical crystals, that means is exactly so this enhancement is related with vibrations and oxygen octahedral. But this is also direction dependent. So we observe direction dependent appearance of resonant crown spectroscopy, and that means that the form polarized get directly around the C-axis. The vertical orientation, the laser, and that's why we do not detect. The activation temperature for this particular amplifier was around 700 K, which corresponds to 0.06, and it is consistent with this temperature. Boron conductivity related with boron copper should dominate because it is above the half of the double thing. So in order to check our hypothesis, because it was still interpretation of the experimental on the electrodes, Green arrived and also two other models in which iron was only in the octahedral strips, or iron was only here. In the octahedral strips we had only magnesium. So what the results tell us? First of all, indeed, we do have energy response to direct transmission, although we have the positive comparison with the experiment, it is similar value as with experiment. Second, it is entirely related with iron, which is on the octahedral. And something more, we will consider the projected orbitals, then we can see the result of the response formed by the relation between this Y orbital iron and its orbital oxygen, while the bottom of the conduction band is formed by the Y square iron and its oxygen, the key points here in these planes, and that means that parallel to the C-axis, exactly what we observed in our experiment. So then, what's going on if we put our sample in nitrogen? Well, again, we have formation of corals in nitrogen, irreversible process, and we have formation of nitrogen. And in air, if we go down in air, vertically displaced. Here, by analysis of the intensity related with the vibrations, the temperature range in which charge carriers in focus form. And the distortion, if we capture distortion in the shear system rings and rings of those rings, they should be influenced. So those rings, the geometry of those rings to accommodate the small size of the headroom where we have effectively 3 valentines. So this can be followed by the temperature dependence of the wave number of the corresponding mode. And indeed, the minimum here means that the local potential is flattened. So that means that indeed we have a structure of tiny points in the experiment with that geometry. In the horizontal geometry, this minimum is actually at different temperature. And that means that simply the anisotropic electronics that develop the cost of borons leads to anisotropic temperature gradient in the crystal. And here in this range, we can actually this temperature range is somehow proportional to the anisotropic vector curve, which practically we know the onset and the completion of electron utilization itself, it should be also related with the magnitude of the average dipole. So we can estimate by this temperature range and this curve immediately influence the formation of photon. And first we went back to Riebertite in order to see the effect of coexistence of trivalent and divalent time. So yes, here again we have formation of photons vertical in nitrogen atmosphere. It is exactly the same as in Buchner, parallel the reduce prime and double prime without, however, changing this temperature. And in independent study, yeah, I should mention that the verticalized nitrogen diffuse stronger in the direction of this perpendicular to the strip. How about cells? Again, we have formation of photon, however, when we the spectrum initially didn't prepare. It prepared only after approximately 2 hours, which means that the presence of the photons somehow slowed down the relocalization that gives us a clue the temperatures at which we can stabilize this funny metastable state. And acations reduce both T prime and T double prime, but they also reduce the temperature range in which we observe, so which is defined by those two temperatures, which means that somehow it reduces the magnitude of the photon dipole. Okay, so that's good. If we have ferrous or ferrous-ferri amphibole, we should have porons, normal. But how about if iron is actually a minor element, if we have predominantly magnesium? And this is the case of actinolite. Well, again, we have formation of porons by observing this resonance Raman enhancement. Of course, we don't have a complete change in the selection rules because now these are defects. And again, a very interesting observation is that when we cool down, so we get these two spectra in vertical orientation and in the horizontal orientation. And after a certain time, actually that was after the weekend, so after 3 days, you see that we have a change between the intensity ratio of the resonance Raman scattering and the strongest peak of non-resonance Raman scattering. That means that even at room temperature, something is moving. So maybe boron tunneling, I don't know. So for now, the mechanism is unclear, but definitely something is moving. And in order to understand why this is happening, we assume that this is because there is a chemical gradient between the bulk of the crystal and the periphery of the crystal. In order to check this, we took one sample which was heated even up to 1300 Kelvin, and then we cut the sample in half in order to reach the bulk, and after that we measured the spectra in the bulk and in the periphery. So you see, there is clearly a different intensity ratio between the resonance Raman scattering and the strongest ring mode. And as you can see here, the resonance Raman signal is stronger in this direction than in that direction, indicating that even at room temperature, we have a motion of porons, which is preferably along this direction, along the octahedral strips. So, implications. Actually, we studied all these because there is an interesting, very well-known phenomenon in geophysics that close to the subduction zone, so this is when we have a plate tectonics. That's why we have earthquakes, volcanic activity, all that's funny stuff on a macro scale. Then people measured here conductivity. So it is enormously high conductivity. It is actually higher than the conductivity of silicon wafers at room temperature. And besides, it is anisotropic.
So there are two existing models to explain this. First, we have release of water from hydrous minerals, and then we have ionic conductivity of those fluids. So those fluids, they contain ions, so ions move around the big crystals, so we have ionic conductivity. But it turned out it is not enough to explain the current, the measured via geophysical methods conductivity, neither to explain the anisotropy in this conductivity. So there is an alternative model. People measured simply the via electrical measurements different rocks or containing amphiboles with different amount of iron, and according to the activation temperature based on kinetic experiments, it should correspond to indeed porons. So porons were assumed but never measured directly, as we demonstrate from our polarized Raman experiments. And finally, what are the implications in material physics? Well, we do have geostripes, in which we have temperature-activated anisotropic boron conductivity in this direction and hydrogen diffusion in the perpendicular direction. That's quite funny. And we have a tool via crystal chemistry to control the activation temperature and the temperature range in which those phenomena happen. So many thanks for your attention.
Thanks very much for the very refreshing topic. Yeah. So now the session is open for questions and remarks. Please.
It's quite different from high temperature superconductors. Yes. Absolutely. Absolutely, you're absolutely right. And we have done Nussbaum spectroscopy on, actually we have done, wait a minute. No, I'm lost in my own, okay, good. So we have done Nussbaum spectroscopy on Rieberkeit. So Rieberkeit has been studied very, very in details. And what we observe by Raman spectroscopy is completely confirmed by Nussbaum spectroscopy. Actually, it's we have done also single crystal X-ray diffractions, infrared spectroscopy, so plenty of methods to characterize the samples. So, yeah, with great pleasure. Okay, thank you.
Actually, one more different question. Since the economy now is moving wider, one of the major issues is where to hide. So people seem very interested in getting and extract hydrogen in a safe way, just because they need solid and stable extremely high temperature rather than
Yes, you're absolutely right. So, and in particular, results about actinoide, which is iron poor, it turned out that the formation of porons actually activates the delocalization of all hydrogen there, no matter if it is attached to iron, magnesium, 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 or iron, iron, magnesium, as it should be, because there are different possibilities. And then the whole hydrogen actually is delocalized and can be somehow moved in the opposite direction if we apply temperature gradient or some kind of chemical gradient. So that's very important. So with the little efforts, actually, you activate the whole hydrogen there. And if you want, maybe you can put it back. So we're still thinking how really to interpret those results over there. So there are some issues also to be resolved, but indeed it's very interesting that poron formation can actually activate the delocalization of hydrogen and consequently its mobility. Yes.
Yes, please.
Question, I don't remember this one. Very interesting. I heard you talk about data how I think that this hydrogen
water can survive, but go down up to the core, up to the iron core almost. Which people said crazy because it's so hot down there and the water will evaporate. Then it will happen. So how was yours?
So water may survive not only because it is hot, but it is also high pressures. And that's why a lot of stuff may survive. But is it really true? Maybe Giancarlo. But definitely it is not pouring water. Yes, definitely it is not pouring water. And actually, nowadays we're talking about delivery of hydroxyl groups even, right? With these hydrous minerals. Sorry, couldn't. Is it bendy?
Band insulator.
Oh, yes, of course. It's a bent insulator at room temperature, but at high temperature, apparently it becomes semiconductive. Yes. Yeah, that's the cool point. That's the cool point. Sorry.
I feel really sorry to interrupt all the very nice conversation, but I think we need to move on. Thank you so much again for that very interesting talk. So our next speaker is Simone Bernardini. So you have 20 minutes to talk and 5 minutes for questions. So please go ahead.
Thank you. No, this is okay. Okay. So good evening, everybody. It's a real pleasure to be here presenting you our result about the laser-induced degradation of manganese oxide. So we speak again about mineralogy after amphiboles. And I wish to thank the organizer for this opportunity. And why it's so important to study these materials? Because as you can see here, they found a large number of applications over the millennia, from Paleolithic art, pottery, stained glass, dry batteries, and recently as a nanostructured material with very important chemical physical properties. And these properties strongly depend on the mineralogy, oxidation state, and coordination environment of manganese. And recently, we show that the Raman spectroscopy it's a powerful technique for determining the oxidation state of manganese and the coordination environment. As we can see in this figure, so we have manganese 2+, 3+, and 4+ in octahedral coordination, and the bands of manganese 2+, 5, 6, 7 in tetrahedral coordination. However, these compounds are blackish, and they easily absorb the photon energy, and this produces a strong heating and degradation of our sample. As you can see here, this figure shows the evolution of the spectrum of grutelite, that is a very important cathode material, increasing the laser power. And this is the structure of grutelite. And at 3D at around 2 milliwatt, we have a strong degradation of the sample. We can see that we have also the oxidation of manganese between 1 milliwatt and 2 milliwatt, and then a reduction and also a change of the structure to a spinel structure, and a reduction of manganese to manganese 2+, but now also in tetrahedral coordination. But now we have a new method to study the laser-induced redox processes that produced by the laser beam on the most common manganese oxide. And it's very interesting to note that we are now, we have the possibility to monitor the degradation of the material by using the same beam that produced the damage. Let's start with the first example, in which we will speak about the pyrolusite, that is a manganese oxide with a channel structure, in which all manganese occur in octahedral coordination and has 4+ cation. And in this structure, we have no cation in the channel. So here we can see the evolution of the spectrum increasing the laser power, and at around, so let's say above 6 milliwatt, we have a clear change in the spectrum, and this peak disappears, and we have this strong peak around 630. And when we decrease the laser power, we can easily recognize the spectrum of Hausmannite. So we have obtained a new minerals with a spinel structure. And it's also interesting to note that we have a reduction of manganese and also a change of the coordination environment. So the degradation of manganese oxide with a vacant channel site is a one-step process in which we have the irreversible transition from a channel to a spinel structure, the reduction of manganese from 4+ to 3 and 2+, and also a partial change of the coordination environment from octahedra to tetrahedra. But now we want also to study the effect of the channel cation on the degradation process. To do this, we are going to compare two compounds of the coronadite group. So the first one that is cryptomelaine, and the second one is hollandite, in which, so they share the same channel structure, but the only difference is the cation in the channel. So cryptomelaine has potassium, so a monovalent cation, and hollandite host barium, so a divalent cation. Let's start from cryptomelaine. So as we can see here, already at 3 milliwatt, this peak, this shoulder, around 580 disappear. And then when we decrease the laser power, we can again identify the spectrum of Hausmannite. So even if we have a channel, a cation inside the channel, we obtain again the transition to a spinel structure. But now we can again to see that we have a reduction of manganese, because this peak is related to manganese 3+, this one to manganese 4+, and this peak is related to manganese 2+, but now in tetrahedral coordination. So we know that between 0.5 milliwatt to 6.1, we have the reduction of manganese and the phase transition. And when we reduce the laser power, we can see that the process is not reversible. But now we want to understand, to study what happened here before. So if we study the ratio between this peak, that is the peak of manganese 4+, and this peak that is the peak of manganese 3+, we can see that this ratio increases. So we have a clear oxidation of manganese from 3+ to 4+. So we have, before the reduction and the phase transition, we have the oxidation of manganese, and the ejection of the cation from the channel, and then the reduction and the transition to the spinel structure. And it's very interesting to note that this happened already at around 50 micron. And moreover, this is just our second point. So probably this oxidation started even before, but we cannot to see this process because we have a limited number of filters. And now we want to compare this result with the result that we obtained from hollandite. So we have always the same structure, but we are changing the cation in the channel. So we have a divalent cation. And again, we obtain osmannite. So we have, again, the final product that is a compound with a spinel structure. But now this process, we can see that start at a higher laser power. And since now we have a divalent cation, we have also the bands of manganese 2+. So we can see that we have, again, a clear reduction of manganese. And again, we want to see what happened before. So if we plot the ratio between manganese 4, 3, and 2+, so we can see again that we have the oxidation of manganese. And also, of course, the ejection of barium from the structure. But now, if we plot also the ratio between manganese 4 and 3+, so we can see that this ratio decreases. This means that now we have the oxidation from manganese 2+ to 3+. And again, this process occurs already at around 50 micron watt. So we can say that the degradation of manganese oxide with a filler channel site is a two-step process. The first step involves the ejection of the cation from the channel and the oxidation of manganese. And now we know that we have the oxidation of the lower valence manganese cation. So if in our structure we have manganese 2+, so we will have the oxidation from 2 to 3+, otherwise from 3 to 4. And it's very interesting to note that the valence of the channel cation control this process of oxidation of manganese, and then the stability of the compounds under the laser beam. As we can see here, if we compare the behavior of hollandite and cryptomelaine, we can see that hollandite show a higher stability under the laser beam compared to cryptomelaine. And then we have the second step that involves the transition, the phase transition to the spinel structure and the irreversible reduction of manganese, and also a partial change of the coordination environment. And we have not time to discuss also about the degradation of manganese oxide with a layer structure, but they show the same behavior. So we have the first step that involves the oxidation of manganese and the ejection of the cation, and then the phase transition to the spinel structure and the reduction of manganese. Exactly the same behavior. So in conclusion, the stability of manganese oxide under the laser beam depends on the structural arrangement and the presence and type of the channel cation. And it's very interesting to note that redox reaction in manganese oxide with a filler channel site cannot be avoided. So the oxidation occurs even under a very low laser power, we stick around 50 micron watt, and a very short exposure time, few seconds. And the laser degradation process of manganese oxide is a two-step process in which we have, first of all, the ejection of the cation, of course, if it's present from the channel side, and the oxidation of manganese, and then the transition to the spinel structure with a reduction of manganese and also a partial change of the coordination environment. And the spinel structure of osmannite is the final degradation product during the irradiation, irrespective of the starting phase. So this work provided the analytical basis for proper use of Raman spectroscopy as a sensitive tool for monitoring redox processes during the operation also of manganese-based materials. And what's next? We want also to study the effect of time on the degradation process. And our preliminary data show that we have also the oxidation of manganese with the time. If we work at the same laser power, we can see that anyway we have the oxidation of manganese. And we want also to verify if the process of manganese oxidation, of course, before the phase transition, it's reversible or not. Thank you for your attention.
Thanks a lot for the very interesting talk. Now the session is open for questions. We have ample time, so just feel free. Raise your hand. May I just start with? So you mentioned about the manganese oxidation from the 3+ or 4+ to the 2+. I'm a bit confused that you showed in one of the Raman shift that seems that there are two different species of manganese 2+.
Yeah.
So can you comment on that?
You mean this?
Yes.
Yeah. Yeah. Yes. So we have this peak belong to manganese 4+ in octahedral coordination. This is the peak of manganese 2+ in tetrahedral coordination. So let's show you. Okay. So this, of course, they show a very similar wave number, no? But since the spectrum of Hausmann-Knight is very typical, we can easily identify manganese 2+ in tetrahedral coordination. Fortunately for us, this is the only compound just for this. Otherwise,
okay,
I understand the point.
Okay, so you have the
exactly.
basic tetraplan.
Exactly. Fortunately, the spectrum is typical. Okay. So we are lucky.
Thanks. And you look into this, let's say the material stability. I mean, I think broadly the material is from the actual application point of view. Is this more like towards fundamental understanding of the stability of the structure, or do you have any consideration in a let's say a violet environment that you want to understand better the material in terms of structure stability, or more this is more like for the fundamental understanding of the material?
No, I don't understand the question.
Sorry. So what I'm trying to ask is this topic is more to understand the basic property of the material, or are you interested in terms of the actual application?
So this work it's to find a way to properly study this material by Raman spectroscopy, which is the problem. That since they can easily undergo degradation processes, in literature we have a huge confusion. Okay, so sometimes you can find the same, so different spectra for the same material, which is the problem. That someone work not in the, so maybe with too much high laser power. Mm-hmm. So, and since we can also study the oxidation state of manganese, and to do this task by Raman spectroscopy, it's very interesting. Mm-hmm. Because it's accessible, sure. It's faster, yeah. No? And but the key is to work properly, because otherwise we can say, so you can just think that these compounds are very important also for environmental studies. So always we speak also about Mars, because they found manganese oxide on Mars. So now the question is, the data that we will have from Mars are correct or not? So we have Hausmann-Knight on Mars, or we are going to produce Hausmann-Knight on Mars. So this is the
interesting. Okay.
Yeah.
Claudia.
Why the surface of Mars is covered only by the fact that because they reaction of iron, and so on. And if you go into the device core in a practice, and you go below, you find Jerusalem. So Jerusalem is clearly the interaction of ice with the magnetic. And so why Jerusalem is on Mars? Because Mars was covered by ice. Okay? And now ice definitely is on Mars. So we explain this work. So now we understand that the model of ice on Mars it is true because we found on Earth only below the ice. And the question was why not to finally it's not only the ocean, and there are basically lower, and then we want to know if the prime reflection, which is much easier than X-ray, can actually understand what's going on the ocean or on the planet.
Oh, thank you so much for the very nice comment. Yeah, really enjoyed the conversation.
Thank you.
Okay, let's thank the speaker again. Yeah. So our next speaker is Katarzyna Dziedzic. I hope I did right. So you have 20 minutes and 5 minutes for questions. Please go ahead.
Yeah, thank you, Chairman, for introduction. Claudio, my surname is not the password. It has a meaning. The first part, Dziedzic, means inheritor, and the second part means little male cat. So it's easier to remember. And Katarzyna is really international name. So, and I'm coming from Kraków, from the Jagiellonian University, out of the Faculty of Physics, Astronomy, and Applied Computer Science. This is the long name of our faculty. From the part of the faculty that is Institute of Experimental Physics, Marian Smoluchowski Institute of Experimental Physics, in fact, and from the Department of Medical Physics that I didn't even wrote here. So my background is medical physics. I'm graduated from medical physics, and then I was doing PhD in biophysics. So I've been always interested in applying physics into biology or medical problems. And then I grew up and decided that really it's so much important to know the basics and fundamentals of physics. And I know it really deeply, having really interactive and interdisciplinary studies, talking to different people from different areas, how much important is to know the basics and sometimes to translate into different languages, I mean the different languages, but of the same science. Anyway, all of us are studying the same nature, and it's really a challenge, sometimes to talk each other. So today I'm going to show you about the power of Mös-Bauer spectroscopy. With Professor Michalova, we have already some short discussion about that, and I'm happy that Professor Michalova know about Mös-Bauer spectroscopy. I know that Professor Mazzoli as well know. But first, I would like to really thank the organizers for being here, for inviting me for that conference. That place is special for me. I know probably all of us have special association with that special place here in Frascati. I was here for the first time in 2005, and that time, the friend of mine, who is my collaborator, she was awarded in that conference. That time I was presenting the poster in the poster session about the, probably it was iron valence states in tissues studied by X-ray spectroscopy and Mös-Bauer. And then last time I was here in 2016, I was honored to be also awarded at that conference. And afterwards I had a long break, and this is my first time after 2016 to be for the conference abroad to Poland. I had a maternity leave, there was a COVID, and I'm really happy to be here. So I decided to give that short introduction. Excuse me, please, but it's almost the last talk today, and it's so nice, and we feel all like in a big family. So now about Missbauer. So let's go back further. Not 2005, but 1121, when Rudolf Ludwig Missbauer was born. He already died in 2011. He discovered the phenomenon that is called by his name in 1858, and it was done as his PhD thesis that was entitled Recoilless Neutral Fluorescence of Gamma Rays in Iridium, in fact. And afterwards, that made the further step to the other scientists that use Missbauer effect to prove the redshift of gamma radiation in the gravitational field. And afterwards, in 1961, he was already awarded with the Nobel Prize with Robert Hofstadter. So it is a very short story of Rudolf Ludwig Missbauer. And for anyone who has any association with Missbauer, or maybe for all of you, this is something that must be connected with the Missbauer. So this is absorption spectrum of iron that is typically studied in Missbauer spectroscopy, but not only iron. So some short introduction about Missbauer spectroscopy. The whole name is Missbauer spectroscopy is the recoil-free emission and absorption of gamma rays. So this is my favorite scheme that comes from the handbook of Missbauer spectroscopy written by Uli Gonser. And it shows how much recoil effect disturbs the resonance effect and the absorption of X-rays. So finally, when we have that guy that is on boats that are on a frozen lake, let's assume, we may observe that resonant absorption. So the clue is that Missbauer effect is we may only observe in bulk, in the frozen materials. So we cannot exploit the Missbauer effect on the substances that are kind of liquid, but somehow something that we may call liquids because we've been studying Missbauer in fact in gels, so it is possible. But that's for another talks. One very important factor from the perspective of Missbauer effect and this recoilless absorption is Lamb-Missbauer factor. On the other words, Debye-Waller factor is the same name of the same factor. And what does it mean? It measures, in fact, the probability of absorption, of this resonant absorption. And yes, the same, it measures the recoil-free fraction of the iron ions that had finally absorbed the X-ray. And it's also related to the vibrational properties of the crystal lattice. So here we have like the very first term that describes Lamb-Missbauer factor. X squared is the mean displacement of the nucleus. Lambda is, of course, the wavelength. And here, if we assume the model for the low temperature approximation, then we can easily see the F factor increases with decrease in recoil energy. So it depends specifically on the ion, the element that we would apply for the Missbauer effect. With decreasing temperature, so this is something that is totally dependent on us. So we may decrease temperature to make the absorption effect higher. And also it increases with increasing Debye temperature, but somehow it's already connected to the lattice that we are studying. So here is whole table, the pink happy of the Missbauer elements. The element that I'm studying is iron, mostly. And why? Because it appears in nature very, very often. And as said, I'm from the field of biophysics, that's why for me that element plays really crucial role. But we are not constrained only to iron. And here are some parameters of iron, in fact, of isotope, stable isotope 57. The natural abundance of that isotope is only 2% in nature. And it makes also challenging the Miss-Bauer effect in terms of the iron ions, especially if you are studying some biological structure when the iron concentrations, as whole, is really low. But we can cope with the problem. Gamma ray energy is 14 keV, so we say that it's gamma ray, but for the nuclear physicist, it's really very, very low energy gamma ray. So it mostly behaves like X-ray because in terms of the electromagnetic field, electromagnetic wave distribution, this is the area that covers both gamma and X-rays, of course. Natural line width is also some important parameters of the iron studies. Mean lifetime of the excited state that we are studying is 141 nanoseconds. It also implies further both challenges and on the other side some possibilities that we may use having that specific time, very short, but for studying some biological processes, it's the perfect time. And the recoil energy is enough to be used in the Miss-Bauer effect. That's what we're interested in. And what is the power? At the title by power, I meant the precision and the scale of Miss-Bauer spectroscopy and why it is so precise. So the source is put here. And it's some rover, let's call it rover. In Miss-Bauer spectroscopy, we call it drive. And that rover possesses that nuclei, that isotope, that in the decay produces that gamma rays that we're interested in. And also the percentage of this recoil and of this decay is not very high, what makes the next challenge. However, we can cope with that challenge. And what we make further? So that drive is being moved. And it's being moved, that's why we are using the Doppler effect to achieve slight changes in the relative energy. What does it mean, slight changes? Here is some short calculations. If we have velocity of 1 millimeters per second, it means that we are shifting the energy about 50 nanoelectronvolts. So itself, the energy is 14 kiloelectronvolts, and we are shifting that energy about such a value. That's why it's so much precise. For rest of you who are not convinced yet, I did some funny drawing yesterday. So the precision is as if we are considering the weight of 2 elephants. The elephant, that weight is around 6 tons. And this is if we would discuss if the weight differs of around 1.5 micrograms or 1.4 micrograms. This is that precision that we are getting using this relative movement of the source between the source and between the absorber. But what for? Such a precision. Because we are studying hyperfine interactions. And when I'm teaching students by hyperfine, I'm saying that it is so much precise. This is hyper precise method that is using hyper delicate interactions. Sometimes it helps the students to convince them. And these are the Miss-Bauer, very characteristic Miss-Bauer, 3 Miss-Bauer parameters: isomer shift, quadruple splitting, and magnetic splitting. And what is the source of those parameters? Here is the list, short list of the type of the interaction. So if you are considering isomer shift, this is interaction between electric moments, Coulombic force, and this is that interaction between nucleus and the electrons that penetrates the iron. So this is the shift, kind of that Robin yesterday was talking in terms of the NMR, something comparable. The second one is quadrupole splitting that senses the interaction between nuclear quadrupole moment and inhomogeneity of electric field. That inhomogeneity might be in terms of a single ion, and of course, also in terms of the lattice gradient, electric gradient. And this is that parameter that is sensitive on those interactions. And the third one is magnetic splitting or Zeeman splitting, that of course measures, if such exists, interactions between dipole magnetic moments and nuclear magnetic dipole interaction between nuclear magnetic dipole moment and magnetic field, either internal, if exists, or external, if we would apply it. And here are the list of the information from the chemical point of view. This is how the other master of Mössbauer spectroscopy says. This is Peter Güttlich, that made really brilliant lecture notes to Mössbauer spectroscopy. And on the courtesy of this lecture, I put some slides out of these notes. And they are really, really precious for anyone who would love to study more Mössbauer spectroscopy in more details. But what we observe in the Mössbauer spectrum, isomer shift, as Robin yesterday was telling, it is just shifting from the zero position. And quadrupole splitting, if we have quadrupole splitting, we observe a transition between the bottom and the excited state, and the excited state is being split into two states, and according to the selection rules, the transition might happen between that state and that state, and the lower is here and the higher is here in terms of the higher energies. And there is the third interaction, the magnetic splitting, and again we observe the splitting both of the ground state and of the excited state, and this is the most complex spectrum that we might observe in terms of the hyperfine interactions. And here is also something what makes Mössbauer spectroscopy somehow tempting, because here is a list of different iron valence states and the spin states. And each square tells that if we have isomer shift in some regime, that we may assume that the spin, both the valence and the spin state of iron, is like it's written in that field. But the problem is, if, for example, isomer shift is 0.2 or 0.3, so that's not enough indication to conclude what is really the final state, the final electronic state of ion. But it is also not a problem. Some applications, these are some applications that have been not published by Peter Güttlich. So he was doing some analysis of the banknotes. And that what is precious here to denote is, if we, in one sample, have iron in different electronic states, in one run, we are measuring all of the states of iron. We do not do somehow dedicate the system to measure precisely Fe2 plus low states or Fe2 plus high states. It's been measured at the same time. So we have the indication of whole iron balance, of whole iron and electronic balance and spin states in one run. So here you may see the difference between $1 and 50 euros. And the other curiosity made that Peter Güttlich studied that iron, I don't know which crystal he was studying, is high spin Fe3 plus, or of course spinach. The story of spinach is well known. Probably all of you already know that it's not true that the concentration is iron is that high. because someone made mistake and shifted the comma in the value. But anyway, spinach is healthy because of vitamin A and C. So I encourage you to still to eat, have in your diary spinach. Absolutely. So it was mostly done by curiosity. But now the opportunity. Claudio and Simone had a discussion about magnesium and some mineral that was supposed to be on Mars. And what is the name of this mineral? Jarosite, sorry. And the other was also, so jarosite, mandarin planum jarosite. We are talking about the same, not the same, because that one doesn't possess, maybe X is manganese. Yes? However, on this rover opportunity that landed in January 2004 on Mars, there was installed Mössbauer spectrometer. So it was, yeah, detector was made in Poland. The detector was made in Poland, that's true. And it was also the confirmation that water is or was on Mars, is still on Mars, because of the state of iron. The jarosite wouldn't have iron in that state as it has if on this path, the previous time, it wouldn't interact with water. Absolutely. It must have interact with water. So it was the next indication that water was or is on Mars. This is something to make you impression that Mössbauer spectroscopy is really widely used. Absolutely is widely used. But today I would like to talk about, in more details, about one of our latest discovery, I would say it, in such molecules. These are carboranes. I don't know if any of you have heard about such molecules, why they are important for us. They contain iron, but also boron. Boron is important for boron neutron capture therapy, and this is my other interest in my scientific field. For the boron neutron capture therapy, we need a boron carrier. So this is the therapy, radiation therapy that is used in oncology. And that boron carrier also consists of iron. That's why we were tempted to study it also with Mössbauer spectroscopy. So our collaborators from the not even university, Polish Academy of Science in Łódź, from the Department of Medicinal Chemistry are interested in those compounds from the point of view of BNCT therapy. And we decided to study those two different molecules. The difference is, here is the zoom-in picture. In both of the cases, iron ions are coordinated by two pairs of carbon. Carbon are black, and two sets of three boron atoms. Boron atoms are the green one. And the main difference is that the second compound is coordinated by this oxime ligand. And that oxime ligand made that complex really interested. So that friend of mine, our collaborator, made the DFT calculations of that molecules. And we did Mössbauer spectroscopy. So these are typical Mössbauer spectra, as if they look, but it's not typical what they consist of. So our group from Łódź was expecting that in all of the cases, we would have only one doublet. But it turned out that in the second compound, that one that is combined with this oxime group, we have some more complex spectrum. Yes, 5 minutes, okay. More complex spectrum. And here are our further studies and simulations. So I'm showing you some precise and detailed analysis, but let's assume it in a few words. In each configurations, iron ions experiences slightly different electric fields. That's why we might conclude, surprisingly, that the low spin state of iron is in both cases, but in the second one, we have also the low spin of iron 2 plus. This was something what was really surprising. And the strong reduction of the quadrupole splitting in the second compounds versus one is indicative on the change of the iron electron strains from paramagnetic, of course, to diamagnetic. So it's just set in the other one. And by comparing the experimental and simulated Miss-Bauer spectra, we were studying broadening of the absorption lines. That's what I was asking to Professor Michalova, because by examining broadening of the line, we may assume something about the vibrational states, about movement of the iron ions. That's why it's so much important. And we were able to calculate the frequency of the rotation at each temperature. Each temperature means it was between 300 kelvins and 70 kelvins, because this was the lowest temperature we were able to measure. And what is more interesting, that joining that oxime group softens iron bonding, not strengthens, but softens the iron bonding, as seen from the decrease of the recoil less free fraction. So like the deepest of the absorption spectrum. And what does it mean? That joining that oxime group doesn't block rotation, but in contrast lowers the rotation energy barrier. And it was really interesting. So it was like fundamental physics and chemistry, and now it would be good to imply it in designing these boron carriers in future. And these are some selected examples of other studies we were performing using Miss-Bauer spectroscopy. Those two are in a cooperation with the chemists from the university, and we are studying spin crossover phenomenon in metallo-organic different compounds. We were studying also mobility, and we discovered somehow the frictionless mobility in nanoscale. It was in these gel substances. And here is the whole list, but I would like to say some conclusions. Miss-Bauer, yes, enables, of course, microscopic insights and enables really precise local electronic state studies of iron ions, but not only. So we are constrained to the iron being constrained by the source of the X-rays that we have. That's the point. And it may absolutely play a role of extremely sensitive probe. And we may monitor absolutely the dynamic properties of the different molecules and also of complex system. What does it mean, complex system? This is zebra finches, a bird. I don't know if any of you have seen or maybe have in your cages at home that bird. And we are interested in studying the erythrocytes of the zebra finches. But why? Because they still possess nucleus. But why? Because they are traveling birds. And they are really extremely interesting objects from the evolutionary point of view. So these are the studies that we are performing with evolutionary biologists. And this is the first spectrum we obtained 2 weeks ago using external magnetic field. And here we have a distribution of magnetic different fields studied in fact in hemoglobin. And we must still analyze those spectra. I show it for the first time. Really, it was done 2 weeks ago. And I was talking to Robin today, and he asked me, okay, so what are you doing here on the Superstripe conference, doing such a thing? And Professor Berconi came and told us, okay, but look, here are the stripes. Yes, here are the stripes. But it's a kind of joke, because these are really complex systems. But I need to know more, and I need to understand more to be able to say something about the superstripes in the biological system, because I need more discussion with Professor Bianconi, because absolutely that exists. And we've done all of those experiments with that equipment. For that external magnetic field, we use superconducting low temperature magnet. And I really ask you to produce the material for high temperature superconducting magnet. It would ace our life, save time, save money so much. So please keep going. And this is our team. So far, at the moment, this is my supervisor, Professor Stanek, Dr. Piotr Folnar, and our future Agata Grabska, who is a bachelor student, and she's not afraid of hyperfied interactions. So that's a good perspective for her, so, and for me as well. Thank you for your attention. Dziękuję bardzo.
Thank you so much for the fascinating talk. Now the session is open for questions and remarks.
So thank you very much for a nice talk. Your enthusiasm is contagious, and I appreciated your commitment to explaining things. So maybe my question is very basic, but maybe you have some intuitive explanation of why across the periodic table there are elements that are most power active and elements that are most power inactive. I couldn't find any pattern. So you showed this table where you highlighted the elements that are active and that are, maybe you have a pictorial or very simplified explanation.
Yes, so I think that I put here, oh yeah, one formula here. Everything is about this F factor, the probability of existing of absorption of this resonance absorption. So it depends mostly on this ER. So this is recoil energy that simply depends on the mass, on the ion. And also about the Debye temperature. So in fact, these are those constants that we might select, but also we have to apply proper energy like the one that is being absorbed. So it's like a game between that is what is emitting and what is absorbing. If we would possess such a nucleus, radiative nucleus, that would produce proper electromagnetic field that would be absorbed by the complex that itself possesses those features, that somehow we can select those pink elements, those pink elements somewhere over here.
Yeah.
So this is the game between the emission and the absorption and this F factor. So yeah, we can cope with the F factor, as I told you, that it's dependent on us only if we are talking about the temperature. That's why all of those fancy systems are employed also with the cryostats. So the typical temperature for us, the lowest is liquid nitrogen, but for that, with the magnet, because we had to cool with the liquid helium, that's why we're also measuring in the liquid helium at the same time, because this Jenny's spectrum, Jenny's magnet and Jenny's cryostat are somehow connected. That's why cooling down the magnet, we have the opportunity to lower the temperature down to liquid helium, and even lower if we are pumping. So we obtain 2 kelvins.
Dziękuję bardzo.
Proszę bardzo. Bardzo dziękuję.
Okay, for the interest of time, I propose to move on to the last talk of the session, and let's thank the speaker again for the very interesting talk. So the last talk of the today's session is Luca Tomarchio, and you have 30 minutes and 2 minutes for questions. Please go ahead.
Thank you, Chairman, for the nice introduction, and I would like to thank the organizer for inviting me here. I will break the refreshing session because I will talk again about high temperature superconductors, but at least they're not cuprates, it's nickelates. I'm Luca Tomarchio. I'm a PhD student at the Sapienza University of Rome under the supervision of Professor Stefano Lupi, and I will talk about a case study for the optical identification of the superconducting gap in the optimal doped nickelate, that is the superconductor. So a few people have already talked about nickelates in this during this day, and I will just give you a fresh, rapid explanation about nickelates. Of course, why we study nickelates. Because nickelates are similar to cuprates, and actually we expect them to be even simpler, and therefore by studying them maybe we can understand something better about cuprates. But actually nickelates are interesting also from different point of view and might also be more complex than cuprates themselves. So we start with a rarity element, nickel and oxygen, of course, and through autoprotective reduction we transform the peroxide structure to an infinite layer structure that is similar to cuprates in this case. And of course, we might expect also superconductive state that has been discovered only in 2019. And we expect to be similar to cuprates in terms of the isostructure, of course, but we find no superconductivity in the bulk. Only in thin films, actually, we can find superconductive features. And also we have many more differences, like we lack magnetic order. At least some new experiments have found traces of magnetic order, but it's absent in general with respect to cuprates. And the metal-insulator transition is also missing from the phase diagram. And nickelates are bad metals, so weak insulators across the phase diagram. So we have this kind of electrodynamical difference with respect to cuprates. Superconductivity has been found, of course, in thin layers, 10 nanometers deposited over STO substrate with a critical temperatures of up to 30 Kelvin. And the phase diagram here, represented on the right, shows how the system is actually a weak insulator when it is underdoped, overdoped at low temperatures, then it becomes metallic at high temperatures. And all measurements actually suggest the presence of a two-band model descriptions, the sync of change of all measurements themselves. And there are some things that are still unknown for this kind of system. For instance, how the interfacial effects actually contribute to the superconductive state, the contribution of 4F states coming from neodymium in this case, and also the effects coming from the lattice strains of the STO substrate. Indeed, this material is superconducting when deposited only on STO, and still we lack some information about this kind of effect, the superconducting state. Moreover, there are problems in terms of the production of this system. It's very hard actually to grow 10 nanometer thickness of an optimal doped nickelate over STO. And indeed, there is no warranty on the accuracy of the doping level. And the intercalating hydrogen during the reduction may give possible problems in terms of the resistivity and also on the whole measurements absolute values. Indeed, as you can see, by changing the doping, we can get different, very different values with respect to the resistivity of the system. So a direct comparison, for instance, between two materials might also be difficult in this case. So say this, let's go now and try to analyze the superconductive features. In particular, London penetration depth suggests, in terms of the symmetry of the superconductive, pairing both S wave and D wave, so there is still a bit of debate about this stuff. And also, tunnel spectroscopy reveals actually the measurements of two gaps, a D wave gap, that is this one, the V1, and also a S wave gap in this case. So still some debate, it's a bit debatable what is the pairing symmetry for this state. Optical spectroscopy measurements actually are lacking, actually now, for a problem that I will show you later, actually, because it's very difficult to measure the low energy optical spectroscopy of these systems. But the study of optical spectroscopy is useful to understand the pairing symmetry in superconductors. So it might be important to present some data about this topic. This is the scheme for the measurements. We send light on the system, that is film over substrate, measure the light reflected from the system. And indeed, since the penetration depth, the optical penetration depth is higher than the thickness of the film, we also have contribution coming from the substrate. Actually, these contributions are pretty strong. And this is the main problem for the study of the system. The experimental setup is, of course, Fourier transform infrared spectroscopy, and the source is a synchrotron source, and the measurements have been performed at the light beam line, and going from the terahertz region to the near infrared spectrum. And of course, we can study the superconducting gaps, but also the normal state of the system through optical spectroscopy. And indeed, the use of synchrotron radiation is useful because we might have, in this case, high intensity, brilliance, and reproducibility to investigate the low energy excitation, not just in superconductors, but also in other quantum materials. So the experimental setup is, of course, a Mazzoli interferometer, and the temperature is controlled by a helium-pulsed cryostat, with the in situ evaporation that permits us to evaporate gold over the system to have absolute measurements for the reflectance of the system. So the experiment is performed in this way. We send light, that is the synchrotron light. We measure in reflectance both the film over substrate, but also the bare substrate, because we need to take in mind the effect of the substrate over the total response of the system. We measure the reflected light through a bolometer detector. And in this way, we can actually perform relative reflectance measurements, meaning that we measure the reflected intensity, not the reflectance actually of the system, and as compared with another temperature like 20 Kelvin that is above the critical temperature. To perform absolute reflectance measurement, instead we need to evaporate gold over the system. In this case, we can actually have a correct reference, that is the gold, to have a measurement of the light intensity that we send of the material. And in this way, therefore, we compute the absolute reflectance in the system. So now let's go to the data. Here on the right, you see the two curves, the blue and the red ones, that are the reflectance, absolute reflectance of the STO and the film over STO at room temperature. As you can see, the red curve, that is the STO, shows the typical phonons of the strontium titanate, while instead the blue curve shows an absorption. I mean, the reflectance is dampening here due to the film absorptions, and then it goes up here at higher frequencies, since the STO is not reflecting anymore that much, and therefore the reflectance is a bit dominated by the film in this case. As you can see, the differences are small. Of course, we are comparing a 10 nanometer film over a strontium titanate that is highly responding in the low energy part. I mean, the phonons are pretty strong here. This is the main difficulty in studying the physical properties through optical spectroscopy of this kind of system. Indeed, you can try to fit this curve, the reflectance. First of all, you need to characterize completely the substrate, take in mind the indexes of refraction, both the real and imaginary part of the substrate, and then extract the conductivity of the film by supposing a model. In this case, we suppose the most simple model, that is a Drude plus a mid-infrared Lorentz oscillator. And of course, this is a very simplistic approach to study this kind of film that we suspect is even way more complicated than a single Drude Lorentz model in this case. However, if you look at the reflectance, you see that actually the system is just absorbing here, and then goes up, and the reflectance goes up again here. And therefore, actually the behavior of the reflectance is very smooth and very simple. And indeed, the use of an extended model, it's not possible because it's impossible actually to fit extract information from extended Drude model for this kind of system. And however, also, actually, the use of a single Drude model, in this case, to study the low energy response of the system is actually supported by the Hall measurements that predict high density of carriers for the systems, and by the parabolic bands predicted by the FT calculations. And actually, the bad metallicity of the systems also gives high resistivity, predicts a low conductivity. So we expect the scattering time to be low. And indeed, if we fit in the best way possible this data, we obtain a scattering time coming from the Drude that is very short, 14 femtoseconds, and we can actually compare it to the gap extracted by tunnel spectroscopy and realize actually that the system is in the dirt limit, in the normal state is in the dirt limit. This is a key information to study further, to understand further the superconducting nature through optical spectroscopy. And this is the conductivity that we extract, the real imaginary part, and the conductivity changes as a function of temperature, meaning that it increases at low temperatures, and the spectral weight is conserved since the mid-infrared band is dampening in this case. And this is in accordance with the resistivity measurements for the same sample. Of course, we can also compute other differences with respect to cuprates, and we realize actually that electrodynamically it is a bit different. If we use this phenomenological comparison for cuprates to understand instead how the nickelates is behaving by comparing the scattering time with the thermal energy of the critical temperature, we realize that this equality is not satisfied. Okay, so we are outside the limit of the behavior of the cuprates. Moreover, we can also have some other information by studying the mirror band, in particular by comparing the oscillator strength of the mirror band with the plasma frequency of the Drude band, and we realize actually that the system it's an intermediate correlated state, meaning that this result, the closer it is to 1, the less correlated is the system, and it appears to be higher with respect to cuprates, as nearly 0.4. So the major problem when studying the system at low temperatures is the substrate. The substrate, as you know, STO actually has the soft phonon that by lowering the temperature, it becomes stronger and stronger, it goes down to low frequencies, and indeed the reflectance goes up to 99%. Therefore, we need to characterize very precisely the substrate to understand what are the differences instead of on the film that we measure. We characterize very well the substrate. Actually, this is we can compare this to literature, and there are very small deviations up to maximum of 5%. And the solution, of course, to study the film is to use high signal-to-noise relative reflectance measurements performed through synchrotron radiation at Soleil. So these are the results, and stunningly, actually, we see some key differences with respect to the study of the bare substrate and the film over substrate. These are the absolute reflectances, and these, the most important, are the relative reflectance measurements. So the STO, indeed, the soft phonon, it can be seen by this behavior, while instead the nickelate shows similar but also different behavior. Therefore, we expect actually to be able to extract some information of the superconducting nature at low temperatures from these measurements. Indeed, we need to fit the relative reflectance data. Okay, how do we fit this? We know from the previous normal state analysis that the dirty limit, that material is in the dirty limit. Therefore, we might expect to use the Matisse-Bardin model to fit the superconducting conductivity of the system. Indeed, these are the equations of the Matisse-Bardin model, where delta is the superconducting gap, sigma C is the superconducting conductivity, and this is the conductivity of the normal state. The fitting process is performed through gradient descent algorithm. I'm not going to explain you too much the algorithm. You just follow the minimum chi-square and then extract the gap through the fitting of the relative reflectance, and this is the result. So this is the gap as extracted by optical spectroscopy. So below 30 Kelvin, we have an activation of the, an opening of the gap as measured that goes up to, we can say, 3.2, 3.3 as extracted from these curves here. Indeed, the uncertainty over this gap evaluation is high because the measurements are very difficult. It's very difficult to extract actually optical information from the optical spectroscopy due to the strong substrate response. But the relative behavior as a function of temperature is actually the critical point here. And as you can see, the opening of the gap is also visible in the plot of the superconducting conductivity here on the right. So the gap is opening. This is the curves as a function of temperatures. Indeed, we can fit this behavior, for instance, through a model that is a phenomenological model where K defines symmetry, the pairing symmetry for the superconducting gap. However, due to the strong uncertainty over the values, it's difficult to have a conclusion over the pairing symmetry from optical spectroscopy. As you can see, the fitting of two different Ks for S wave and D wave are pretty similar, and therefore it's very difficult to extract correct information. One last thing, from, of course, the results of the normal state, the superconducting conductivity state, we can extract a value obtained from optical spectroscopy of the penetration depth through the Ferrari-Glover-Tinkham rule by studying the condensation of the spectral weight. As you can see the difference here, and we obtain a value that is comparable with other direct measurements of the London penetration depth, at least at 5 Kelvin. So in conclusion, we said the normal state analysis, and we suspect it to be in the dirty limit for the optimal doped nickelate. We find an electrodynamical behavior that is different quantitatively from cuprates. We determine through optical spectroscopy the opening of the gap of the system, and of course it's hard to extract information about the pairing symmetry due to a strong substrate influence. And as a first last remark, we extract the London penetration depth. This is the paper for reference. And I would like to acknowledge all the people that contribute to this work, in particular Rebecca Servasio, that performed the measurements at Soleil, and with Pascal Roy and Stefano Lupi for the supervision, and Ariando Riando for the samples. And thank you for your attention.
Okay, thanks a lot for the very interesting talk. Now the session is open for the questions, comments, or not.
The what there? I mean, London penetration depth measurements are just pretty new. I mean, you can find on archive the papers, and there are some debate about the validity actually of the London penetration measurements because they give different results actually. The value extracted here through the Ferrari-Glover-Tinkham rule is just the condensation of the spectral weight, meaning that you take the superconductive conductivity and with the difference with normal state conductivity, and you calculate the area, and then you link it to the penetration depth through the Lorentz frequency. And the value extracted here, 490 nanometers, is comparable with the FT results, but actually the FT results do not take in mind many properties of the nickelate, so they might have a strong error, but it's compatible with other London penetration depth measurements performed by Ariando itself that actually gave us the samples in this case. So this is the comparison that I am taking in mind. In terms of the London penetration depth, you mean? HCD. Ah, okay. Actually, I don't remember right now, but from resistivity measurements, just from the resistivity measurements. I don't know.
Any other questions? If not, let's thank our speaker again, and I'd like to, sorry, any questions?
I have difficulties in hearing you. Delta over TC. I mean, we are delta over TC. No, we are not comparing it actually, but if you go back in the, this has been done in tunnel spectroscopy measurements already that are here, because our optical gap that we extract is pretty similar to these values here in terms of absolute values. So this has been performed in this paper.
Let's thank the speaker again for the very interesting talk, and thank all the speakers of the last session.